today we will start our next chapter, that is chemical bonding. This is chapter number 4 of class 11. Now, chemical bonding, as the name suggests, it is related to chemical bonds. And you know, chemical bonds are formed between atoms. So, first question is, why do atoms combine? Atoms combine क्यों करते हैं? तो सबसे पहले जो कॉसेल और जीएन लुइस उन्होंने सोचा कि नोबल गैसेस जो है they exist independently and rest of the atoms they combine to form a molecule containing same atoms or different atoms. So question arises कि why do other elements, other atoms combine and noble gases are independent existence. Noble gases have independent existence, like you know, helium, neon, argon, krypton, xenon. When we see their configuration, you know, helium is 1s2. This is helium 2s2 2p. 6 argon, neon 3s2 3p. 6 krypton, argon 3d10 4s2 4p. 6 then krypton and 4d10 5s2 5p 6. Likewise, so you can see the pattern. In the valence shell there are 8 electrons, except in helium where there is duplet. In rest of them, in the valence shell there is complete octet of electrons. There are 8 electrons. In neon, in the second shell, there are 8 electrons. In argon, third shell has 8 electrons. Krypton, in the fourth shell, there are 8 electrons. In xenon, in the fifth shell, there are valence shell, outermost shell, has 8 electrons each. Okay, so that will give rise to octet rule. So first theory to answer this why do atoms combine is because of octet rule. So what is octet rule? That atoms can combine either by transference of electron, by sharing of electrons, in order to complete their octet. That is called octet rule. There are so many limitations of this rule, but octet rule is successful in explaining many things about the chemical combination of the atoms. First of all, if you say the electronic configuration of noble gases, every atom tries to attain noble gas configuration. Okay, and that's why atoms combine to get stable outermost shell, stable configuration in the outermost shell. Okay, so first of all, let us discuss Kossel-Lewis approach. Kossel-Lewis approach to chemical bonding. in 1916, Lewis and Kossel stated that atoms can combine either by sharing of electrons or by transference of electrons in order to complete their octet or in order to attain noble gas configuration, and that's the reason they combine with each other. Okay, so they can form, in case of diatomic, they can form homodiatomic or heterodiatomic molecules, or maybe more than that. But in case of diatomic, there are two types of molecules: homodiatomic and heterodiatomic. Homodiatomic molecules means molecules having same atoms. For example, H2, O2, N2, Cl2, so on. Okay. Heterodiatomic means molecules having different atoms. Two atoms of the molecule are different. For example, HCl, okay, CO, HF, and so on. This is called octet rule. This statement, okay, you know now the homodiatomic and heterodiatomic. So this statement, this is called octet rule, right? Okay. Now you can say that atoms actually combine to acquire noble gas configuration. This is the octet rule, and in case of helium, that is duplet. For hydrogen, octet rule is not applicable, so rule of duplet is applicable because helium has 2 electrons. Except helium, all other noble gases have 8 electrons in their valence shell. That's why octet rule is covering wide number of molecules. Okay. Now, Lewis symbols for representing valence electrons. Okay. For example, if we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, these are ordinary symbol of atoms. In lithium, we have how many valence electrons? 1. So these dots represent the number of valence electrons. So with dot, it becomes Lewis symbol, and this is also known as electron dot symbol. better to write like this. Okay. Lithium has one valence electron, so one dot is representing the Lewis. Lithium is ordinary symbol, and lithium with one dot is Lewis symbol. With two dots, beryllium with two dots, that is Lewis symbol for beryllium. Boron with three dots, carbon with four dots, nitrogen with five dots, oxygen with six dots, fluorine with seven dots. Okay, so these are called valence electron. So valence electron, these are the Lewis symbols, and valence electron is equal to number of dots. Also called Lewis symbols or electron dot symbols. Okay, you know electronic configuration of each one of them. Okay, for example, for sodium, this is the ordinary symbol for sodium. So with one dot, that become its Lewis symbol. Right? So I think you can write Lewis symbol for any atom. Am I right? Okay. Now, significance of Lewis symbols. What is the significance of Lewis? So Lewis symbols are the element with, means symbol of the element with dots representing number of valence electrons. What is Lewis dot structure? The ordinary symbol of the atom with number of dots equal to number of valence electrons. Right? Now let us discuss the significance of Lewis dot, Lewis dot structure. Okay, here simply Lewis symbol. So significance, first is they represent number of valence electrons. Means number of dots represent number of valence electrons. Second, valence is equal to either n or 8 minus n. And if n is less than or equal to 4, and 8 minus n if n is greater than 4. Okay, and n is number of dots or equal to number of valence electrons. And you know valency means combining capacity of an atom. Valency is combining capacity of an atom. Then third is Lewis symbol of, for example, you know that Lewis symbol of nitrogen is, Lewis symbol of oxygen is O. It is like this. That means number of valence electrons, that is equal to number of dots equal to 6. And what is its valency? Because it is greater than 4, so valency is 8 minus n, so valency is 2. So in this way we can calculate valency as well as valence electrons. So there is a lot of information hidden in the Lewis symbol. Okay, and that will also give us an idea that how many electrons it needs to complete its octet. Say it has 6 electrons. So how many electrons it will share to complete its octet? Obviously 2. So it's combining its valences 2. Right? So in this way, this is what we can predict or we can determine by looking at the Lewis symbol. Okay? So this is significance of Lewis symbols. So if question is what is Lewis symbol and what is its significance, you can write like this. It is most simple question, a most simple chapter, most informative chapter, most basic chapter, and very, very important for the even competitive exam. Okay, so every lecture is very important for chemical bonding because it is used in class 12th as well. Some facts stated by Kossel in relation to chemical bonding. So first is stated that halogens and alkali metals, they are separated by noble gases because they are extreme right and extreme left. They are to the extreme left and extreme right. Okay, separated by noble gases. That's why they are most electronegative and most electropositive. Alkali metals and halogens. Alkali metals are most electropositive, halogens are most electronegative because halogen needs 1 electron to complete its octet and alkali metals lose 1 electron to attain noble gas configuration. That's why both are most reactive elements. So first is in the periodic table, highly electronegative halogens, that is group 17, and highly electropositive alkali metals, that is group 1, are separated by noble gases, separated by noble gases, that is group 18. So this is the first statement or fact given by Kossel that in the periodic table highly electronegative halogens, that is group 17, and highly electropositive alkali metals, that is group 1, are separated by noble gases. Okay, that is separated by noble gases, and these are means halogens are present in the extreme right and alkali metals to the extreme left separated by noble gases. Okay, this is the first statement. Then atoms of the element, this is the first fact. Atoms of halogen family. Atoms of halogen family means fluorine, chlorine, bromine, iodine. Okay, so the atoms of halogen family change into anions by gaining one electron and atoms of alkali metals lose one alkali metals change into cations by losing one electron. This is the second statement. For example, sodium. You know Lewis dot structure of sodium is this. So after losing one electron, it is cation, and chlorine, it has 7 electrons. So after gaining one electron, it forms anion. Halogens form anion, alkali metals form cations. Both cations and anions acquire noble gas configuration. Acquire noble gas configuration, right? Because you know sodium has 11 electrons. So after losing one electron, it acquires configuration of neon. And chlorine has 7 electrons. After gaining one electron, it acquires noble gas configuration of argon. Right? Okay. So now the negative and positive ions are stabilized. The negative and positive ions are stabilized by electrostatic force of attraction between oppositely charged ions, which is called, this is called electrovalent bond. This is the statement of electrovalent bond or can call it as ionic bond. Means electrostatic force of attraction between positive and negative ion, between cation and anion, is known as electrovalent bond or ionic bond. So these are the facts stated by Kossel. Means Kossel give us information about the ionic bonding between the atoms. Okay, after formation of cation and anion. Okay, and electrovalency. Electrovalency is number of electrons gained or lost by an atom in the formation of cation or anion. For example, what is the electrovalence of sodium? You know, sodium is Na1 plus, so it loses one electron. So we can say it is number of positive or negative charge on the ion. Okay, so sodium has electrovalence of 1. Cl, again it gain one electron, so its electrovalence is again 1. It is number actually, magnitude. Okay, it is electrovalence is not -1. It is 1 because it gain one electron, it lose one electron, so it is number. Okay, so tell me, what is the electrovalence of magnesium and aluminium? So magnesium, because it loses 2 electrons, that's why electrovalence of magnesium is 2. Aluminium, you know, it loses 3 electrons to acquire noble gas, so its electrovalence is 3. Electrovalency of sodium, magnesium and aluminium is 1, 2 and 3 respectively. Now, how many types of bonds are possible? So you know, there may be covalent bonds, there may be ionic bonds, there may be coordinate bonds. Covalent, coordinate bonds. So let us discuss about them. Okay, so modes of chemical means types of chemical bonds. Types. So as I said, covalent bond, coordinate bond and ionic bond. So first is by electron transfer. Electron transfer means by gaining electron or by losing electron. Okay, so this electron transfer, so the bonds we have discussed now, only the bonds formed by transference of electrons. Transference of electron is gaining or losing electron. Ionic or electrovalent bond. That we have discussed. Okay. Second is by electron sharing. Now, by electron sharing, one sharing is equal contribution from both the atoms. Means if first atom contribute one electron, then other atom also contribute one. So that is called mutual sharing of electrons. Okay, so that sharing is called, the bond formed by mutual sharing of electrons is known as covalent bond. Second is the bond formed by mutual sharing of electrons. Is called covalent bond. Okay, and third type is, it is again sharing of electrons. The bond formed by sharing of electron, but shared pair is provided by only one atom. Both share, but shared pair is provided by only one atom. That is called coordinate bond. Okay, now I will explain what it means. See, first type, ionic bond. Let us have sodium and chlorine. So you know, sodium has one dot, means one valence electron, and chlorine has 7 valence electron. So if this sodium transfer its electron to chlorine, both acquire noble gas configuration. Sodium becomes sodium 1 plus and chlorine becomes chlorine 1. So this electrostatic force of attraction between this cation and anion is called ionic bond, because this bond is formed between oppositely charged ions by the transfer of electrons between the atoms. Okay, second, let us take nitrogen. Nitrogen has 5 valence electrons. Other nitrogen also have 5 electrons. Both need 3 electrons to complete their octets. Actually, covalent bond is formed between non-metals. So say, if they share 3 electrons with each other, means there is a mutual sharing of equal number of electrons. So this type of bond is called simple covalent bond. Okay, now third type. Third type is, for example, we have see, nitrogen can form 3 bonds. Okay, let me have this whole space. See, nitrogen, you know, it has 5 valence electrons. Out of 5, it needs 3 more to complete its octet. So now see, if one hydrogen is there hydrogen has one electron and it need one more to acquire configuration of helium, so it will share one electron. So in this way each hydrogen form one covalent bond, means this is the structure. It has 3 shared pair and 1 unshared pair. 3 shared pairs and 1 unshared pair. This is also called lone pair. Now let us talk about boron. In boron, it is like this. Boron has 3 valence electrons, right? So it can form 3 bonds with any other atom like fluorine. Fluorine has 7 valence electrons. It needs 1 more electron to complete its octet. So in this way we get BF3. See here, this ammonia has octet of electrons. Ammonia has 8 electrons in its valence shell. 1, 2, 3, 4 pairs. In total 8 electrons. So ammonia has octet. In ammonia, is it visible? Yes. In ammonia, nitrogen has octet of electrons, and at the same time it has 1 unshared pair. Such a molecule is called electron-rich molecule. Any molecule in which central atom, this nitrogen is central atom, has complete octet of electrons and has unshared pair, so that is called electron-rich molecule. Okay, so ammonia is electron-rich molecule. Got it? Now come to BF3. In BF3, can I write? Yes. In BF3, boron has 6 electrons. It has sextet of electrons. Means, say first is electron rich because it can donate this pair. Sorry, it can share this pair with any other molecule. Not donate, but can share. Okay, but BF3, boron has 6 electrons. It is deficient of electrons, means it has not completed its octet. So such molecules are called electron deficient molecule. Means any molecule in which central atom has less than 8 electrons, that is called electron deficient molecule. One is electron rich, other is electron deficient. So electron rich can donate its pair or can share its pair with other molecule or atom. So such a molecule which is electron rich is called Lewis base. That is called Lewis base. And this molecule because it has tendency to gain electrons. The one which has tendency to lose electron is called Lewis base, and the one which has tendency to gain electrons is called Lewis acid. Is it visible? Yes. So I can write it is Lewis acid. So Lewis acid is one which can gain electrons. One which can gain electrons is called Lewis acid, and one which can donate electrons, that is called Lewis base. So now let us write them like this: nitrogen of ammonia with one pair, boron of Bf3 without any electron pair, and it needs two more electrons. Now there is a compromise. See, this nitrogen, if it share this whole pair with boron, like there is a sharing, but shared pair is given by the single atom. Such sharing leads to the formation of bond, a special type of bond, and that is called coordinate bond. That is called coordinate bond, and this arrow indicates the donor and acceptor. The arrow is from the donor to the acceptor. Means this donate the whole pair for the sharing, and this will accept the shared pair of electrons without giving any single electron. But what is the benefit of doing that? Both have octet of electron now. Both have octet of electrons. इसमें किसी का कोई घाटा नहीं है, ठीक है? Rather, BF3 got satisfied by forming this type of bond, because earlier only ammonia has, in the central atom of ammonia has complete octet of electron, but once the bond is formed, both nitrogen as well as boron, now they both have complete octet of electrons. And one more thing, once this bond is formed, there is no difference between covalent and coordinate bond, but coordinate bond is slightly stronger. Why is it so? Because if we write it like this, then boron gets negative and nitrogen gets positive charge. So there is covalent bond when one electron is shifted from nitrogen to boron. Like see, nitrogen with one electron, so it gets positive charge. Boron with one electron, so it gets negative charge because it gained one electron. Now this is sharing. So if we form simple covalent bond, then donor gets positive charge and acceptor gets negative charge. So this is also the symbol which represents this arrow. If we write arrow, then there is no charge shown on boron and nitrogen. But if we form simple covalent bond, then acceptor gets negative charge and donor gets positive charge. So these are the symbols for coordinate bond. So coordinate bond is slightly stronger because of this development of charge than the covalent bond. And you know ionic bonds are strongest, right? Do one more, that is for calcium fluoride, and then we will stop our discussion for today. Coordinate bond, I think you could figure out. One more example I can give, like ammonia and H plus. So you know H plus means with no electron. So if it form bond with H plus, there should be a coordinate bond, because bond is formed between nitrogen and hydrogen, but hydrogen will not contribute. Okay, if hydrogen will not contribute, obviously nitrogen will give its pair for sharing. So this is the case of NH4 plus. So NH4 plus has 3 covalent bonds and 1 coordinate bond. Okay. Now CaF2. CaF2. Yes. So in CaF2, you know calcium. Calcium has 2 electrons. Am I right? Fluorine has 7 electrons. So calcium will donate 1 electron each to fluorines. So calcium is 2 plus and F 1 negative, F 1 negative. So in this way, the ionic bond formed between calcium 2 plus and fluoride ion. Okay. And what is the electrovalency of calcium? So electrovalency of calcium is equal to electrovalency of fluorine as well. 2 and it is 1. And this is called electrovalent bond or ionic bond. Last lecture we have completed what is ionic bond. So ionic bond is the Coulombic force of attraction between the oppositely charged ions. Means electrostatic force of attraction between the oppositely charged ions. Means ionic bond. So ionic bond is, it is electrostatic force of attraction ionic bond is electrostatic force of attraction between oppositely charged ions. It is called electrostatic or Coulombic force of attraction between cation and anion. So now we will discuss factors influencing the formation of ionic bond. Factors. So there are factors which influence the formation of ionic bond. So first factor is ionization enthalpy. It is the amount of energy required to remove an electron from an isolated gaseous atom. Means energy required to form cation actually. energy required to remove an electron from an isolated gaseous atom. That means if energy required to remove the electron is less, then cation can be easily formed, because to form an ionic bond we need a cation as well as an ion, and the attraction between them is the ionic bond, right? So first and foremost thing is we should have cation and anion. So if cation is formed easily, the chances for the formation of ionic bond is more. First factor is lesser is the ionization enthalpy, more is easily cation is formed. More easily cation is formed. So cation formation is easier if energy required to remove the electron is less. So tell me which metals, obviously cation is formed by metals, because metal has greater tendency to lose electrons. And what about non-metals? They have a tendency to gain electrons. So obviously the cation formation is easier for metals. So tell me which metals can form cation most easily. Group 1 elements, because along the period ionization enthalpy increases. So the elements present to the left have greater tendency to form cation because their ionization enthalpy is lowest. Alkali metals and alkaline earth metals, group 1 and group 2, alkali metals and alkaline earth metals can form cation because they have lowest ionization enthalpy in the periodic table. Means these are alkali metals and alkaline earth metals are combinedly known as S block elements. So S block elements they can form cation easily. That means they can form ionic bond easily because they have low ionization enthalpy. So favorable factor as that of ionization enthalpy, with regard to ionization enthalpy, low ionization enthalpy is in favor of ionic bond formation. So low ionization enthalpy of the element and particularly metal. Okay. Now second factor. Second factor is electron gain enthalpy. Electron gain enthalpy, that is electron gain enthalpy. So electron gain enthalpy, as the name suggests, it is electron gain. That means amount of enthalpy change when an electron is added to an isolated gaseous atom. Say if we have B atom in the gaseous state and after gaining electron it forms anion. So how much energy change takes place, that is called electron gain enthalpy. So when electron is added, Say, when electron is removed, that is for ionization, there is a work against attractive force between the electron, which is to be removed, and the nucleus. There is an attraction between the electron and the nucleus. So, to remove it, we have to provide energy. But when electron is added, so it should be attracted by the nucleus. This extra electron from the outside, if it is added to the atom, it is attracted by the nucleus. So when there is an attraction between the nucleus and the added electron, there should be a release of energy. Energy should be released. Okay, and if energy is released, say energy absorbed has sign convention positive sign. Okay, for energy released, it has a negative sign. Okay, so electron gain enthalpy should be negative. First of all, first and foremost condition is when electron is added to an isolated gaseous atom, electron gain enthalpy should be negative. And higher the negative value of electron gain enthalpy, more easily anion is formed. Like lower ionization enthalpy, then more easily cation is formed, and higher the negative value of electron gain enthalpy, more easily anion is formed. So, in favor of anion formation is the higher negative value of electron gain enthalpy. So, electron gain enthalpy should be high. Negative sign only indicates that energy is released. Okay, that is the most of the atoms, when electron is added, energy is released, except in noble gases or fully filled configurations. Okay, when electron is added in noble gases, they are already stable, so they become unstable, so their energy is increased, means they absorb energy, so their electron gain enthalpy is positive. That's why they cannot form anion. Okay, so anion is formed easily by those atoms having higher negative value of electron gain enthalpy. So this is the second factor. First factor is ionization enthalpy should be low, electron gain enthalpy should be more negative. So second factor, which is in favor of ionic bond formation, is high negative value of high negative value of electron gain enthalpy. Low ionization enthalpy and high negative value of electron gain enthalpy. So, if ion enthalpy of metal, right, is low, cation is formed. If high negative value of electron gain enthalpy is for non-metal, anion is formed. Now we get cation and anion. Now third is lattice enthalpy or lattice energy. Do you know what is lattice? Lattice means arrangement of, it is three-dimensional arrangement of particles. 3D arrangement of particles. For example, if a wall is formed, we have to arrange bricks to form a wall. To form a wall, what we do? We arrange the bricks in 3D, right? So that is one type of lattice. Okay, so three-dimensional arrangement of particles like atoms, molecules, or ions, right? So that is called lattice. Okay, now in ionic bonds there is arrangement of cation and anion, right? So lattice enthalpy with regard to ionic bonding. So what is the definition? The energy released. So this 3D arrangement give rise to formation of a solid. Okay, so lattice energy is amount of energy released when 1 mole of crystalline solid is formed by the combination of oppositely charged ions. Okay, cation, anion. I will write one lattice of NaCl, then you will come to know how the lattice looks like. Okay, but anyhow, what is lattice enthalpy? Amount of energy released when 1 mole of crystalline solid. Crystalline means a regular arrangement. Okay, crystalline means when there is a regular arrangement, like in the morning there is a prayer in the school. So during prayer, or we can say during national anthem, everybody is standing in a straight line. Okay, so those straight lines in the school, that means that shows the arrangement of the assembly. Okay, so that type of arrangement is called crystalline, and its opposite is amorphous, recess time. Recess time, everybody is in the random state, everybody is moving here and there are different groups. Okay, so there is randomness in the arrangement. That random arrangement is amorphous. Crystalline, opposite of crystalline is amorphous. Amorphous means random arrangement. And crystalline means regular arrangement. Okay, uniform arrangement. Okay. Okay, so amount of energy released when 1 mole of crystalline solid is formed by the combination of oppositely charged ions, because when there are oppositely charged ions neighboring in the neighborhood, what happened? There is a force of attraction, and whenever there is a force of attraction, energy is released. Okay, so how much energy is released, that depends on the attractions. More are the attractions, more is the energy released, and more is the lattice enthalpy, and higher is the lattice enthalpy, higher are the chances for the formation of ionic bond. Got it? So higher the lattice enthalpy, that means it can be represented as A plus gas plus B negative gas to give AB solid. This is crystalline solid. These are gaseous ions. When they are arranged in 3D, we get ionic solid, and energy released here is called lattice enthalpy. So actually lattice enthalpy is the amount of energy released. That's why higher is the lattice energy or enthalpy, higher is the lattice enthalpy, more is the attraction between oppositely charged ions. More is the attraction between oppositely charged ions, and greater is the stability of ionic bond. Okay, so that means if we say the factors which influence the formation of ionic bond, first is low ionization enthalpy, second is higher, or we can say high negative value of electron gain enthalpy, and third is high lattice energy. Right? So these are the factors which influence the formation of ionic bond. If lattice enthalpy plus negative value of electron gain enthalpy is greater than ionization enthalpy, then ionic bond is formed. Okay, and if lattice enthalpy plus negative value of electron gain enthalpy is less than ionization enthalpy, then ionic bond is not formed. That's it. General characteristics of ionic compounds. Okay, so let us take a case of NaCl. Okay, now NaCl, to have NaCl 1 mole, we need 1 mole of Na plus and 1 mole of Cl negative. They are arranged in 3D. Say like this. NaCl has cubic structure. Now I will make a cube Is it visible? Yes. See. Okay. So this is the cube. Okay. Now NaCl has cubic lattice. NaCl has cubic lattice. Now this lattice I will divide into two equal halves. These are two equal halves. Then from here, four halves. Okay, it is, this cube is divided into four halves. Okay, then okay. Now tell me how many parts this cube has. How many small cubes this cube has? This bigger cube, I have divided it into small cubes. How many small cubes? 1, 2, 3, 4. This one is 1 cube. Okay. 1 cube, and then second cube, third, fourth, fifth, sixth, seventh, eighth. So there are 8 parts. Okay. Now let us start from here. Suppose this is Cl negative and this is Na plus. Okay. So you know, if here it is Cl negative, next one is Na plus, again Cl negative, Na plus, 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 Cl negative, again Na plus, Cl negative, Na plus, Cl negative, Na plus, Cl negative, again Na plus, Cl negative, Na plus, Cl negative, Na plus, Cl negative. Then, okay, Na plus, Cl negative, Cl negative, Na plus. Done. So there are Na plus, Cl negative. Na plus means at alternate position there are Na plus, and each Na plus is surrounded by Cl negative, and each Cl negative is surrounded by Na plus. Okay, arrangement is called a lattice, and when in this type of arrangement 1 mole of cation 1 mole of Na plus and 1 mole of Cl negative are arranged like this. Na plus gas and Cl negative gas, when they are arranged to form NaCl solid 1 mole, so energy released is called lattice energy. That energy is called lattice energy, and this arrangement is called a lattice. This is NaCl type lattice. Yes. So characteristics. So in ionic compounds, oppositely charged ions are arranged in 3D, and there is a strong electrostatic force of attraction. That's why, what is their physical state? Tell me, what is the physical state of ionic compounds? Very good. It is always solid. So ions are arranged in 3D to form lattice, and there is strong forces of attraction. There are strong electrostatic force of attraction. Between oppositely charged ions. So they exist as solid. So first thing, physical state. So ionic compounds are always in solid state. Okay. Second, melting and boiling points. Melting and boiling point is always high because there are strong inter-ionic attraction. There are strong inter-ionic attractions between oppositely charged ions. So they have high melting point as well as boiling point. Electrical conductivity. That is very, very important point. Electrical conductivity. Ionic compounds are bad conductor of electricity. In solid state because there is no movement of ions in solid state, and ionic conductivity is due to the movement of ions. But in molten state or in aqueous solution, ions are free to move. So they are good conductor in molten state or aqueous solution. So you should write that in ionic compounds, electrical conductivity is due to movement of ions. First statement should be that electrical conductivity is due to movement of ions. So electrical conductivity is due to movement of ions, and they are bad conductor of electricity in solid state because ions are not free to move, because there is a strong electrostatic force of attraction. So ions are fixed in solid state, they are not free to move because there is no free movement of ions, or we can say there is no movement of ions in solid state. Got it? Good. Now let us talk about solubility. So this is the third characteristic of ionic compounds. Now solubility. Keep in mind, here we write like dissolves like. Like dissolves like. This is the formula of, this is the principle of solubility. Okay? Means polar compounds are soluble in polar solvents non-polar compounds are soluble in non-polar solvents. So actually ionic compounds they are extreme case of polarity. Say polarity means like we have HCl. In HCl, Cl gets partial negative, hydrogen gets partial positive due to the difference in electronegativity. Cl is more electronegative, hydrogen is less electronegative. Like these are the poles, negative pole, positive pole. More electronegative means electrons shared pair is more attracted towards Cl. It is away from hydrogen and close to chlorine. Unsymmetrical distribution of electrons. Like if we have H and H, it is obviously non-polar. If we have Cl and Cl, bond pair remains in between these two. Bond pair remains between two chlorines. Bond pair remains between two hydrogens. So these are the non-polar bonds. But here it is polar bond. Okay? Or polar molecule. Now in case of ionic compound, NaCl. So Na has complete positive, Cl has complete negative. That this is the extreme case of polarity. Ionic compounds are extreme case of polarity. That means polar compounds or ionic. Ionic or polar compounds are soluble in polar solvents. Okay. Polar solvents like H2O. In H2O, we have oxygen and two hydrogens. oxygen has 6 valence electrons. Out of 6, 2 are shared. So it is left with 2 lone pairs. Out of oxygen and hydrogen, which one is more electronegative? Obviously oxygen. So oxygen gets partial negative and hydrogen gets partial positive. So in this way, water is a polar solvent. Water is a polar solvent. Okay, but benzene, CCl4 are non-polar, or we can say organic, or non-polar solvents. So they are not soluble in non-polar solvents. Now see, we have NaCl solid. So NaCl solid, when dissolved in water, we get Na plus aqueous plus Cl negative aqueous. NaCl solid, when dissolved in water, we get Na plus Aq. Aq means aqueous. Cl negative, Aq means aqueous. What it means actually? See, NaCl, when it is converted into Na plus aqueous, Na plus gas and Cl negative gas, up to this stage, it is called lattice energy. Means lattice energy is defined in 2 ways. First is amount of energy released when 1 mole of ionic solid is formed from its gaseous ions. From these ions, 1 mole of ionic solid is formed. This is called lattice energy, but definition is amount of energy released when 1 mole of ionic solid or 1 mole of crystalline solid is formed from its constituent gaseous ions, or amount of energy required to break 1 mole of ionic solid into its gaseous ions. Energy is absorbed. Here energy is released and here equal amount of energy is absorbed. So I can define lattice energy in second way, that is amount of energy required to break 1 mole of ionic solid into its gaseous ions and vice versa. Okay, so this is lattice energy. Now these ions, when interact with water, we get Na plus aqueous, Cl negative aqueous. How it is formed? See, this is Na plus. So Na plus in water, it is like this, negative, positive. So Na plus, O negative is attracted towards Na plus, so it is like this. Water around Na plus, and what about Cl negative? Hydrogen is towards Cl negative. So So this is called hydration. When water interact with cation and anion, this is called hydration. So amount of energy released, because Na plus and hydration enthalpy. This is called hydration enthalpy. Amount of energy released, amount of energy released when amount of energy released as a result of attraction between ions formed from 1 mole of ionic solid and water. Ions जो बने from 1 mole of ionic solid, when they interact with water, the energy released is called hydration energy. Say here energy is absorbed, here energy is released. So if hydration enthalpy is low, is high, or lattice energy is low, they favor the solubility of ionic compounds in water. That means hydration enthalpy should be high, lattice enthalpy should be low, then solubility is high. So ionic compounds actually they are soluble in water, but because hydration enthalpy is high. What is hydration? Water surrounding the ions, and because of this arrangement of water or water surrounding this ion, there is an attraction, and due to that attraction energy is released, and that energy released is called hydration energy. Okay, and most favorable factor is lattice energy should be less than hydration enthalpy, then solubility is high. Okay, so this is about solubility and hydration energy. So you got what is hydration? Yes, anybody who has doubt? Beta, only 2 minutes more. Yes, less lattice energy and high hydration enthalpy, more soluble compound. Okay. Now last is ionic reactions. This is 5th point. So ionic reactions, say covalent compounds give molecular reactions, ionic compounds give ionic reactions. So keep in mind ionic reactions are fast, because there is only rearrangement of ions. There is no breaking or formation of bonds. Okay, For example, if we have AgNO3 along with NaCl, then we get AgCl solid plus NaNO3 aqueous. Actually, in this case, if we look at this reaction, AgNO3 aqueous means it is simply in the form of Ag plus and NO3 negative. Already it is in this form in the solution. NaCl aqueous means it is already in this form. So there is no need to break it. They are already in ionic state. Okay. So Ag plus will choose Cl negative and form AgCl solid, which is white PPT. You know AgNO3 is test for chloride ions. Okay, white PPT along with Na plus aqueous and NO3 negative aqueous. So, in nutshell, ionic characteristics are ionic compounds are solid. They have high melting and boiling point. They are bad conductor in the solid state, but very good conductor in molten or aqueous solution. Then they are soluble in polar solvents like water, and ionic reactions are fast. So these are characteristics of ionic compounds. I repeat once again, ionic compounds are solid, ionic compounds have high melting and boiling point. Ionic compounds are a good conductor in molten state or aqueous solution, but bad conductor in solid state. Then ionic compounds are soluble in polar solvents like water. Then ionic reactions are fast. In the last lecture we have completed about ionic bond. You know, ionic bond is formed by the transfer of electrons from the more electropositive to more electronegative atom. There is a formation of cation and anion, and there is electrostatic force of attraction or Coulombic force of attraction between oppositely charged ions, and that is called ionic bond. Now, covalent bond. Covalent bond is formed by the mutual sharing of electron. The bond, first of all, the bond formed between non-metals is generally covalent bond, and this type of bond is present in most of the compounds. It covers large number of molecules. So there are many theories which explain the chemical bond which is called covalent bond. So there are different theories. To explain covalent bond. So for the explanation of covalent bond, there are different theories. First theory is given by Lewis Langmuir. That is called Lewis Langmuir theory. Second theory is Valence bond theory. And third one is molecular orbital theory. All the theories are covered in this chapter. Lewis Langmuir theory, that is most basic theory about covalent bond, and then we will discuss Valence bond theory, and at the last we will discuss molecular orbital theory. So first of all, let us discuss this one. Theory about the explanation of covalent bond. Actually, the Langmuir in collaboration with Lewis, introduced a new type of chemical bond known as covalent bond. And according to Langmuir and Lewis, the bond formed by contribution and mutual sharing of electrons is called covalent bond. The bond formed between two atoms, and these two atoms may be similar or different. Bond formed between two atoms by contribution and mutual sharing of electrons is called covalent bond. And you know, they may share one pair or two pair or three pair of electrons, and accordingly they leads to the formation of single bond, double bond or triple bond respectively. Means if two atoms say if we have A atom, each atom contribute one electron and share with each other, then there is a formation of single bond. If A atom share two electrons, B atom also share two electrons, then there is a formation of double bond. A atom share three electrons, B atom also share three electrons, then there is a formation of triple bond. That means if atoms share one electron each, then we have a single bond between two atoms. If they share two electrons each, then there is a double bond. If they share three electrons each, then there is a triple bond between two atoms. But what would happen when they form single, double or triple bond? You know, there is more bonding in triple bond than double than single. That means A atoms are closest in triple bond and farthest in single bond. Same is the case with different atoms. If atoms are similar, they are called homoatomic molecules. Homoatomic means if there are only two, then that is called homodiatomic molecules. If there are three, they are called homotriatomic molecules. Three similar atoms. Okay? Like O2 is homodiatomic. O3 is homotriatomic. And if atoms are different, they are called heteroatomic molecules. Means different atoms, they are called heteroatomic, same atoms, they are called homoatomics. Okay, like A single bond B, A double bond B, A triple bond B. They are hetero-diatomic. They are homo-diatomic. I think you would understand homo-diatomic, hetero-diatomic. Two atoms in the bond, if they are different, they are called hetero-diatomic. If two atoms in a bond are similar, they are called homo-diatomic. Okay? Now let us discuss H2. This is the most simple homodiatomic molecule. Homodiatomic molecule. Now in H2, tell me how many bonds are there? Single bond, because each hydrogen contribute one electron. Okay, so you can write it like this. So each hydrogen has attained noble gas configuration of helium. Okay, so this is called Lewis structure. If there are dots representing the bond, then that is called Lewis structure. And if there is a line, single line, double line, triple line, or we can say dash between single dash, double dash, triple dash, they are called Couper structures. Not Couper. R is silent. That is called Couper. I can write in Hindi. Couper, okay? R is silent. If there are lines, or we can say there is a line between two atoms, single line, double line, triple line, to represent the bond, they are called Couper structures. And if there are dots, electron dot represent Lewis symbol. So if there are dots representing the bond, that is called Lewis structure. Okay? Done. So H2 likewise O2. Oxygen has atomic number 8. It needs 2 more electrons to acquire noble gas configuration. It has 6 valence electrons. So 2 electrons shared between each other. So there is a formation of double bond. What about fluorine? F2. Only one, because fluorine has atomic number 9. It has 7 valence electrons. If it shares 1 electron, each fluorine will acquire octet of electron. So fluorine, there is single bond. Okay. What about nitrogen? N2. Nitrogen, it has atomic number 7. So nitrogen share 3 electrons, because it is 2, 5. So when it shares 3 electrons, each nitrogen acquire noble gas configuration, and it is like this. Yes, what about methane? Carbon, because carbon has 4 electrons, valence electrons, So each fluorine share each carbon share one electron with hydrogen. So it complete duplet of each hydrogen and octet of carbon. Okay, so in this way this is methane. Okay, so in methane this is Lewis structure and this is Couper structure. Okay, because first time Couper let us know that if they represent this one pair by this line, it will be okay. Means these lines represent the bond. This dash represent the bond. That's why they are called Couper structures. What about H2O? H2O. In H2O, oxygen has 6 electrons. Hydrogen will contribute 1 electron each. So it will complete duplet of hydrogen and octet of oxygen. So in this way, it is water. Okay. Now ethane, C2H6. C2H6. So C2H6, it is CH3, CH3. Okay, C2H6 is CH3, CH3, or it can be represented as this is Couper structure, or it can be written as each carbon has 4 electrons, 1 electron shared between carbon, and 3 electron of each carbon share with 3 hydrogens. So each hydrogen has its duplet and each carbon complete its octet. Okay? Yes, so what about C2H4? C2H4. So in C2H4, it is CH2, CH2. Each carbon form 2 bonds with hydrogen, so 2 left. So there is a double bond. Carbon, double bond carbon, hydrogen. That means carbon share each carbon share 2 electrons with 2 hydrogens. So each carbon left with 2 electrons, and this way each carbon completes its octet and each hydrogen completes its duplet. For hydrogen, duplet. For other atoms, there is octet. Okay? Now, that means there is a double bond between 2 carbons. Now, C2H6 CH. That means there is only one bond formed with with hydrogen. Therefore, there are 3 bonds between 2 carbons. Like this. That means each carbon share 1 electron with hydrogen and 3 electrons are shared between 2 carbons. So each carbon has octet of electron, each hydrogen has duplet of electron. That's it. What about NH3? Okay, PCl3. So in NH3, nitrogen share 3 electrons with 3 hydrogens, and nitrogen has how many valence electrons? 5. So it is like this. Each hydrogen has duplet. So it is like this. PCl3, again each chlorine share 1 electron and each chlorine has 7, total 7 electrons. So each chlorine has octet of electron. Even phosphorus has octet of electron. So in this way, PCl. Now see, these bonds are called shared pairs or bond pairs. These lines are called shared pairs or bond pairs. So shared pairs or bond pairs in ammonia, this is called NH3 is ammonia, and this is phosphorus trichloride. Okay, so there are bond pairs. How many bond pairs are there? 3 unshared pairs, or we can say lone pairs equal to 1, or 3 unshared pair or lone pair in ammonia is equal to 1. Same is the case with PCl3. 3 bond pairs, 1 lone pair. Means this pair which is not shared with any other atom, that is called unshared pair. And how many unshared pairs are there? 1. But when we write H2O, in H2O there are, tell me, how many shared pairs and unshared pairs are there? There are 2 bond pairs and plus 2 lone pairs, or we can write 2 shared pairs or 2 unshared pairs. See, this line is called shared pair because it is shared between oxygen and hydrogen. It is also shared between oxygen and hydrogen, but these 2 are unshared pairs. There is no other atom which share this pair. That's why they are called unshared pairs or lone pairs. Molecular ions. Like CO3 2 negative, carbonate, SO4 2 negative, sulfate. This is called carbonate ion, and this is called sulfate ion. Now in carbonate ion, number of negative charge means number of single bonds. Two negative, so two single bonds with oxygen, and you know oxygen is divalent, oxygen form two bonds, but because there are two negative, that's why there is single bond with two oxygens. So you know this oxygen is like this, and this one it is like this. You know oxygen has 6 electrons, one is shared, so it should have 5 electrons, but because there is one negative, is 2 negative, so 2 negative are attained by 2 oxygens, 1 negative each, okay, for each oxygen. So in this way, this is the structure. What about sulfate? In sulfate there is again 2 negative and total oxygen are 4. So 2 oxygens form single bond and 2 other oxygens form double bond. 2 single and 2 double. And each oxygen should have octet of electron. So it is like this. How do we write this structure for simple molecules? Molecules or ions. What are the steps involved? That I will explain to you now. First step is count number of valence electrons. For example, let us take the case of, okay, in CO, total number of valence electrons is, carbon has 4 valence electrons, okay, valence electron oxygen has, atomic number of oxygen is 8, so 2 for helium and rest 6, total valence electrons are 10. This is the first step. Whenever we have a molecule or ion, we will calculate total number of valence electrons. Step 2. If a species is cation, then subtract number of electrons equal to magnitude of positive charge from total number of valence electrons. For For example, if we have NH4 1 plus, we have NH4 1 plus. You know, total valence electrons to calculate, you know, nitrogen has 5 valence electrons, each hydrogen has 1, but there are 4 hydrogens, so 4 into 1, and magnitude of positive charge is 1, so subtract 1 from it. So total number of valence electrons comes out to be 8 now. Okay, step 3. Step 2 means it is, if it is not a cation, we will skip step 2. We come to step 3. If species is an anion, you know anion means negative charge, then add number of electrons equal to the magnitude of negative charge, equal to the magnitude of negative charge from total number of valence electrons. Okay, so that means step 1 is for neutral molecules, step 2 is for cation, and step 3 is for anion. Okay, so for example, if we have NO2 negative, tell me total number of valence electrons. Nitrogen has 5 valence electrons, oxygen has 6 valence electrons, and what is the magnitude of negative charge? 1. So we add 1 in it. So 12, total 18. Yes, tell me about CO3 2 negative. See, there is 1 carbon, 4 electrons, 3 oxygens, each oxygen has 6 electrons, and add magnitude of negative charge. So magnitude of negative charge is 2, so plus 2, 18 plus, yes, it is 24. Very good. So for neutral molecule, we will skip second and third step. There is only first step. If we have cation, we will skip first step, come to the second step, we will skip first and third step. For an anion, we will skip first and second step. Okay, so these 3 steps are for different type of species. For a neutral molecule, we will do by first step only. If we have a cation, second step is applied. If we have anion, third step is applied. Okay, we skip other steps. Okay, now after getting total number of valence electrons, we will select the central atom. Step 4. Select the central atom. Central atom single atom in the molecule or atom of low electronegativity. Atom of low electronegativity. For example, if we have carbonate, what is the central atom? Or which one is the central atom? Yes, in this case, carbon is central atom. Okay, and in case of NO2 negative, which one is central atom? Is nitrogen. So, sorry, nitrogen. Okay, and what about NH3? Ammonia, again nitrogen is central atom. Okay, then H2O is oxygen. This is an intelligent guess, right? To select the central atom, and these are the qualities. After selecting the central atom and attach the other atom with central atom initially by single bond. Initially by single bond. Okay. So this is the fourth step. Like if we have carbonate 2 negative, so we will write carbon in the center and single bonds for other oxygens. Okay, like we have NO2 negative, we will write nitrogen in the center and oxygen like this. Okay, then after writing this, step 5. Now in step 5, complete the octet of each atom by writing appropriate number of shared pairs or unshared pairs by simply write by number of shared pairs or unshared pairs. Okay. Now this is the theoretical, these are the theoretical steps. Now these are the 5 steps. Now we will write, let us take carbonate. Okay. Total valence electrons are 24 that you have calculated. Okay. After calculating this number, you know, carbon these are the oxygens. Now you know this carbon has how many valence electrons? This carbon has 4 valence electrons. Only 3 are used. So one of the oxygen should be double bond. So all the electrons of this carbon are used up now. All the electrons of this carbon are used up. So this is is like this. This carbon and oxygen, there is a double bond, and at the same time, how many electrons left? 4. So carbon has octet of electron. This oxygen also has octet of electron. What about these oxygens? We left with 3, 3. So this is the overall Lewis structure of carbonate. This carbonate, number 2, 3, 4. Total shared pairs are 4. And number of unshared pairs, 1, 2, 3, 4, 5, 6, 7, 8. Unshared pairs are, shared pairs are 4, unshared pairs are 8. See, calculate total valence electrons. There are 10. Now, to complete octet of each atom, okay, each atom should have 8 electrons. So, in CO there are 2 atoms. So, 2 into 8 is total 16. So, shared electrons now equal to total electrons required to complete their octets minus valence electrons. Yes, this is the right formula. Stamp लगा लो इस पे. So there comes out to be 6. And shared electrons equal to shared electron divided by 2, that is 3. We will use the same formula for carbonate as well. Okay. Now, unshared electrons, that is equal to valence electrons minus shared electrons. Valence electrons minus shared electrons. So 10 minus 6, that is 4. So unshared electron equal to unshared pairs equal to unshared electrons divided by 2. So that comes out to be 2. That's right. See, first calculate valence electrons, then number of electrons required to complete the octet of each atom. That is always equal to number of atoms into 8. Okay. Then shared electrons equal to total electrons to complete octet of each atom minus valence electrons. Okay. So shared pairs equal to 3. Unshared electrons, out of valence electrons subtract the shared electron. So we get 4 numbers. So unshared electron equal to 2. Unshared pairs equal to 2. Let us apply the same for carbonate. In carbonate, valence electrons are 24 that you have calculated, and total electrons required to complete the octet of each atom is equal to, how many atoms are there? 3 oxygen, 1 carbon. 4 into 8. So 32. So shared electrons equal to electrons required to complete the octet minus valence electron, that is 32 minus 24, that is 8. So shared pairs equal to 8 by 2, that is 4. Okay. Now unshared electrons equal to valence electrons minus shared electrons, that is 24 minus 8, that is 16. So unshared pair is equal to 16 by 2 means 8. That's right. So this formula is used. First calculate valence electrons, then calculate total number of electrons to complete octet of each atom, then shared electrons, then shared pairs, unshared electrons, unshared pairs. Okay. So let us apply it for NO2 negative. So for carbonate, for carbon monoxide, there is carbon and oxygen only. there are 3 shared pairs. So there are 3 shared pairs and 2 unshared pairs. So one with each atom, and we get this type of structure. Okay. Now let us apply for NO2 negative. Calculate for NO2 negative by applying the same formula. Valence electrons, 5 from nitrogen, 6 from each oxygen, and plus 1 for negative. So total 18 valence electrons. Now electrons required to complete the octet of each atom. How many atoms are there? 2 oxygen and 1 nitrogen. 3. And to complete octet means 8 electrons in each atom. So total 24. Shared electrons equal to total electrons to complete octet minus valence electron means 24 minus 18, that is 6. So shared pairs equal to 3. Very good. And what about unshared pairs? Okay. And unshared electrons equal to valence electrons minus shared electrons. Valence electrons is 18 minus shared जो है 6, so 12. So unshared pairs equal to unshared electron divided by 2. 12 by 2 means 6. Now nitrogen is central, so there are oxygens. Shared pairs are 3. So how to distribute? 2 1 2 1 or 1 2. You can write 2 1 or 1 2. Total shared pairs are 3. So you can distribute like this only. Because if there are 4, you can write 2 2 or 3 1 or 1 3. But if there are 3 only, there is only one option. That is 2 1 or 1 2. And whole negative. So tell me, how many lone pair I will attach to this? This oxygen has total 4 electrons, 2 plus 2. So it need 2 more to complete its octet. What about nitrogen? How many lone pair I will attach? For nitrogen I will attach 1 to complete its octet, because 1 2 3 6 electrons already it has, so 2 more electrons are required. This oxygen 3. So see 1 2 3 4 5 6. Here 3 1 2. That's it. Right? Lewis dot structure of CO2. So for CO2, you know, total number of valence electrons are 4 from carbon and 6 from each oxygen. So total valence electrons are 6, and total number of electrons required to complete their octets is 3 into 8, that is 24. So number of shared electrons equal to total electrons required to complete octet minus valence electron, that is 24 minus 16. So 8. That means shared pair is equal to number of shared electrons divided by 2. That is shared pairs are 4, and unshared electrons, that is equal to valence electrons minus shared electrons. So valence electrons are 16 and shared electrons are 8. So 8, so unshared electrons are divided by 2, that is 4. So 4 shared pairs and 4 unshared pairs, right? So best way to distribute around central atom is 2 2, but it can be 1 3 or 3 1. If there are 3 bond pairs, there is only 1 bond pair. If there are 1 bond pair, then there are 3 lone pairs. Here 2 2. In this case, so these are the structures for Lewis structures for CO2. Okay? Okay, no worries now, but next time please keep in mind that you should submit the assigned task. Okay? So this is for CO2. Okay? So Lewis structure for CO2 is this one. These are the Lewis structures of CO2. Now, formal charge. Say charge on the molecule, charge on the ion is charge as a whole on, means charge on the molecule on ion is sum of the apparent charges on individual atoms, right? Charge on the ion is actually the sum of the apparent charges on the individual atoms, and total sum of apparent charges on all the atoms in a molecule is equal to 0. So this is the funda behind the total charge. Now, if we assign charge on each atom, that is called formal charge. It is not actual charge on the atom, but if we assign the charge on the basis of electrons, that is called as formal charge. That means formal charge is the charge on individual atom, okay, on the basis of covalent bonding. So formula for formal charge is formal charge on any atom is equal to valence electrons on each valence electron on atom number of unshared electrons minus half of number of shared electrons. So this is the formula to calculate formal charge on any atom. Let us take example of CO2 1, 2 and 3, or you can write A, B and C. So formal charge on A atom. Formal charge on atom A. Oxygen atom. How many valence electrons are there? 6. Minus unshared 2 minus half of shared. So how many shared electrons are? 6. Total shared electrons 6. 3 its own and 3 of carbon. Total 6. That means it is equal to 6 minus 2 minus 3. That is equal to plus 1. So formal charge on this carbon is plus 1. What about carbon? Formal charge on atom B. So valence electrons of carbon are 4 minus unshared 0 minus half of shared. So 1, 2, 3, 4. 4 bonds mean total 8 electrons. So 4 minus 4 means 0. So formal charge on this is 0. What about this? Formal charge on atom C. Yes, tell me. So 6 valence electrons. Total shared electrons, sorry, unshared electrons 6 minus half of 2. So it is minus 1. So formal charge on C is minus 1. Plus 1, 0 and minus 1. Okay? Formal charge on each atom in ozone. Formal charge on each oxygen atom in ozone. Okay, so say in ozone its structure is O double bond single bond. How do we know that ozone is like this? You know, in ozone valence electrons are 3 into 6 18. Total electrons required to complete their octet 24. So shared electrons 24 minus 18 means 6. So shared pairs 6 by 2 means 3. So 3 shared pairs between 3 oxygens. So 2 1 or 1 2. And unshared electrons, valence electrons minus shared electrons. So valence electrons are 18, shared electrons are 6. So 12. So unshared pairs equal to 12 by 2 means 6. So 3 shared pairs that we have arranged and 6 unshared. So say in this case, you know, total 2 plus 2, 4 electrons are used. It has 4 electrons. So 4 more are required to complete its octet. This oxygen 2, 4, 6. 6 electrons it has. So 2 more are required. 2 it has, so 6 more are required to complete its octet. So in this way, 1, 2, 3, 4, 5, 6. So 6 unshared pairs. That's it. So take it as A, B and C. So what is formal charge on oxygen A? Formal charge on oxygen B. Formal charge on oxygen C. 6 electrons minus 2 plus 2 shared, unshared 4 minus shared 4. So 6 minus 6 means 0. So on oxygen A there is 0 formal charge. Oxygen B, 6 minus 1, 2, 3. 6 minus half of 2, that is minus 1. 6 minus 6, sorry. Yes, 6 minus 2 minus half of, sorry beta, for B, 6 minus 2 unshared and 1, 2, 3, 6 shared. So it is plus 1 actually. Plus 1 on B. Okay. For C, 6 minus 6 minus half of 2. So minus 1. So for C it is minus 1. For B it is plus 1. For A it is 0. So formal charge is equal to charge assigned to the individual atoms in a molecule or ion. It is the charge assigned on each atom in the molecule or ion. Okay. Now, octet rule that we have already done, octet rule and its limitations. This is also very important question. What is octet rule and what are its limitations? So octet rule is, what is octet rule? That atoms can combine either by sharing of electrons or by transference of electrons in order to complete their octets, in order to acquire noble gas configuration. Okay, so that is called octet rule that we have already discussed. What is that? Atoms can combine either by sharing of electrons or by transference of electrons in order to complete their octets, in order to have 8 electrons in their valence shell, or in order to have electronic configuration, have noble gas configuration. So that is called octet rule. Now what are the limitations? Actually, according to octet rule, those atoms which has complete, those molecules in which each atom has complete octet of electron are more stable. It is supposed to be. Okay. But there are many molecules which are stable, but they have either less than 8 electrons or more than 8 electrons, or sometimes odd number of electrons. Even then they are stable. So they are the limitations of octet rule. Okay. So first is what limitations. I am discussing about limitations. because octet rule we have already covered, okay, in previous lectures. So first limitation is electron deficient molecules. Electron deficient molecules. So those molecules which are stable, but in these molecules central atom has less than 8 electrons, they are called electron deficient molecules. Few molecules which are stable but their central atom has less than 8 electrons in their valence shell are called electron deficient molecules. For example, lithium chloride. You know, lithium has one valence electron and chlorine need one more electron to complete its octet. So lithium chloride is a stable molecule, but lithium has only 2 electrons in their valence, in its valence shell. Okay, beryllium chloride. Beryllium chloride. In beryllium chloride, beryllium has 4 electrons in its valence shell to its own, and 2 are shared with 2 chlorines. So it has only 4 electrons, but BeCl2 is stable. Then AlCl3. In AlCl3, aluminium has 3 valence electrons. It shares electron with chlorine. So aluminium okay. So in this aluminium there are 6 electrons. In lithium chloride, lithium has 2 electrons only. In beryllium chloride, beryllium has 4 electrons only. In AlCl3, aluminium has 6 electrons only, but they are stable. Octet is not complete, but even then they are stable. Okay, so this is limitation of octet rule. Beta, we are talking about valence shell 1s2, 2s1. So in the valence shell it has only 1 electron. So it is shared, say, less than 8 electrons in their valence shell. We are not talking about core electrons. So this is the first limitation, that there are electron deficient molecules. They are stable. Okay. Though they have tendency to gain electrons, okay, but they exist as lithium chloride, beryllium chloride, aluminium chloride. BeCl2 beta, beryllium has 2 valence electrons. So 2 electrons are shared with 1 with each chlorine. That's it. Okay, I got your point. You have 2s2, okay? 2p is vacant. This is ground state, okay? So beryllium in excited state, one of the electrons shift from 2s to 2p. So these two electrons form bond with chlorine. It is like this. Okay. Ralam, got it? Actually, it is next topic, but I think you have in mind that it has a pair of electron. And how can it be formed a bond? I think so. You have this thing in mind. So what happened? One of the electron from 2s is shifted to 2p. So it has two unpaired electrons. Okay? Okay, done. Same is the case with aluminium. Okay. Now, second point. Second is odd electron molecules. Odd electron molecules. Molecules having no doubt less than 8 electrons, but in odd numbers. Okay? For example, nitric oxide, NO. So this molecule NO, it can be written like this or this. So this is an odd electron molecule. Okay, nitrogen has 2, 4, 6, 7 valence electrons. See, 2, 4, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 7. So means it cannot be like that. So it is like a 3 electron bond, but it is like 2 electron belongs to oxygen and 1 electron belongs to nitrogen. It is half electron bond actually. 3 electron bond has half bond order. Bond order means how many bonds? So it has 2.5. 1, 2 and 2 and 0.5. 2.5 bond order. Okay. But anyhow, that is not our case. We are talking about that this is odd electron molecule, but it exists. NO does exist in the atmosphere. Okay. Then NO2. NO2 and double bond O, single bond NO2 is like this. Here again, nitrogen has odd number of electrons. So NO2, this molecule does exist. Okay, and they have no complete octet of electrons. Here nitrogen 2, 4, 6, 7. There are 7 electrons around nitrogen. In nitric oxide as well as NO2, nitrogen dioxide. Okay, so odd electron molecule also exist, which is the limitation of octet rule. Means octet rule is not followed by these molecules. Okay. Then third one, expanded octet. Molecules with expanded octet. Means they have more than 8 electrons. Okay, for example, PCl5, SF6, IF7. There are so many more, but we are talking about that these type of atoms. For example, in PCl5, you know, phosphorus has 5 valence electrons. So they form 5 bonds. Why structure is like this, that I will explain in the next lecture. PCl5, so around phosphorus there are 10 electrons, right? SF6, sulfur is surrounded by 6 fluorines, so there are 12 electrons. Around sulfur. IF7, so there are 14 electrons around iodine. 7 its own and 7 are shared with 7 fluorines. Sulfur has 6 electrons, valence electrons, 6 are shared with fluorines, so total 12 electrons. So they have more than 8 electrons in their valence shell, but they are stable and they do exist. Okay, so this is the third category of molecules which do not follow the octet rule. Then fourth limitation is shape of molecules. Like in PCl5, SF6, IF7, I have drawn some particular shapes. So these shapes were not explained by octet rule. Shapes and arrangement of electron pairs were not explained by octet rule, and even their energies as well. What is the energy of the molecules? What is the shape of the molecules? What is the arrangement of electron pairs? That is not explained by octet rule. Fifth one. Compounds of noble gases. This is the big jerk to the octet rule. Why is it so? Because octet rule is based on the stability of noble gases. That atoms can combine by sharing of electrons, by transfer of electrons to have noble gas configuration. So now noble gases also form bond. So means octet rule is nowhere then. But even then, in spite of all these limitations, octet rule is followed by most of the molecules. In the covalent molecules, in most of the covalent molecules, octet rule is followed. And we can explain their structure, we can explain the bonding, covalent bonding by using octet rule. Okay. So compounds of noble gases as xenon can form xenon as well as krypton, but let us take xenon. For example, as xenon can form compounds with fluorine and oxygen. So that is the biggest jerk to the or I think biggest limitation to the octet rule. For example, XC F2, XC F4, XC F6, XC O3, XC O4, XC O2 F2, XC O F4, and many more. Okay, so this is also the limitation of octet rule. And you know, hydrogen, compounds of hydrogen is always limitation to the octet rule. Compounds involving hydrogen, H in their compounds, in their compound और मॉलिक्यूल लेगी compounds involving hydrogen atom, hydrogen as H as their one of the atoms. For example, HCl, H2O, NH3. That's all. Okay. So these are all limitations of the octet rule. चलो आज यहीं तक करते हैं. आप लास्ट ये करो, राइट फॉर्मल चार्ज on each atom in carbonate ion. Okay, carbonate में it is like this. There are 4 pairs actually that we have already discussed. So now and sum of the formal charge is equal to charge on the ion. So A oxygen, B oxygen, C oxygen and D carbon. So what is formal charge on oxygen A? Valence electrons are 6. Oxygen has 6 valence electrons minus unshared electrons. 1, 2, 3, 4, 5, 6. 6 unshared minus half of shared. So shared electrons are 2. So total 6 minus 6 0 means minus 1. On this oxygen, valence electrons are 6 minus unshared 2 plus 2 4. 4 unshared minus half of shared. So shared electrons are again 4. So 6 minus 4 minus 2 0. And formal charge on oxygen C, that is same as A, because same number of electron pairs, unshared pair, same number of bond pairs, same number of valence electrons. Now formal charge on carbon D. So carbon has valence electrons 4 minus unshared 0. Very good. And shared 2, 4, 6, 8. That is 4 minus 4, that is 0. That's it. So this is all about formal charge and limitations of octet rule. Next topic is bonding parameters. First, bond enthalpy, amount of energy required to break 1 mole of particular type of bond into its gaseous atoms. For example, let us take, we have hydrogen molecule, okay? So there is a bond between the two atoms. So breaking of this bond leads to the formation of two hydrogen atoms. So to convert this hydrogen molecule into its gaseous atom, one bond is broken. We take it as 1 mole. So to break this 1 mole of bond, how much energy is required? That is called bond enthalpy. Got it? This is single bond between two hydrogen atoms. Okay. This bond, to break this bond, energy is required because we have to break. There is an attraction between two hydrogen atoms. Maximum attraction between two hydrogen atoms. Now we break this bond. So that means we have to move them apart to such a large distance that there is no attraction between two atoms. So to remove them from each other, energy is required because we have to work against attractive forces. To take them away from each other, what we do? We do work against the attractive forces. Okay? So that is in the form of energy. In case of polyatomic bond enthalpy, in case of polyatomic molecules. See, in case of diatomic molecule, it is very simple case. But if we have polyatomic molecules, let us take example of H2O. In H2O, there are two OH bonds. So to break first OH, breaking of one OH bond. Okay, so let us take energy required is X1, and to break second, energy required is X2. Okay. Now, and keep in mind, H2O is also in gaseous form. OH in gaseous forms. All are in gaseous form. While calculating bond enthalpy, all the molecule as well as breaking of species, when it bond breaks and species are formed, they all are in gaseous state. And when environment changes, then energy required is different. Though in both cases OH bond breaking takes place, but in this case, when OH bond breaks, then there is one more OH bond. Means it is like this, OH, OH. But in this case, environment is different, so energy required are different. But if question is, what is bond enthalpy, then we calculate average bond enthalpy for OH bond in H2O. Here we use average, that is X1 plus X2 divided by 2. So this is the averaging of, in case of polyatomic molecules, we use average bond enthalpy. Okay, and its units are either kilojoule per mole or joule per mole, right? Even calories can be used in case of food. Okay, so this is unit of bond enthalpy. Okay, let us take case of methane. In case of methane, first we get CH3 gas and H gas, then CH3 gas to give CH2 gas plus H gas, then CH2 gas to give CH gas plus H gas, and at the end CH gas into C gas plus H gas. So overall it is CH4 gas to give C gas plus 4H gas. Okay, so let us take delta H. For first one is X1, for second one it is X2, for third one it is X3, for fourth one it is X4. So what is delta H for this? It is X1 plus X2 plus X3 plus X4. But to calculate average bond enthalpy for CH in CH4, that is equal to X1 plus X2 plus X3 plus X4 divided by 4, because there is a breaking of 4 CH bonds. Okay, so divided by 4 is average bond enthalpy for CH bond in CH4. We have say single bond, say double bond. Okay, it gives 2C gas, it also gives 2C gas. Delta H for this, let us take as X, and delta H for second is Y. So what is the relation between X and Y? Tell me. Is X greater than Y, X equal to Y, or X less than Y? Or any of the above? Yes, tell me. Y is greater than X, or X is less than Y, because here we have to break single bond, but in this case we have to break double bond. That means as number of bonds increases, atoms come closer to each other, and when atoms come closer, bond length decreases and bond strength increases. Relation is, say, number of bonds means bond order. Single bond means bond order is 1. Double bond order is 2. Triple bond, bond order is 3. And Z is greater than Y, Y is greater than X. Now see, bond order is inversely proportional to bond length. Bond length means distance between the two atoms. Okay, is proportional to bond strength. So more is the number of bonds, greater is the strength of the bond. Strength means how strong the bond is. Okay, and is proportional to bond enthalpy, because stronger is the bond, more energy is required to break the bond. Okay, this is the relation. Right? Now let us discuss the factors affecting bond enthalpy, or let us discuss bond length. It is average equilibrium distance between centers of two bonded atoms. This bond is considered as a spring. This is the average distance, right? Average equilibrium distance. Now if we compress it, these are the two atoms. When we compress it, spring goes out because there is a repulsion, and if we stretch it, it comes closer. So this is called equilibrium distance. Equilibrium means when potential energy is minimum. In spring, if we stretch it, there is an increase in potential energy. If we compress it, again there is an increase in potential energy. Okay? So this is the distance between the two atoms, that is called average equilibrium distance between centers of two bonded atoms. That is called bond length. And bond length is determined by X-ray diffraction. Bond length is measured by X-ray diffraction. Bond length is measured by X-ray diffraction. So factors affecting bond length. And bond length is measured in picometer, nanometer, centimeter, angstrom. Okay? So factors affecting bond length. First is size of atoms. Yes, tell me. What is the effect of size? If size of the atom is large, then what is the relation with the bond length? See, if atoms are small, atoms are large, what happened? If atoms are small, bond length is smaller. If atoms are large, bond length is large. So bond length is directly linked to the size of atom. Now tell me, out of chlorine and bromine, which one is larger in size? Chlorine, bromine, iodine. As we go down the group, size increases. So bromine is larger than. So for example, as bromine is larger than that of chlorine, bond length HBr greater than HCl, right? Because bromine is larger than chlorine, so HBr is, bond length of HBr is more than that of HCl. Now, second, multiplicity of the bond. Second factor. Multiplicity of bond. Tell me, what is the relation with the multiplicity of the bond? Multiplicity means multiple bonds between two atoms. Double, triple. So as number of bonds between two atoms increases, multiplicity increases. As multiplicity of the bond increases, atoms come close to each other, so bond length decreases. Okay, for example, bond length of say triple bond C is less than double bond, which is less than single bond. So for triple bond it is 120 picometer, for double bond it is 134 picometer, and for single bond it is 154 picometer. Okay, multiplicity of the bond is bond order. Simple. Bond order increases, bond length decreases. Okay, now third point. Type of hybridization. So tell me, SPDF, out of SPDF, which one is closest to the nucleus? Keep in mind, bond length is also associated with type of hybridization. Hybridization means mixing of orbitals. Okay, so as S character increases, bond length decreases, because S orbital is smaller than that of P orbital, or we can say S orbital is closest to the nucleus. Okay, can we write? Yes, we can write here. So say if there is CH bond with sp3 hybridization, means 1s and 3p, or CH bond where carbon is sp2 hybridized and third is CH bond sp hybridized. So tell me, in sp3 what is the percentage of S character? Say, how do we calculate? Percentage of S character is equal to number of S orbital over total into 100. See, total orbitals are 1s and 3p. Total are 4. And out of 4, 1 is S. So 1 upon 4 into 100. So it is 25%. sp2. What is the percentage of S character? sp2, 1s and total 3. So it is 33.3%, or we can say 33.33%. Good, Sakshi, Namita, Ralam, Abhay. What about the others? Now understood? How do we calculate? Even if you don't know earlier, it is simple. SP means 1S, 1P. Total 2. Out of 2, 1 is S. So 50%. SP3 is largest because percentage of S character is minimum. More is the S character, smaller is the bond length. This is largest bond length. Can I write here? So bond length of CH is greater than for sp2 and then sp. This is 111 picometer, this is 110 picometer, and it is 108 picometer. There are three factors. First, size of the atom, larger size, large bond length, smaller size, small bond length. Multiplicity of the bond, more is the number of bonds between two atoms. They are closest to each other, so bond length is smallest. Okay, and third is hybridization. More is the S character, smaller is the bond length. Bond angle. It is the angle between the bond pairs. Angle between bond pairs. Angle between bond pairs. For example, in CO2, you know, there are two bond pairs. It lies like this. So angle between the two bonds is 180 degree. So angle between bond pairs is called bond angle. In BF3, boron, it is like this. So angle is 120 degree. Methane, it is non-planar and angle is 109 degree 28 minute. 109 degree 28 minute. And NH3, see, actually angle is between the bonds. Here they are repelled, so the bonds are closer to each other. So angle is 107 degree. In water, they are further closest, and angle is 104.5 degree. Means as lone pair increases, say total electron pairs 4. Total electron pairs 4. Total electron pairs 4. But because electron pair repel each other because of like charge. In electron pairs, electrons are negatively charged. So negative charges means like charges repel each other. But lone pairs repel more than bond pairs. So this is the relation. Lone pair repulsion is greater than lone pair bond pair repulsion, which in turn greater than bond pair repulsion. Right? Because lone pairs occupy large surface area. Coordinate bond or dative bond. Coordinate bond or dative bond. I have given some idea about that. Actually, coordinate bond, once it is formed, it is just like covalent bond. There is sharing of electrons. Like in covalent bond, what would happen? Like hydrogen has one electron, each hydrogen has one electron. So they will share these two electrons. Okay, one electron each will contribute, and therefore there is a formation of covalent bond where 50% share is of first hydrogen and 50% share is of the other hydrogen. Like covalent bond, I am talking about covalent bond. In nitrogen, like nitrogen has 5 valence electrons, so each nitrogen contribute 3 electrons. Each nitrogen contribute 3 electrons to share with each other, and therefore there is a formation of 3 covalent bonds between 2 nitrogen atoms. So in covalent bonds, 50% share is of each atom, 50-50. Both will contribute equally. When sharing takes place, for the sharing, both contribute equally. But in coordinate bond, see the case of coordinate bond. In coordinate bond, like we have ammonia. This is ammonia. Ammonia has 3 covalent bonds and 1 unshared electron pair, because nitrogen has total 5 electrons. Out of 5, 3 are shared with hydrogens and 1 electron pair left unshared, that is called lone pair. Now when it comes in contact with VF3, in VF3, see, in VF3, boron has 3 valence electrons. All the 3 are shared with each fluorine, 3 fluorines. Now, how many electrons it has? 6 in its valence shell. Ammonia, 8, complete. But if ammonia share its electron pair with boron, then both have octet of electrons like this. But in this sharing, total share is provided by ammonia. Total share is provided by ammonia, and it is denoted like this arrow, and this arrow is from the one which donate the pair and towards the atom which accept the pair. So here nitrogen is donor and boron is acceptor. So that is why it is also called dative bond. There is donation of the pair for sharing, and that shared pair comes from the same atom. In covalent bond, there is 50-50% share, but here 100% share is from the single atom, okay, and that will share with other atom which is deficient of electron. So such a molecule having unshared pair and complete octet, that is called electron Electron-rich molecule, and one which has less than 8 electrons, that is called electron deficient molecule, and such a bond is called dative bond or coordinate bond. Now see, in H3O plus, water is like this, okay, and H plus has no electron. So when H plus is attached to it, it is like this. NH4 plus. In NH4 plus, again same case, ammonia has a lone pair, H plus has no electron. So this is called ammonium ion, this is called hydronium ion. Hydronium ion, and this is ammonium ion. So there is a formation of this type of bond. So this arrow indicates that there is a bond formation between H and N, and shared pair comes from nitrogen only. Okay, second thing, say if we don't want to represent it by this coordinate bond, then we just write simple this bond, and this gets positive and boron gets negative. So this is also one of the representation of coordinate bond. Either you make an arrow or positive and negative. Positive to the donor and negative to the acceptor. Okay, so in this case, if we remove it by this type of bond, then H is, because H gets negative, already it has positive, so it is neutral and this gets positive. Right? Here, if we remove it by this, it gets neutral, means negative, already positive, so it is neutral, and this gets positive. Like that. Or simply you can write it as NHHH whole positive. Today's topic is resonance. So what is resonance actually? Actually, some molecules we cannot explain all its properties by using Lewis structure, because all the covalent molecules, their structure is explained by drawing their Lewis structures. For example, take an example like ozone. In ozone, there are 3 bond pairs and rest are lone pairs. So, ozone, it is represented like this. Or it can be represented like this. Right? Okay, ozone has only 3 bond pairs. So 3 bond pairs can be arranged as 2-1 or 1-2. 2-1 or 1-2. These are the 2 possibilities for ozone. Okay, and keep in mind the bonds between two atoms is called bond order. What is bond order? Number of bonds between two atoms, that is called bond order. And more the number of bonds, lesser is length, lesser is bond length. That means bond order is inversely proportional to bond length. So that means if we say these are Lewis structures of ozone, right? These are Lewis structures of ozone, and bond order is inversely proportional to bond length. More the number of bonds, lesser is the bond length. So let us take this as A bond length and this bond length as B. So it is a double bond, it is a single bond. So what is the relation between A and B? Either A is less than B, or A is greater than B, or A is equal to B according to this structure. So ये double bond है and this one is single bond. So more is the number of bonds, more is the bond order, and lesser is bond length. जैसे मैंने आपको एक और एग्जांपल दिया था कि कार्बन कार्बन सिंगल बॉन्ड, कार्बन कार्बन डबल बॉन्ड, कार्बन कार्बन ट्रिपल बॉन्ड. तो इसकी बॉन्ड लेंथ होती है 120 पिकोमीटर, इसकी राउंड अबाउट 130 पिकोमीटर, 134 या 133, और इसकी होती है सॉरी उल्टा हो गया, सिंगल बॉन्ड में 154 पिकोमीटर और ट्रिपल बॉन्ड की 120 पिकोमीटर. तो ये बॉन्ड का लेंथ का ऑर्डर है. सिंगल बॉन्ड मींस बॉन्ड ऑर्डर 1, बॉन्ड ऑर्डर 2, बॉन्ड ऑर्डर 3. तो बॉन्ड लेंथ का देखेंगे तो लेंथ सिंगल बॉन्ड की सबसे बड़ी होगी, डबल बॉन्ड की थोड़ी छोटी हो जाएगी, ट्रिपल बॉन्ड की और स्मॉल हो जाएगी. दैट मीन्स A is less than B. So now that means bond length A should be less than bond length B. But in real, both A is equal to B. So that means if bond lengths are equal, experimentally it is proved. What I said, experimentally, when we calculate bond length, the bond length is 1 only, that is same bond length of these bonds. That means neither this structure 1 nor 2 is the actual structure of ozone. They are not the actual structure of ozone. That means ozone is not represented by any one of them, or we can say Lewis structures cannot explain all the properties of the molecule, or in other words we can say ozone cannot be represented by a Lewis structure, because if bond order is 3, so there should be either 2-1 or 1-2. There is no concept of fractional order in Lewis structure. So keep in mind that ozone has same bond order, and it is like this. means both the bonds are more than single bond, less than double bond. They are more than single bond and less than double bond. Means they have fractional bond order. And to calculate bond order is equal to bonds between two atoms, 2 plus 1 divided by positions. That means its bond order is 1.5. It is neither 2 nor 1. It is 1.5. That's why. But this type of structure cannot be represented by Lewis structure. This is not a Lewis structure. And that is called resonance hybrid. This is the actual structure. Okay? And these are called resonating structures or canonical structures. Resonating structure or canonical structures. That means resonating structures or canonical structures are the one which are drawn for the molecule to explain its properties, but it cannot explain all the properties. ये जो structures हैं ओजोन के, ये actual नहीं है, ये हमने draw किए हैं to explain few of its properties, क्योंकि most of the properties matches. There are 3 atoms, there are total 3 bonds, 2, 1 or 1.5 plus 1.5. Okay, total 3 bonds are there, but ये actual structure नहीं है, क्योंकि experimentally it has been proved that OO bond जो हैं दोनों, उनका जो bond length है वो same है, but इन दोनों में से कोई भी ऐसा structure नहीं है जो explain कर दे कि bond order same क्यों है, क्योंकि ये तो बोल रहा है कि एक सिंगल होगा एक डबल होगा, और सिंगल और डबल होगा तो बॉन्ड लेंथ शुड बी डिफरेंट, बट एक्सपेरिमेंटली बॉन्ड लेंथ इज सेम. इसलिए ऐसे स्ट्रक्चर्स को एक्सप्लेन करने के लिए जो नेक्स्ट कंसेप्ट आता है दैट इज कॉल्ड रेजोनेंस. डबल एंड सिंगल बॉन्ड दे आर नॉट द एक्चुअल स्ट्रक्चर्स ऑफ ओजोन. Actual structure is this one. That means resonance hybrid is the actual structure and resonating structure or canonical structures are imaginary structures. They are imaginary structure of ozone. It is a phenomenon as a result of which a molecule can be expressed in different forms, none of which can explain all the properties of the molecules, the actual structure of the molecule, is called resonance hybrid. And the Lewis structures the molecule to explain few of its properties are called resonating structures or canonical structures. Called resonating structures or canonical structures. Okay. Say for example, that means it is the phenomenon as a result of which a molecule can be expressed in different Lewis forms. In different, we can write Lewis forms. Okay. None of which can explain all the properties of the molecule. For example, let us take example of benzene. Benzene is generally drawn like this: 3 double bonds, 3 single bonds, and position may be like these two. Okay, none of which can explain all the properties of the molecule. Okay, and the actual structure, these are the resonating structures of benzene. None of them is actual. Now look at these structures. In these two structures, there is a carbon-carbon double bonds, 3 carbon-carbon double bonds, 3 carbon-carbon single bonds. Am I right? So there are 2 types of bond lengths. Say carbon-carbon single bond length is 154 picometer, and carbon-carbon double bond length is 133 or 134 picometer. Okay, that means these molecules should have 2 types of carbon-carbon bond lengths, but in actual it is like this: a resonance hybrid. So all the experimentally it is proved that all the carbon-carbon bond lengths are equal, and that is equal to 139 picometer. So that means none of these structures of benzene can explain all the properties of benzene. Means they are not actual structure of benzene. Actual structure of benzene is this one, and that is called resonance hybrid. Resonance hybrid is always more stable than any of the resonating structures. So if we talk in terms of energy of resonance hybrid is least because it is most stable, and canonical structures, different canonical structures, obviously this is most stable resonating structure. The one which has least energy among resonating structures, that is most stable. So the difference between these two is called resonance energy. So resonance energy is equal to difference in energy between most stable resonating structure and resonance hybrid. Difference in energy between most stable resonating structure and resonance hybrid, that is called resonance energy. That means lower the energy of resonance hybrid, more is the resonance energy. So higher is resonance energy, more stable is resonance hybrid. For example, resonance energy of benzene is 150 kilojoule per mole. How to draw resonating structure, or what is the condition for a resonating structure? Favorable conditions to draw resonating structures. So to say these favorable conditions, first we draw resonating structure of carbonate. In carbonate, how many bond pairs are there? In carbonate, how many bond pairs are there? Bond pair, shared pair in carbonate. In carbonate, how many bond pairs are there? I have done it before, but number of valence electrons they have calculated to draw Lewis structure. Carbon has 4, each oxygen has 6 plus 2 for 2 negative charges, okay? So 24, and number of electrons required to complete their octet, 4 into 8 means 32. That means number of shared electrons is 32 minus 24, that is 8. So number of shared pair equal to 8 by 2. I have explained it earlier. 4. Okay, that means shared pair are 4. Say now, you know, there are 3 oxygens. Oxygens are 3, but shared pairs are 4. So as shared pairs are 4, so 3 we can arrange like this. So 1 that may be at this position or this position, any one of them. So if we draw double bond here, so there are other 2 single bonds. So 1, 2, 3, 4, 5, 6, 7 and 8. 8 lone pair should come. Unshared pairs are 8. Okay, so this is a resonating structure of carbonate. We can draw like this. If double bond is here, can be. Or so now listen, double bond may be at this position or next position or even next to it. Means these 3 are called resonating structures of carbonate. So in resonating structures, say position of atoms remains same. There is no change in position of the atoms, but there is different distribution of bond pairs and lone pairs. Distribution of bond pair and lone pair is different. Like say, if we say here, there is a double bond. If this oxygen has 2 bond pairs, 2 lone pairs, but same in other structure, this has 3 lone pairs and 1 bond pair. Okay, and see this one remains same, but these two interchange. In this case, these two interchange. Got it? That means, in what are the favorable conditions to draw resonating structures? First condition, position of the atoms remains same. Means different contributing structures or resonating structures. Different contributing structures should have same position of atoms. That you can see. In all of them, position of the atoms is same. There is no change in the position of atoms. But there is a change in the position of bond pairs and lone pairs. Okay? But number remains same. Bond pairs 4, 4, 4. Lone pairs 8, 8, 8. In all the resonance structures, bond pairs are 4 and lone pairs are 8. It's true for all the structures, but distribution is different. The contributing structures should have same number of shared pairs and unshared pairs. They differ only in their positions. Their positions are different. Okay. Now, third point is contributing structures should have nearly same energy. Should have nearly same energy. Their energy should be almost equal to each other. There is a slight difference in their energies. Because as bond pair and lone pair are same, position of the atoms are same, so they have almost similar energy. Okay. Then in all the contributing structures, like charges should not reside on neighboring atoms. Means adjacent there should not be positive charge or negative charge. It may be positive and negative, but two like charges, two positive charges or two negative charges should not reside on the adjacent atoms, on the neighboring atoms. So these are the conditions. So first we have drawn structure of carbonate, benzene, ozone. Carbonate is very important. Structure of carbonate, that is very important. Let us draw structure for nitric acid. Nitric acid or nitrate ion. Okay, nitric acid, HNO3. So keep in mind, in HNO3, nitrogen it is like this, because nitrogen can form maximum 4 bonds. Lone pair, it is like this, or it may be like these are the resonating structures of nitric acid, HN3. So in HN3 is HN double bond N or HN or HN triple bond N single bond N. Now basic question is, you can ask, okay, why you write double single triple single? Say, so how could we calculate? See, if we have N, leave H, remove H, it is N3 negative. Okay, in N3 negative, number of valence electrons 3 into 5, 15 plus 1 is total 16. Now to complete their octet, 3 into 8, 24. So number of shared electrons, you can calculate 24 minus 16, 8. So number of shared pairs equal to 4. Okay, so shared pair of 4 between 3 nitrogen atoms, it can be double 2 or 1 3 or 3 1. So in this case, say total 4, so 2 pairs, total 4 plus 4, 8, done, 2. Here 3 lone pairs, 1 bond pair, 1 lone pair, 1 lone pair, 3 lone pairs. So you can say in N3 negative, this is called azide ion. There are 4 bond pairs, 4 lone pairs in azide ion. Okay. Here same. Here I attach H plus. So it is like it has 1 lone pair, it has 2 lone pair. Here it has 2 lone pairs, 1 lone pair. No lone pair. again no lone pair and 3 lone pairs. Now another method to calculate formal charge. I think we are running short of time. Okay, see, in this case nitrogen has how many valence electrons? 5. So 1 is shared 6, 7, 8. 5 valence electron it has and 3 are shared. So that means its formal charge is 0. Its formal charge is 0 because 5 it has and 3 are shared. So total 8. That means it's okay. Nothing to and no electron to gain or lose to complete its octet. This nitrogen, it has 5, 4 are shared. It has 5 valence electrons and 4 are shared. So it should have 9 electrons. That is not possible. That means it loses 1 electron. So it has plus 1 formal charge. What about this? 5 electrons, 2 are shared. So 5 plus 2, 7. That means one more electron is needed to complete its octet. Means minus 1. So this is the method to calculate formal charge. What about this? Tell me. What is the formal charge on this nitrogen? This nitrogen. Fast. Do it fast. Can you calculate for this? This nitrogen has how many valence electrons? 5. Any nitrogen has 5 valence electrons, okay? Out of 5, how many are shared? 2. So 5 plus 2, 7. But it has 8. So minus 1. This nitrogen, 5 valence electrons, 4 are shared. So 9. 4 are shared. So 9. That means it loses 1 electron. So plus 1. 5 plus 3, 8. Are you getting this? 5 plus 4. 3 on one side, 1 on other side. 5 plus 4. 9. That means it has plus 1. 5 plus 4. Very good. B plus 1. Very good, Namita. Plus 1. Again plus 1. Tell me what is the charge, what is the formal charge on this nitrogen? 5 it has, 1 is shared. So 6 and 2 electrons are required, minus 2. So tell me, out of these 3 structures, which one is most unstable? Out of these 3 structures, which one is least favorable? Out of these 3 structures, which structure is least probable? Third one, because in this case like charges reside on the neighboring atoms. Like charges reside on the neighboring atoms, and because they repel each other, like charges repel each other, so this is the least stable resonating structure or least favorable resonating structure for hydrozoic acid. That's all for the day.
गुड मॉर्निंग फ्रेंड्स। तो आज का हमारा टॉपिक है डाइपोल मूवमेंट, और ये जो टॉपिक है इट इज मोस्ट इंपॉर्टेंट एज फार एज द कंसेप्ट इज कंसर्न्ड, और इसके बेस पे बहुत सारे क्वेश्चन पूछे गए हैं कॉम्पिटिटिव एग्जाम्स में, इवन आपके बोर्ड एग्जाम्स में, यूनिवर्सिटी एग्जाम्स में इस पे क्वेश्चन पूछे जाते हैं। नाउ डाइपोल मूवमेंट के पहले हम बात करते हैं पोलर एंड नॉन पोलर कोवलेंट बॉन्ड्स की। बॉन्ड बिटवीन टू सिमिलर एटम, चाहे सिंगल बॉन्ड हो, डबल बॉन्ड हो या ट्रिपल बॉन्ड हो, अगर सिमिलर एटम्स के बीच में बॉन्ड है तो शेयर्ड पेयर जो है कहां रहेगा? मिड में, इक्वल डिस्टेंस फ्रॉम ईच एटम, सो दैट इज कॉल्ड नॉन पोलर कोवलेंट बॉन्ड। और ऐसे मॉलिक्यूल का डाइपोल मूवमेंट जो है दैट इज इक्वल टू 0। बट अगर दो एटम्स के बीच में जो बॉन्ड है वो दो डिसिमिलर एटम्स के बीच में है और उनकी इलेक्ट्रोनेगेटिविटी डिफरेंट है, याद रखना, देयर इज अ डिफरेंस इन इलेक्ट्रोनेगेटिविटी। तो डिफरेंस इन इलेक्ट्रोनेगेटिविटी इज द की फॉर द पोलैरिटी ऑफ अ बॉन्ड। तो अगर इलेक्ट्रोनेगेटिविटी डिफरेंट है, मान लिया ये वाला मॉलिक्यूल ये वाला एटम मोर इलेक्ट्रोनेगेटिव है बी और ए वाला लेस इलेक्ट्रोनेगेटिव है, आपको पता है मोर इलेक्ट्रोनेगेटिव शेयर्ड पेयर को अपनी तरफ खींचेगा, क्योंकि इलेक्ट्रोनेगेटिविटी का डेफिनेशन ये है, टेंडेंसी ऑफ एन एटम टू अट्रैक्ट द शेयर्ड पेयर, दैट इज कॉल्ड इलेक्ट्रोनेगेटिविटी। तो शेयर्ड पेयर इज क्लोजर टू बी, तो उसके ऊपर क्या जाएगा? पार्शियल नेगेटिव चार्ज, और दूसरे पे आ जाएगा पार्शियल पॉजिटिव। जितना बी पे पार्शियल नेगेटिव होगा उतना ही ए पे पार्शियल पॉजिटिव चार्ज होगा। तो दैट इज कॉल्ड पोलर कोवलेंट बॉन्ड। और ऐसे मॉलिक्यूल का डाइपोल मूवमेंट नॉन जीरो होता है। अब अगर एग्जैक्ट वैल्यू फाइंड आउट करनी है तो डाइपोल मूवमेंट इज इक्वल टू प्रोडक्ट ऑफ चार्ज, जो पार्शियल चार्ज है, पार्शियल पॉजिटिव और पार्शियल नेगेटिव, प्रोडक्ट ऑफ द चार्ज, मैग्नीट्यूड ऑफ द चार्ज, दिस इज मैग्नीट्यूड ऑफ द चार्ज ऑन द कोवलेंटली बॉन्डेड एटम्स into the distance of separation, that is actually bond length between two atoms, और bond की length that is called distance of separation। तो ये डाइपोल मोमेंट का फॉर्मूला है। और डाइपोल मोमेंट जो है इट इज अ वेक्टर क्वांटिटी, और वेक्टर क्वांटिटी की जो डायरेक्शन होती है दैट इज फ्रॉम लेस इलेक्ट्रोनेगेटिव टू मोर इलेक्ट्रोनेगेटिव। और ये एरो क्या शो कर रहा है? टेल इज नियर टू लेस इलेक्ट्रोनेगेटिव एटम एंड हेड टुवर्ड्स मोर इलेक्ट्रोनेगेटिव एटम। और ये जो एरो का डायरेक्शन है इट इंडिकेट्स डायरेक्शन ऑफ द ट्रांसफर ऑफ इलेक्ट्रॉन, क्योंकि इलेक्ट्रॉन इज मोर टुवर्ड्स बी, इलेक्ट्रॉन मूव्स अवे फ्रॉम ए एंड क्लोजर टू बी। तो ये डाइपोल मूवमेंट की डायरेक्शन है। तो अगर एक ही बॉन्ड है, मतलब हेट्रो न्यूक्लियर डायटोमिक मॉलिक्यूल है, तो वो हमेशा ही पोलर होगा। वो मॉलिक्यूल का है हमेशा पोलर, क्योंकि उसका डाइपोल मोमेंट हमेशा क्या होगा? नॉट इक्वल टू 0। और यूनिट ऑफ डाइपोल मोमेंट इज dB, एंड 1d, dB को कैपिटल D से डिनोट करते हैं, और 1d इज इक्वल टू 3.33564 इंटू 10⁻⁻30 कूलम मीटर। C for coulomb, that is charge, SI unit of charge, and distance meter, so coulomb meter। और in terms of CGS unit it is 1 into 10⁻18 ESU centimeter। 1 इंटू 10⁻⁻18 ESU सेंटीमीटर। तो अभी हमने किया कि अगर होमोडायटोमिक हो, दिस इज कॉल्ड होमोडायटोमिक। होमोडायटोमिक मीन्स जैसे अपने पास आ गया H2, O2, N2, F2, ये सारे क्या हैं जिनमें सेम टाइप के दोनों एटम्स हैं, होमोडायटोमिक मॉलिक्यूल्स, उनका डाइपोल मोमेंट हमेशा ही 0 होता है, क्योंकि चार्ज का सेपरेशन होगा ही नहीं। तो ये ऐसे मॉलिक्यूल जो हैं वो हमेशा ही नॉन पोलर होते हैं, क्योंकि एक ही बॉन्ड है, तो नॉन पोलर कोवलेंट बॉन्ड है, और ये नॉन पोलर मॉलिक्यूल्स होते हैं। अगर हेट्रो न्यूक्लियर डायटोमिक मॉलिक्यूल्स हैं तो वो हमेशा ही पोलर होते हैं, उनका बॉन्ड भी पोलर होता है, उनका वो मॉलिक्यूल भी पोलर होता है, और उनका डाइपोल मोमेंट हमेशा ही नॉट इक्वल टू 0 होता है। इट इज नॉट इक्वल टू 0। अब अगर हम बात करें कि पॉलीन्यूक्लियर मॉलिक्यूल्स हों जिसमें 2 से ज्यादा एटम्स हों, ठीक है, तो उस केस में हमें क्या करना पड़ता है, क्योंकि अभी बताया हमने कि डाइपोल मोमेंट इज अ वेक्टर क्वांटिटी, तो हमें लॉ ऑफ वेक्टर एडिशन लगाना पड़ता है। अगर वेक्टर एडिशन करके मॉलिक्यूल में बॉन्ड्स चाहे पोलर हों बट उनका नेट डाइपोल मोमेंट 0 हो जाए तो वो मॉलिक्यूल नॉन पोलर होता है। लेट अस टेक एन एग्जांपल। तो पहला मैं एग्जांपल ले रहा हूं CO2। अब CO2 मॉलिक्यूल जो होता है उसमें 2 CO बॉन्ड्स हैं। अब और ये लीनियर स्ट्रक्चर है। अब आपको पता है कि CO बॉन्ड जो है वो पोलर होगा। CO के में C और O में O इज मोर इलेक्ट्रोनेगेटिव देन कार्बन, तो डायरेक्शन कहां होगी? O की तरफ। इधर भी डायरेक्शन इज टुवर्ड्स O। देखो जितना ये इस साइड जाएगा उतना ही दूसरी साइड, तो नेट जो वैल्यू है ये बॉन्ड मूवमेंट्स है। बॉन्ड मूवमेंट ऑफ वन CO is equal and opposite to other CO, therefore net dipole moment is 0। तो ऐसा मॉलिक्यूल जो क्या होगा? नॉन पोलर। ये मॉलिक्यूल क्या है? नॉन पोलर। 2 बॉन्ड्स आर पोलर बट मॉलिक्यूल एज अ होल इज नॉन पोलर। और एग्जांपल लेते हैं BF3। BF3 में ऐसा स्ट्रक्चर है। अब B और F में विच वन इज मोर इलेक्ट्रोनेगेटिव? सबको पता है फ्लोरीन इज मोर इलेक्ट्रोनेगेटिव देन ब्रोमीन, सो पोलैरिटी इज टुवर्ड्स फ्लोरीन। डायरेक्शन कहां होगी? फ्लोरीन की तरफ। और इनके बीच में एंगल कितना होता है? 120 डिग्री। तो याद रखना कि इस BF का डाइपोल मोमेंट इन दोनों के नेट डाइपोल मोमेंट के बराबर आएगा। तो हम क्या करेंगे? पैरेललोग्राम लॉ ऑफ वेक्टर एडिशन लगाएंगे। देखो ये दोनों नीचे हैं तो इन दोनों का डाइपोल मोमेंट क्या आएगा? नीचे। तो हम लेट अस टेक कि डाइपोल मोमेंट इनका है x x x। तो ये तो x है, ये दोनों का नेट फाइंड आउट करते हैं। इसको मान लेते हैं म्यू r। सो म्यू r अकॉर्डिंग टू कौन सा लॉ लगेगा? पैरेललोग्राम लॉ ऑफ वेक्टर एडिशन। जो नेट डाइपोल मोमेंट आएगा दैट इज, अगर इसको a ले लें और उसको b, तो a² प्लस b² प्लस 2ab cos थीटा। तो a भी x है तो ये x² प्लस x² प्लस 2x इंटू x 2x² और cos 120 डिग्री। कितना हो गया? 2x² प्लस 2x²। अब cos 120 डिग्री जो है दैट इज इक्वल टू cos 90 प्लस 30। और कौन सा क्वाड्रेंट हुआ? सेकंड। सेकंड क्वाड्रेंट में cos क्या होता है? नेगेटिव, क्योंकि ये होता है ना ऑल स्कूल टू कॉलेज। इसमें ऑल पॉजिटिव होते हैं, इसमें साइन पॉजिटिव होता है, इसमें tan पॉजिटिव होता है, इसमें cos पॉजिटिव होता है। तो इसका मतलब सेकंड क्वाड्रेंट में साइन पॉजिटिव होता है, तो ये तो क्या होगा? नेगेटिव। और 90 प्लस है तो cos का क्या हो जाएगा? साइन। तो साइन 30। साइन 30 डिग्री कितना होता है? 1/2। तो इट इज -1/2। तो जस्ट पुट द वैल्यू। -1/2, so it comes out to be 2x² minus x², that is x², that is equal to x। तो ये भी x, नेट रिजल्टेंट x, ये भी x, इक्वल एंड अपोजिट। सो नेट डाइपोल मोमेंट ऑफ BF3 is equal to 0। so BF3 is also नॉन पोलर मॉलिक्यूल। तो ये तो मैंने आपको एक हिंट दिया। अब ऐसा तो हो नहीं सकता कि हर एक का हम फाइंड आउट करें ऐसे। तो सिंपल सा फंडा है कि जो भी मॉलिक्यूल जिसमें बॉन्ड्स पोलर हों बट सारे बॉन्ड पेयर्स हों और दे आर अरेंज्ड सिमेट्रिकली, तो वो सिमेट्रिकल ज्योमेट्री होगी, रेगुलर ज्योमेट्री होगी और उसका डाइपोल मोमेंट 0 आएगा और ऐसा मॉलिक्यूल नॉन पोलर होगा। या फिर बॉन्ड पेयर भी हो, लोन पेयर भी हो, बट बॉन्ड पेयर की अरेंजमेंट सिमेट्रिकल हो तो उसका भी डाइपोल मोमेंट 0 होगा और वो भी नॉन पोलर होगा। तो और एग्जांपल करते हैं, जैसे BF3 किया है हमने, BeCl2, ओनली बॉन्ड पेयर्स, दोनों एक जैसे, ओनली बॉन्ड पेयर्स एंड और बॉन्ड पेयर्स आर ऑफ सेम टाइप। जैसे BeCl है तो दूसरी साइड भी BeCl। फिर CCl4, CH4, PCl5, SF6। तो ये सारे जो हैं नॉन पोलर मॉलिक्यूल्स हैं, तो इनका डाइपोल मोमेंट क्या होगा? 0। दो बॉन्ड्स पोलर हैं, PCl, SF, CCl, CH2 इट इज ऑलमोस्ट नॉन पोलर, BF, BeCl सारे बॉन्ड्स पोलर हैं, बट बॉन्ड की जो अरेंजमेंट है उससे नेट डाइपोल मोमेंट 0 आता है, इसलिए ये सारे नॉन पोलर मॉलिक्यूल्स हैं। तो ये सिमेट्रिकल ज्योमेट्री है सबकी। अगर मॉलिक्यूल हैं जिनके अनसिमेट्रिकल ज्योमेट्री हो, अनसिमेट्रिकल जिसमें बॉन्ड पेयर भी हो, लोन पेयर भी हो, जैसे अमोनिया ले लो, NF3 ले लो, H2O, H2S और हेट्रोडायटोमिक HCl, HBr, तो इन सब का डाइपोल मोमेंट जो है दैट इज नॉट इक्वल टू 0 और ये सारे मॉलिक्यूल क्या होंगे? पोलर मॉलिक्यूल्स, राइट। Can be used to distinguish between cis and trans isomer। You know, cis के केस में जैसे ये एग्जांपल ले लेते हैं, ये cis आइसोमर है और ये ट्रांस। तो सिस और ट्रांस में यहां पे CCl की वजह से पोलैरिटी टुवर्ड्स क्लोरीन, क्योंकि क्लोरीन इज मोर इलेक्ट्रोनेगेटिव। H को नहीं भी कंसिडर करेगा तो चलेगा, क्योंकि CH बॉन्ड इज ऑलमोस्ट नॉन पोलर, इसलिए CCl बॉन्ड कंसिडर किए। तो यहां पे क्या हो रहा है, पोलैरिटी ड्यू टू वन CCl इज कैंसल्ड बाय अदर, क्योंकि जस्ट अपोजिट डायरेक्शन में है, इसलिए इसका नेट डाइपोल मोमेंट इज ऑलमोस्ट 0। बट इसका डाइपोल मोमेंट इज ग्रेटर देन 0, क्योंकि ये नेट पैरेललोग्राम लॉ ऑफ वेक्टर एडिशन लग जाएगा। सो सिस का डाइपोल मोमेंट इज ग्रेटर देन ट्रांस। और इट कैन ऑल्सो बी यूज टू डिस्टिंग्विश बिटवीन ऑर्थो, मेटा एंड पैरा आइसोमर्स। तो आपको पता है बेंजीन रिंग जो है उसके रिस्पेक्ट में अगर यहां पे एक Cl लगाया है, यहां पे दो Cl है, तो ये ऑर्थो आइसोमर है, ऑर्थो डाइक्लोरोबेंजीन। दिस इज मेटा डाइक्लोरोबेंजीन। पैरा डाइक्लोरोबेंजीन। तो CCl में पोलैरिटीज टुवर्ड्स Cl, अभी ऊपर वाला जैसे किया हमने। तो इसमें तो क्या हो रहा है, जितना पोलैरिटी अप उतना डाउन, और इनके बीच में एंगल कितना होगा 180 डिग्री। इनमें एंगल इज 120 डिग्री, इधर एंगल इज 60 डिग्री। तो अभी हमने किया था कि जो रिजल्टेंट डाइपोल मोमेंट इज स्क्वायर रूट ऑफ a² प्लस b² प्लस 2ab cos theta. So as theta increases, cos theta decreases. थीटा इंक्रीज करता है तो cos थीटा डिक्रीज करता है। इसका मतलब एंगल जैसे जैसे बढ़ेगा वैसे वैसे जो डाइपोल मोमेंट की वैल्यू है वो कम होती जाएगी। इसका मतलब डाइपोल मोमेंट ऑफ ऑर्थो इज ग्रेटर देन मेटा इज ग्रेटर देन पैरा। और अगर दोनों ऐसे हैं जैसे Cl है, एक ही एटम है ना इसके ऊपर, तो ऐसे केस में डाइपोल मोमेंट क्या होगा 0। बट इट ऑल डिपेंड्स ऑन द सब्स्टिट्यूएंट्स। जैसे अगर मान लिया इस बेंजीन रिंग के ऊपर एक OH है, तो इनका डाइपोल मोमेंट 0 नहीं होगा, है तो पैरा ही ये भी, बट क्योंकि ये अनसिमेट्रिकल है तो इस केस में डाइपोल मोमेंट 0 ही होगा। इवन अगर एक तरफ CH3 है दूसरी तरफ Cl है तब भी डाइपोल मोमेंट 0 नहीं होगा। समझ में आया पॉइंट? यहां एक ही एटम था, जैसे Cn हो तो भी लीनियर होता है ना वो, तो भी 0 होगा। बट OH के केस में क्या होगा, लोन पेयर आगे बॉन्ड पेयर आगे हो गया ना, ये लीनियर नहीं है ये। इस केस में डाइपोल मोमेंट क्योंकि एग्जैक्ट कैंसलेशन नहीं होगी, और इस केस में तो होगा नहीं, CH3 का डाउन आएगा इसका भी डाउन आएगा, तो एक ही तरफ हो गया ना सारा, तो डाइपोल मोमेंट इज नॉट इक्वल टू 0। परसेंटेज ऑफ आयनिक कैरेक्टर निकाल सकते हैं हम बाय यूजिंग डाइपोल मोमेंट। परसेंटेज ऑफ आयनिक कैरेक्टर इज इक्वल टू एक्सपेरिमेंटल डाइपोल मोमेंट to the theoretical dipole moment multiplied by 100, or we can say observed dipole moment divided by dipole moment for 100% ionic character into 100. So this is all about dipole moment. नमस्कार दोस्तों, तो आज का हमारा क्वेश्चन जो है दैट इज वेरी वेरी इंपॉर्टेंट फ्रॉम योर एग्जामिनेशन पॉइंट ऑफ व्यू, दैट आउट ऑफ NH3 एंड NF3 विच वन हैज हायर डाइपोल मोमेंट एंड व्हाई। तो जब भी आपके पास ऐसे मॉलिक्यूल्स हों जिनमें दो से ज्यादा एटम्स हों, तो सबसे पहला काम है ड्रॉ द स्ट्रक्चर। तो अगर आप देखोगे नाइट्रोजन के वैलेंस शेल में 5 इलेक्ट्रॉन है, 5 में से 3 हाइड्रोजन अटैच हैं, तो 3 हाइड्रोजन में से 3 इलेक्ट्रॉन यूज हो गए, तो नाइट्रोजन के 3 बॉन्ड पेयर हैं और कितने इलेक्ट्रॉन बचे? 2। तो 2 का एक पेयर बनेगा, दैट इज 1 लोन पेयर। सो NH3 और NF3 दोनों में ही 3 बॉन्ड पेयर हैं और 1 लोन पेयर, और उसको हमने ड्रॉ कर लिया। ये लोन पेयर, 3 बॉन्ड पेयर, इसका भी एक लोन पेयर, 3 बॉन्ड पेयर। अब आपको पता है कि जो पोलैरिटी है ड्यू टू लोन पेयर, वो तो लोन पेयर की डायरेक्शन में ही होगी। बचे बॉन्ड्स, तो NH में विच वन इज मोर इलेक्ट्रोनेगेटिव? नाइट्रोजन। सो नाइट्रोजन की तरफ पोलैरिटी होगी इनकी, और नेट पोलैरिटी भी अपवर्ड ही होगी। इधर आ जाओ, नाइट्रोजन और फ्लोरीन में विच वन इज मोर इलेक्ट्रोनेगेटिव? फ्लोरीन। सो इसकी पोलैरिटी फ्लोरीन की तरफ होगी। अब बात करते हैं कि यहां पे दोनों एक ही डायरेक्शन में है, तो डाइपोल मोमेंट ड्यू टू लोन पेयर इज reinforced by net dipole moment due to NH bonds. Dipole moment due to lone pair is reinforced, added to the net dipole moment due to NH bonds. तो यहां पे एडिशन ऑफ डाइपोल मोमेंट्स हो रहा है क्योंकि दोनों वेक्टर्स एक ही डायरेक्शन में हैं। इधर आ जाओ, डाइपोल मोमेंट ड्यू टू लोन पेयर, बताओ क्या होगा? लोन पेयर, और ये तीनों का जो डाइपोल मोमेंट है वो कहां होगा? नेट डाउनवर्ड्स। सो इज पार्शियली कैंसल्ड बाय नेट डाइपोल मोमेंट बाय नेट dipole moment due to NF bonds. So पार्शियल कैंसिलेशन हो जाएगी। इस वजह से जो NH3 है दैट हैज हायर डाइपोल मोमेंट देन NF3। तो इतना सा लिखना है आपको कि लोन पेयर की डायरेक्शन में ही NH बॉन्ड की मूवमेंट्स है। बॉन्ड मूवमेंट जो है नेट बॉन्ड मूवमेंट और नेट डाइपोल मूवमेंट ड्यू टू NH बॉन्ड्स इज टुवर्ड्स लोन पेयर, एक ही डायरेक्शन में, इसलिए रीइंफोर्समेंट मिलेगी, बढ़ जाएगा डाइपोल मूवमेंट। इस केस में क्या हो रहा है? लोन पेयर का जो मूवमेंट है उससे अपोजिट डायरेक्शन में नेट NF बॉन्ड्स का डाइपोल मूवमेंट है, इसलिए पार्शियल क्या हो जाएगी? कैंसिलेशन। और बिकॉज ऑफ दैट NH3 हैज हायर डाइपोल मोमेंट देन NF3।
नमस्कार दोस्तों, so today we will discuss
VSEPR theory, that is valence shell electron pair repulsion theory. It was first proposed by Sidgwick and Powell in 1940 and later developed by Nyholm and Gillespie in 1957. So main features of this theory, or we can say main postulates of this theory are, the first postulate of VSEPR theory is that shape of the molecule depends upon the bonded or non-bonded electron pairs around the central atom. For example, if there are only two bond pairs, shape of the molecule is linear. If there are three bond pairs, shape of the molecule is trigonal planar. And if there are four bond pairs, shape of the molecule is tetrahedral. If there are five bond pairs, shape of the molecule is trigonal bipyramidal. And if we have six bond pairs, shape of the molecule is octahedral. And if we have seven molecules, then shape of the molecule is pentagonal bipyramidal. These are the basic shapes of the molecules. And why these shapes are like that? Because electron pairs tend to repel each other, because electron pairs are negatively charged, and you know like charges repel each other. That's why they try to maximize their distance and minimize the repulsion, so that arrangement is stable. That's why when there are only two bond pairs, then there is a 180-degree angle, means there are maximum distance apart and shape is linear. Now see, when we have three bond pairs, it is again planar and angle is 120 degree. Means each bond angle is 120 degree. But when there is one lone pair, two bond pairs, then keep in mind lone pair occupy more space than bond pairs. That's why lone pair repulsion is more than bond pair. Means lone pair repulsion is greater than lone pair bond pair repulsion, which in turn greater than bond pair repulsion. So when lone pair repel these bond pairs, and you know bond pair repulsion is less, so they come closer, so angle is less than 120 degree. And shape is called bent or V-shaped. Now here we have four bond pairs. Now this molecule is non-planar. It goes out of the plane. And you know these electron pairs lie in a sphere, in a spherical shape, so that the repulsion is minimum and stability is maximum. That's why angle is 109 degree 28 minute. Now when we have one lone pair, then what would happen? Lone pair repel more than bond pairs. So this type of shape is called trigonal pyramidal, and angle is less than 109 degree 28 minute. When we have two bond pairs and two lone pairs, then again arrangement is same, but now because lone pair repel each other, then lone pair repel bond pairs. That's why angle is less than even angle when there is one lone pair, and this shape is also called bent shape, V shaped or angular. Now come to this part. In this case, see, we have three bonds on the plane. These are called equatorial bonds. Two, one above the plane, other is below the plane. These three bonds are on the plane. These are called axial bonds. And equatorial angle is 120 degree. Axial angle is 180, and equatorial axial angle is 90 degree. So you can say angle is minimum here. So equatorial axial repulsion is maximum. So when we consider this repulsion, axial bonds have three equatorial bonds, means 390 degree repulsion on axial, and equatorial bonds have two axial bonds. So repulsion on equatorial bond is less. That's why axial bonds are longer than equatorial bonds. So lone pair if comes, that will occupy the position with less repulsion. So that will occupy equatorial positions. So when we have one lone pair, then shape is seesaw. When we have two lone pairs and three bond pairs, shape is T shape. It is slightly bent because lone pair repel these axial bonds, so it is called bent T shape. And when we have three lone pairs and two bond pairs, shape is called linear due to the symmetrical arrangement of lone pairs. Now come to this part. Here all the angles are at 90 degree. This is called octahedral shape, and when there is one lone pair along with five bond pairs, arrangement is octahedral, and this shape is called square pyramidal. Next, when we have two lone pairs and four bond pairs, shape is square planar. Right? Now come to this part. If there is one lone pair along with six bond pairs, then shape is generally distorted octahedral. Lone pair occupy one of the octahedron. This is called distorted octahedral shape. Postulate is multiple bond if it is there in any of the molecule. If multiple bond is there, multiple bond is treated as a single super pair, or we can say single electron pair in VSEPR theory or VSEPR model. Means अगर दो एटम के बीच में डबल बॉन्ड हो या ट्रिपल बॉन्ड हो, उसको हम सिंगल बॉन्ड ही कंसीडर करते हैं. Now come to sixth postulate. Sixth postulate is, on the basis of VSEPR theory, covalent molecules can have two types of geometries, regular and irregular. Regular geometry means if molecule has only bond pairs and all bond pairs are of same type. Same type means if, for example, we have methane. So in methane, carbon is attached to 4 hydrogens. That means all the bond pairs are of same type. और there should be no lone pair. Lone pair नहीं होना चाहिए. सिर्फ bond pair और bond pair भी एक जैसे. Means similar atoms attach होने चाहिए central atom से. तो इन केस में क्या होता है कि उनके जो इलेक्ट्रॉन पेयर्स हैं, उनके रिपल्सिव इंटरेक्शंस आर म्यूचुअली बैलेंस ईच अदर. और मॉलिक्यूल को बोलते हैं सिमेट्रिकल मॉलिक्यूल एंड हैज रेगुलर ज्योमेट्री. Now irregular geometry. If molecule has only bond pairs but bond pair में क्या हो कि जैसे मैंने लिख दिया CH3Cl, अब इसमें क्या है, 3 तो CH बॉन्ड्स है और एक CCl बॉन्ड है, तो सिर्फ बॉन्ड पेयर्स, पर बॉन्ड जो सेंट्रल एटम है दैट इज अटैच्ड टू डिफरेंट एटम्स। ये तो ऐसा केस हो, या मान लिया अमोनिया ले लिया आपने, अमोनिया में क्या है, 3 बॉन्ड पेयर 1 लोन पेयर, वाटर में 2 बॉन्ड पेयर 2 लोन पेयर। अगर ऐसा केस हो, या तो सिर्फ बॉन्ड पेयर हो बट बॉन्ड पेयर जो हैं वो अलग अलग टाइप के हो, मीन सेंट्रल एटम डिफरेंट एटम से अटैच हो, या फिर मॉलिक्यूल में बॉन्ड पेयर और लोन पेयर दोनों ही हो, तो ऐसे केस में जो रिपल्सिव इंटरेक्शंस है दे डू नॉट बैलेंस ईच अदर, म्यूचुअल बैलेंस नहीं होते हैं, तो ऐसे मॉलिक्यूल को हम बोलते हैं अनसिमेट्रिकल मॉलिक्यूल, और मॉलिक्यूल इज सेड टू हैव इररेगुलर ज्योमेट्री। तो ये 6th पोस्टुलेट है वेस्पर थ्योरी का। सो 7th पोस्टुलेट इज कि व्हेन अ मॉलिक्यूल इज रिप्रेजेंटेड बाय इट्स रेजोनेटिंग स्ट्रक्चर्स, मींस कैनोनिकल स्ट्रक्चर्स। आपको पता है ये रेजोनेंस कब होती है, व्हेन अ सिंगल लुईस स्ट्रक्चर कैनॉट एक्सप्लेन all the properties of molecule, more than one structure is required to explain their properties, तो उनको बोलते हैं हम रेजोनेटिंग स्ट्रक्चर्स और कैनोनिकल स्ट्रक्चर। तो बोलते हैं जो भी उसके कैनोनिकल स्ट्रक्चर होंगे हर स्ट्रक्चर के लिए वेस्पर मॉडल एप्लीकेबल होगा। ये हो गया वेस्पर थ्योरी का 7th पोस्टुलेट। 8th पोस्टुलेट इज कि डबल बॉन्ड जो होता है और सिंगल बॉन्ड में, you know, double bond requires more space around the central atom, that's why अगर हम repulsive interaction की बात करें, जैसे मैंने बताया था कि lone pair occupies more space than bond pair, अब bond pair ही है बट एक डबल बॉन्ड है एक सिंगल बॉन्ड है, तो बोलता है डबल बॉन्ड ऑक्यूपाई मोर स्पेस, उसमें क्या था, लोन पेयर ऑक्यूपाई मोर स्पेस, इसलिए लोन पेयर रिपल्शन इज ग्रेटर देन लोन पेयर बॉन्ड पेयर which in turn greater than bond pair। यहां पे डबल बॉन्ड की बात हो रही है, तो डबल बॉन्ड के बीच में जो रिपल्शन होगा दैट इज मोर देन डबल बॉन्ड सिंगल बॉन्ड which in turn greater than single bond। So this is postulate number 8। now come to the 9th postulate, that if we keep the central atom same but ऐसा central atom which has lone pair, अगर लोन पेयर नहीं होंगे तो सराउंडिंग एटम जो मर्जी होता रहे बॉन्ड एंगल रिमेन्स सेम। जैसे मैं लूं एक CH4 और दूसरा लूं CCl4 और पूछूं कि बॉन्ड एंगल कितना है, तो दोनों में ही बॉन्ड एंगल 109 डिग्री 28 मिनट होगा, क्योंकि ये क्या है, इनकी रेगुलर ज्योमेट्री है दोनों की। तो पहली कंडीशन कि मॉलिक्यूल की इररेगुलर ज्योमेट्री होनी चाहिए, तब ये 9th और 10th पोस्टुलेट एप्लीकेबल होगा। तो बोलता है कि इफ सेंट्रल एटम इज सेम एंड इलेक्ट्रोनेगेटिविटी ऑफ द सराउंडिंग एटम इंक्रीजेस, सराउंडिंग एटम की इलेक्ट्रोनेगेटिविटी अगर बढ़ाते हैं तो बॉन्ड एंगल क्या हो जाएगा, डिक्रीज, बॉन्ड एंगल डिक्रीज हो जाएगा, प्रोवाइडेड कि साइज कोई इफेक्ट ना करे और ना ही उसमें बैक बॉन्डिंग हो। वो हम अगले नेक्स्ट 11th पोस्टुलेट में बैक बॉन्डिंग के बारे में पढ़ेंगे कि बैक बॉन्डिंग से क्या होता है। बट हम एग्जांपल लेते हैं NH3 NF3। अब NH3 और NF3 में दोनों के पास 3 बॉन्ड पेयर है और एक लोन पेयर। अब इसकी शेप बनाओ, ऐसा हो जाएगा ट्राइगोनल पिरामिडल, ट्राइगोनल पिरामिड। अब आपको पता है कि फ्लोरीन इज मोर इलेक्ट्रोनेगेटिव देन नाइट्रोजन, तो जो बॉन्ड पेयर होगा दैट इज क्लोज टू फ्लोरीन, बट हियर नाइट्रोजन इज मोर इलेक्ट्रोनेगेटिव देन हाइड्रोजन, so lone bond pair is closer to नाइट्रोजन। सो यहां बॉन्ड पेयर रिपल्शन ज्यादा होगा, यहां बॉन्ड पेयर रिपल्शन कम, क्योंकि बॉन्ड पेयर के बीच में डिस्टेंस बढ़ गई। इसलिए वैसे लोन पेयर इन बॉन्ड पेयर को तो रिपेल कर ही रहा है, दोनों में एंगल लेस देन टेट्राहेड्रल होगा ड्यू टू लोन पेयर, बट इन दोनों का कंपैरिजन करें तो जिसमें सराउंडिंग एटम की इलेक्ट्रोनेगेटिविटी ज्यादा होगी उसका बॉन्ड एंगल कम होगा। तो ऑर्डर ये होता है, इसका 107 डिग्री होता है बॉन्ड एंगल और इसका होता है 102 डिग्री। तो ये भी याद रखना है। नेक्स्ट इज कीपिंग द सराउंडिंग एटम सेम एंड चेंज द सेंट्रल एटम। तो लेट अस टेक again अमोनिया और PH3। तो इन दोनों की बात करें अगर अमोनिया और PH3 की, तो आपको पता है नाइट्रोजन इज मोर इलेक्ट्रोनेगेटिव, फॉस्फोरस इज लेस इलेक्ट्रोनेगेटिव। तो एज नाइट्रोजन इज मोर इलेक्ट्रोनेगेटिव तो बॉन्ड पेयर ज्यादा क्लोज होंगे सेंट्रल एटम के, इसमें थोड़े दूर होंगे, इस वजह से यहां रिपल्शन कम होगा, यहां रिपल्शन ज्यादा होगा, इसलिए बॉन्ड एंगल ऑफ NH3 इज ग्रेटर देन PH3। सो कीपिंग द सराउंडिंग एटम सेम, इफ इलेक्ट्रोनेगेटिविटी ऑफ द सेंट्रल एटम हैविंग लोन पेयर increases then bond angle increases। so इसका एंगल होता है 107 डिग्री और इसका 93.8 डिग्री। इसको कैसे रैशनलाइज करते हैं भाई, इट इज क्लोज टू 90, वो हमने पिछले वीडियो में आपको बताया था कि यहाँ पे ड्रैगोज रूल लगता है, बट यहाँ पे सिर्फ ये बात हो रही है कि अगर सेंट्रल एटम की इलेक्ट्रोनेगेटिविटी बढ़ती है तो बॉन्ड एंगल भी इंक्रीज करता है। सो ये हो गया 10th postulate। नाउ कम टू 11th postulate। 11th postulate is कि sometimes lone pair may be transferred from filled shell of an atom to unfilled shell of the adjacent bonded atom। जो दोनों एटम ने बॉन्ड बनाया है, एक के पास फील्ड ऑर्बिटल हो, लोन पेयर हो। लोन पेयर किसमें होना चाहिए, जो कि डोनेटिंग पावर रखता हो। मोस्ट ऑफ द केसेस में वो फ्लोरीन हो सकता है, ऑक्सीजन हो सकता है, नाइट्रोजन हो सकता है, समटाइम्स इट इज क्लोरीन, ब्रोमीन, आयोडीन, फास्फोरस, सल्फर। तो वो डोनेट करेंगे और सामने वाले के पास वेकेंट ऑर्बिटल होना चाहिए, देन दिस ट्रांसफर टेक्स प्लेस। तो उस फिनोमिनन को हम बोलते हैं बैक बॉन्डिंग, और उसमें जो बॉन्ड बनता है दैट इज पाई कोऑर्डिनेट बॉन्ड, पाई कोऑर्डिनेट बॉन्ड। तो उस बैक बॉन्डिंग का इफेक्ट होता है सीधा ही बॉन्ड एंगल पे, जैसे हमने पिछले पढ़ा ना कि कीपिंग द सेंट्रल एटम सेम, इलेक्ट्रोनेगेटिविटी ऑफ द सराउंडिंग एटम इफ इट इंक्रीजेस बॉन्ड एंगल डिक्रीजेस, बट provided other factors will not affect it like size and back bonding। अब हम बैक बॉन्डिंग का इफेक्ट देखेंगे। जैसे मैं ले लूं एक PH3 और दूसरा ले लूं PF3। अब PH3 की बात करोगे तो क्या होगा, देयर इज वन लोन पेयर, 3 बॉन्ड पेयर, हियर अगेन वन लोन पेयर, 3 बॉन्ड पेयर। तो जैसे हमने NH3 और NF3 का किया था, अगर उस बेस पे सोचे हम तो किसका बॉन्ड एंगल ज्यादा होना चाहिए, ऑब्वियसली PH3 का, क्योंकि इसमें बॉन्ड पेयर जो है दैट इज क्लोजर टू फ्लोरीन, इसमें क्लोजर टू फॉस्फोरस, इसलिए यहां पे रिपल्शन बॉन्ड पेयर ज्यादा होगा, यहां बॉन्ड पेयर रिपल्शन कम होगा। तो ये ऑर्डर होना चाहिए, बट इट इज रॉन्ग, ये ऑर्डर सही नहीं है। अब ये ऑर्डर सही नहीं है तो सही है क्या फिर, उसको एक्सप्लेन करने के लिए
ये बैक बॉन्डिंग का कंसेप्ट आता है। इसमें बैक बॉन्डिंग होती है। उसमें क्या था, नाइट्रोजन था, नाइट्रोजन हैज नो वेकेंट डी ऑर्बिटल, बट यहां फॉस्फोरस है, यू नो फॉस्फोरस बिलोंग्स टू थर्ड पीरियड, इट हैज वेकेंट डी ऑर्बिटल। इसलिए क्या होता है, फॉस्फोरस के वेकेंट डी ऑर्बिटल को जो फ्लोरीन है उसका फिल्ड पी ऑर्बिटल बैक डोनेट करता है इलेक्ट्रॉन, उससे फ्लोरीन और फास्फोरस के बीच में डबल बॉन्ड कैरेक्टर आ जाता है। तो अब क्या होगा, फास्फोरस जो है उसके ऊपर एक लोन पेयर तो है ही, अब डबल बॉन्ड एक जगह पे, कहीं भी एक जगह पे डबल बॉन्ड, अगर यहां पे डबल बॉन्ड बनता है, अब ये देखो अगर आप इसको कोऑर्डिनेट बॉन्ड बनाते हो तो इसको ऐसे रहने दो, बट अगर इसको आप कोवलेंट बॉन्ड बनाते हो तो फ्लोरीन पे क्या आएगा, पॉजिटिव, फास्फोरस पे क्या आएगा, नेगेटिव, क्योंकि फ्लोरीन डोनर है और फास्फोरस एक्सेप्टर। वैसे ही या तो डबल बॉन्ड इसमें बनेगा या डबल बॉन्ड कोई भी एक फ्लोरीन एट ए टाइम इलेक्ट्रॉन डोनेट करेगा, या फिर यहां। दैट मीन्स इसमें फास्फोरस और फ्लोरीन के बीच में देयर इज अ डबल बॉन्ड कैरेक्टर। तो बिकॉज ऑफ दिस डबल बॉन्ड कैरेक्टर, अभी पढ़ा हमने कि डबल बॉन्ड रिपेल मोर देन सिंगल बॉन्ड, डबल बॉन्ड रिपल्शन इज मोर देन डबल बॉन्ड सिंगल बॉन्ड, विच इन टर्न ग्रेटर देन सिंगल बॉन्ड सिंगल बॉन्ड। तो इस वजह से डबल बॉन्ड आने की वजह से जो बॉन्ड एंगल है वो कम तो नहीं हो सकता। मैं नहीं बोल रहा हूं कि बहुत ज्यादा बढ़ जाए, बट कम होने के चांसेस नहीं है। इसलिए जो PF3 है, बिकॉज ऑफ दिस डबल बॉन्ड कैरेक्टर बाय बैक बॉन्डिंग, और कौन सी बैक बॉन्डिंग हुई, P पाई D पाई बैक बॉन्डिंग। और इसको बैक बॉन्डिंग क्यों बोलते हैं, क्योंकि फ्लोरीन तो मोर इलेक्ट्रोनेगेटिव है, तो इलेक्ट्रॉन इसकी तरफ आने चाहिए, बट ये तो वापस दे रहा है ना फ्लोरीन को, फास्फोरस को, इसलिए इसको बैक बॉन्डिंग बोलते हैं। और इससे पाई बॉन्ड बनता है, इसलिए P पाई D पाई बैक बॉन्डिंग, क्योंकि सिग्मा बॉन्ड तो ऑलरेडी बना होता है ना, इसलिए P पाई D पाई बैक बॉन्डिंग बोलते हैं। और इस वजह से जो PH3 है उसका बॉन्ड एंगल कम होगा, PF3 का ज्यादा होगा। और बॉन्ड एंगल इसका तो पता ही है आपको 93.8 डिग्री होता है, और इसका जो है 97.8 डिग्री होता है। तो इस तरह से वी कैन एक्सप्लेन द कंसेप्ट ऑफ बैक बॉन्डिंग। तो ये बैक बॉन्डिंग का कंसेप्ट मैंने आपको बताया। अब अगर हम साइज का इफेक्ट देखें, और आपको पता है NH3 NF3, इनको हमने देखा कि NF3 का जो है वो बॉन्ड एंगल इज लेस देन NH3, इसका 107 डिग्री था, इसका 102 डिग्री। क्यों, क्योंकि फ्लोरीन इज मोर इलेक्ट्रोनेगेटिव देन हाइड्रोजन। अगर मैं इसके साथ NCl3 भी ले लूं, अब ये तीनों में अगर हमने बॉन्ड एंगल लिखना हो तो अकॉर्डिंग टू आवर कंसेप्ट, इलेक्ट्रोनेगेटिविटी कंसेप्ट, क्या होना चाहिए, सबसे बड़ा एंगल NH3 का, फिर NCl3, फिर NF3, ऐसा होना चाहिए। क्यों, क्योंकि हाइड्रोजन सबसे कम इलेक्ट्रोनेगेटिविटी की वैल्यू देखें तो हाइड्रोजन की इलेक्ट्रोनेगेटिविटी सबसे कम, क्लोरीन की उससे ज्यादा, फ्लोरीन की सबसे ज्यादा। और जैसे जैसे सराउंडिंग एटम की इलेक्ट्रोनेगेटिविटी बढ़ती है तो बॉन्ड एंगल कम होता है। तो बॉन्ड एंगल का ऑर्डर ऐसा होना चाहिए एज पर कंसेप्ट ऑफ इलेक्ट्रोनेगेटिविटी, विच इज रॉन्ग। अब आप बोलोगे ये तो सारा कंफ्यूज हो गया, बट दीज आर द एक्सेप्शंस
जो आपको अगर आती होगी तो दैट मेक्स योर कंसेप्ट स्ट्रॉन्गर एंड बूस्ट योर मोरल. तो लेट अस टेक दिस एग्जांपल इन द नेक्स्ट लेवल के ये जो NCl3 है इसमें आपको पता है कि यहाँ पे बैक बॉन्डिंग पॉसिबल नहीं है क्योंकि नाइट्रोजन और हाइड्रोजन में वेकेंट ऑर्बिटल कोई है ही नहीं, इधर भी बैक बॉन्डिंग पॉसिबल नहीं है. बट यहां पे अगर बात करोगे तो यू नो नाइट्रोजन और क्लोरीन, नाइट्रोजन हैज filled orbital and chlorine has vacant orbital. So nitrogen can back donate its electron to chlorine, but back donation is very very less क्योंकि नाइट्रोजन का जो ऑर्बिटल है वो 2p है और इसका क्या है 3d. नाइट्रोजन का 2p, इसका 3d, बट एनी हाउ ड्यू टू बैक बॉन्डिंग डबल बॉन्ड कैरेक्टर आएगा और लोन पेयर का जो इफेक्ट है कम हो जाएगा. इसलिए जो NCl3 है उसका बॉन्ड एंगल सबसे बड़ा होता है और उससे कम NH3 और सबसे कम NF3. दिस इज नॉर्मल ऑर्डर, बट ये जो ऑर्डर आगे आया इट इज ड्यू टू बैक बॉन्डिंग. अगेन p पाई d पाई बैक बॉन्डिंग. और इसको साइज से भी हम समझा सकते हैं, बट दिस इज द बेस्ट एक्सप्लेनेशन फॉर द ऑर्डर. दिस इज द राइट ऑर्डर क्योंकि यहां पे बैक बॉन्डिंग पॉसिबल है, बाकियों में बैक बॉन्डिंग नहीं होती, इसलिए NCl3 का बॉन्ड एंगल इन दोनों से ज्यादा है. So today we will learn shapes of the molecules. You know how to calculate bond pairs and lone pairs of a molecule. After calculating bond pair and lone pair, we can predict the shapes. For example, if a molecule has two bond pairs, central atom along with two bond pairs, then shape of the molecule is linear. This is basic shape of a molecule. The shape of the molecule is linear when we have two bond pairs. Now, if we have three bond pairs, when we have three bond pairs, then shape of the molecule is trigonal planar. Shape of the molecule is trigonal planar. Angle in case of linear is 180 degree. Here angle is 120 degree. Now same case when we have three pairs but two bond pairs and one lone pair, then see arrangement is same. Two bond pairs and we have one lone pair, so one position is occupied by lone pair. Now the shape, see this lone pair is not included in the shape. First thing, because lone pair bond pair repulsion is greater than bond pair repulsion, therefore bond angle is less than 120. At the same time shape is decided by bond pairs, so it is V shaped, or we say angular or bent, right? Four pairs. First case is if we have all the bond pairs, then basic shape or geometry or arrangement, it is tetrahedral. Now if we have three bond pairs and one lone pair, now one position of the tetrahedral is occupied by lone pair. Now
the shape is trigonal pyramidal. Trigonal pyramidal. And if we have two bond pairs and two lone pairs, then two positions are occupied by lone pair. So now two positions are occupied by lone pair, and it is like when we have two lone pairs and two bond pair, see, shape is V shaped or angular or bent. So in this way, when we have four pairs, shape is tetrahedral, that is regular geometry. If we have one lone pair, then shape is pyramidal, trigonal pyramidal. If we have two lone pair, then shape become V-shaped or angular or bent. Now, angle in case of a regular tetrahedral, angle is 109 degree 28 minutes. Here angle is less than this, and when we have two lone pairs, bond angle is lesser than this. That means order of bond angle is like this. Okay, in case of 5 bond pairs, basic shape is trigonal bipyramidal. Basic shape is trigonal bipyramidal. Now in this case, all the bonds are not equivalent. In the case of linear, trigonal, planar, tetrahedral, all the bonds are equivalent. But in this case, there are two types of bonds. First is the bonds in the trigon. These are called equatorial bonds. E for equatorial bonds. And these two are called axial bonds. Equatorial bonds and axial bonds. Now see, in the equatorial, these are three. So this axial bond forms 390 degree angle with the three bonds, 90 degree angle with three bonds. So 90 degree bond pair repulsion on axial bonds are 3. But same 90 degree bond pair repulsion on equatorial bonds are only 2, because equatorial bonds there are two 90 degree repulsion, because equatorial bonds are 90 degree with the axial bonds and axial bonds are at 90 degree with equatorial bonds. That's why axial bonds are longer than equatorial bonds. Axial bonds are longer than equatorial bonds. So repulsion on axial bond is more than on equatorial bonds. So if we have lone pair, then lone pair occupy equatorial positions because repulsion on equatorial bonds is less. For example, if we have 4 bond pairs and 1 lone pair, then lone pair is on the equatorial position, and this is called seesaw. This shape is known as seesaw. If we have 2 lone pairs, then again 2 lone pairs are on equatorial, and because of these lone pairs, bond pair are slightly bent, so this is called bent T-shaped. See, it is a T. If we rotate it, it become a T. If we rotate it, it becomes seesaw. Now, if we have all the 3 lone pairs, all the 3 positions, 3 equatorial positions are occupied by lone pairs. So shape is linear, right? 6 bond pairs. If we have 6 bond pairs, then geometry is octahedral. Geometry is octahedral, and all the angles are at 90 degree. Now if we have one lone pair, then because now all the positions are equivalent, so one lone pair occupy one of the position, so it become square pyramidal. If we have two lone pairs, then shape is square planar, right? So these are the shapes for 6 bond pairs. All the bonds are at 90 degree. If we have 7 bond pairs, 7 electron pairs, then the regular shape is pentagonal, bipyramidal. If we have one lone pair, then its shape become distorted octahedral. 6 bond pairs form octahedron, and one of the position is occupied by lone pair. One of the octahedron is occupied by lone pair, so it is distorted octahedral if we have 6 bond pairs and one lone pair. Types of orbital overlap: sigma and pi bond. You know, covalent bond. What is covalent bond? Covalent bond is formed by mutual sharing of electrons. Now, when this covalent bond is formed, there is a mutual sharing of electrons, means there is overlap of atomic orbitals. So, depending upon the type of overlapping, the covalent bond is divided into sigma and pi bond. Depending on the type of overlap, the covalent bond are separated as here, or they are defined as sigma bond or pi bond. Okay, first we will discuss sigma bond. So sigma bond is denoted by letter sigma. So this is called head-on overlapping, head-on overlapping of atomic orbitals or axial overlap of atomic orbitals. Okay, and because of this head-on overlapping is maximum in sigma bond. Overlapping region is large. So sigma bond is more stable and large amount of energy is released. When sigma bond is formed. So keep in mind that on sigma bond formation, energy released is more, overlapping is more effective, and that's why this bond is more stable. Okay, and overlapping region is quite large. It is written, overlapping region is large. Okay, and at the same time, most of the time S and P orbitals are involved in bonding in most of the cases. Okay, so if we compare these orbitals, so sigma bond is formed between S and S, SS overlapping, or EP overlapping, or SP overlapping. So these are the three types of sigma bonds formed. In SS, there is one S overlap with another S, and this overlapping is along the internuclear axis. Overlapping is along the internuclear axis, on the internuclear axis. See, what is the internuclear axis? Axis passing through the nuclei of the bonded atoms. This is the axis passing through the nuclei of the bonded atoms, right? Now in PP case, this is p orbital dumbbell shape. So one lobe of each orbital overlap with each other. So this is PP type overlapping. And SP, one S orbital. S orbital is spherically symmetrical, and one p orbital. So these are the three types of sigma bonds formed. Okay, out of these, SS is more stable than SP, which in turn more stable than PP. Okay, so in pi bond there is sidewise or lateral overlapping between atomic orbitals of bonded atoms. If there is sidewise or lateral overlapping, means it is not head on, there is sidewise overlapping. Okay, side to side. Therefore in this case, overlapping is less, overlapping region is less than in sigma bond. So bond is comparatively weaker. Bond is comparatively weaker. It is not as strong as sigma bond, because here overlapping is less as compared to sigma bond, because in sigma bond overlapping is head on. Okay, but here overlapping is sidewise. That's why bond is comparatively weak. Okay, you can write weak or weaker. ठीक है. Now here only pp overlapping is considered. S orbital can never form pi bond. Keep in mind, S orbital can never form pi bond, and there is only pp overlapping. Where, see, this is p orbital, this is second p orbital, they overlap with each other sidewise. This is internuclear axis, so overlapping is above and below the internuclear axis, means it is perpendicular to internuclear axis. So there are two electron clouds, one above the plane, other below the internuclear axis. If we write it as plus minus crust and trough, so plus overlap, minus, so it is like this. One electron cloud is above the internuclear axis, other is below the internuclear axis, but overlapping is less as compared to sigma. So let us find out what is the difference between sigma and pi bond. Difference between sigma and pi bond. And keep in mind, pi bond is always formed. Pi bond is always formed between already bonded atoms. Already sigma bonded atom means pi bond cannot be formed alone. Sigma bond can be formed alone, but pi bond is formed when already one sigma bond is there. Okay, so difference between sigma and pi bond, you can write pi like this or pi. Okay. So sigma bond and pi bond. Difference between sigma and pi bond. This may be the question of 2 marks. Okay? Many times there is a question. Yes, sigma and pi both are covalent bonds. They are formed by mutual sharing of electrons, but first bond is always sigma bond and next multiple bonds are pi. For example, if we have this bond, these are single bond, double bond, triple bond. So in first case it is always sigma bond. Single bond is always sigma bond. Then here, with few exceptions, there are only 2 exceptions. Sigma bond and 1 pi bond. Here 1 sigma bond and 2 pi bonds. In this case, there is only 1 sigma bond between 2 atoms. Okay, 1 sigma bond. Here 1 sigma bond and 1 pi bond. Here 1 sigma bond and 2 pi bonds. If there are 3 bonds, one is sigma is always 1, other are pi bonds. The bond is formed, sigma bond, the bond is formed by axial overlap of the atomic orbitals. Okay, yes, we have done now that bond, the bond which is formed by axial or head-on overlap of atomic orbitals, that is called sigma bond, and the bond pi bond, the bond is formed by sidewise overlap of the atomic orbitals. Is it visible? Yes. Okay. Second, the overlap is, yes, in sigma bond overlap is large or small? Yes. Tell me. In sigma bond overlap is large or small? Yes. So the overlap is quite large and bond is strong. In this case, overlap is less and bond is comparatively weak, right? S orbital can take part, S orbital can take part in sigma bond formation, but here S orbitals do not take part in pi bond formation, right? Only p orbitals, okay, s orbital can never participate in pi bond formation. Then the only one lobe of p orbitals, only one lobe of p orbitals is involved in the overlap. You saw na? Like this, only one lobe is involved, but in pi bond both the lobes of p orbital are involved in bond formation. The electron cloud because when atomic orbitals combine, they form molecular orbitals, right? The electron cloud of molecular orbital is symmetrical, around the internuclear axis. Okay, here the electron cloud is unsymmetrical. It is above and below the internuclear axis. The bond is formed in the absence of pi bond. bond can be formed. The bond means sigma bond can be formed in the absence of pi bond. It cannot be can be formed alone. Okay, but pi bond cannot be formed in the absence of sigma bond. Okay, see, free rotation of sigma bond is possible because see, if we have single bond, the single bond, so that can be rotated easily, but if we have double bond, rotation is not possible. Rotation around the internuclear axis is not free. We have to break it to get it free. Okay, so free rotation of the atom around sigma bond is free. Okay, is possible, sorry. But free rotation of atoms around pi bond is not possible. Okay, free rotation of the atom around sigma bond is possible, but around pi bond is not possible because pi bond is along with sigma bond, so that is at least double bond, so free rotation of the atom is not possible. Let us discuss the formation of N2 molecule. On the basis of orbital overlap concept, let us discuss what is the overlapping concept for N2 molecule. On the basis of valence bond theory, see, in nitrogen, you know what is its electronic configuration? 1s2, 2s2, 2p, 3. How many electrons are required? First condition, nitrogen, valence shell is involved in overlapping, right? So this is for nitrogen. Okay, 2s fully filled and 2p half filled. Now second nitrogen. So when second nitrogen comes closer to it, then these 2p orbitals, they are of opposite spin. They should be of opposite spin. So they overlap with each other. First form sigma bond. This overlapping gives pi bond. Second also gives pi bond. So 2p orbital overlap with 2p to give first sigma bond, and then 2p, next 2p overlap with 2p to give pi bond, and there is lone pair on each nitrogen. So in this way we can explain it. Okay, overlapping concept. So what are the favorable conditions for orbital overlap? Got it? So favorable conditions conditions orbital overlap. Only half-filled atomic orbitals can take part in the overlap. Okay, first condition. Second condition, at the time of overlap, the combining atomic orbitals must have opposite spin. You can see in nitrogen, combining atomic orbitals must have opposite spin, right? Second condition. Now what is the third condition? The overlap must be maximum as far as possible. Overlap must be maximum as far as possible. Okay, so these are the favorable conditions for the formation of bond by overlap or orbital overlap. Okay, let us see the case of F2. So first condition is only half-filled orbitals take part in the overlap. Second condition is at the time of overlap, combining atomic orbitals must have opposite spin. And third condition is overlap must be maximum. Let us take the case of F2. In F2, fluorine has electronic configuration 1s2, 2s2 and 2p5. So fluorine valence shell 2s2 and 2p5. So second F it should be like this. Then okay, so they can overlap and form a sigma bond. And there are 3 lone pairs on each fluorine. Three lone pairs and 1 sigma bond. Let us discuss the formation of H2O. Now in H2O, there are 2 hydrogens and 1 oxygen. So first draw the oxygen. It is 2s2 and 2p4. Like so 2 hydrogens. So one hydrogen right this side, other hydrogen you can write or other side or on the same side you can write anywhere. Now this hydrogen has up spin, oxygen has up spin, so hydrogen should have downspin in order to overlap. This hydrogen has upspin, oxygen has upspin, so hydrogen should have downspin to overlap. So two sigma bonds are formed and it has two lone pairs. So oxygen, two sigma bonds and two lone pairs. In same way you can draw for ammonia. So in ammonia we have nitrogen, so nitrogen there is two S2 2p3, so three hydrogens. So upspin it should have downspin. Upspin it should have downspin. Upspin it should have downspin. So three sigma bonds are formed. So here there is one lone pair and three sigma bonds. Okay, so why these atoms combine with each other to become more stable? That means bond is formed when they become stable. So what about helium? Helium cannot form bond. Why is it so? Helium is already stable. When there are two hydrogen atoms come close to each other, attractive forces are more than repulsive forces. And when two helium atoms come close to each other, repulsive forces are more than attractive forces. So that is the concept of valence bond theory. That's all we have done, this overlap concept. So let us take two hydrogen atoms, Ha and Hb. Now in hydrogen there is nuclei and one electron each. There are nuclei and one electron each. So hydrogen A has nucleus A and electron. So this nucleus attracts its electron. Second nucleus also attracts its electron. This nucleus of first hydrogen, A hydrogen atom, nucleus of A attract electron of A and nucleus of B attract electron of B. When they are isolated, they are separated. One. Now when they come close to each other, what happened? They continue to attract each other, but now this nucleus repel nucleus of other atom. This electron repel electron of the other atom. These are the new repulsive forces. See, these are the repulsive forces. Means force of repulsion. nucleus of A repel nucleus of B, electron of A repel electron of B. Okay, so these are the repulsive forces. Now come to attractive forces. We have already seen that nucleus of A attract electron of A and nucleus of B attract electron of B. But now when they come closer, say nucleus of A is attracting nucleus of electron of A, nucleus of B attracting electron of B. These are the old forces. Now electron of B attract nucleus of A. New attractive force. Nucleus of A attract electron of B and nucleus of B attract electron of A. Okay, these are the forces of attraction and these two are forces of repulsion. But attractive forces are more than repulsive forces. That's why when they come closer, as attractions are more, then energy is released, continue to release, and it reaches minimum and then increases. So this is the minimum. And this is called bond length. I think we have done this part. Here force of attractions are greater than force of repulsion. Force of attraction is equal to force of repulsion. Force of attraction is less than force of repulsion. I think we have done this. This is called valence bond theory. And this equilibrium distance between the two atoms when potential energy is minimum, that is called bond length. Okay? Helium-2 does not exist. If question is why is helium-2 does not exist on the basis of valence bond theory, then we can explain it like this. In this case, we can say that attractions are more than repulsions. Why helium-2 does not exist? Why helium-2 does not exist? If question is this, then nucleus of A in helium, let us consider two atoms. Nucleus of A, first electron, second electron. Nucleus of electron of A1, A2. First electron of A, second electron of A. First electron of B, second electron of B. Okay, so this nucleus has two electrons. Second nucleus also has two electrons. Okay, so if we talk about attractive forces, nucleus of A1, nucleus of A with A2, they are already existing. Nucleus of B attract nucleus as electron of B, but when they come closer, then nucleus of B also attract electron of A, nucleus nucleus of B also attract electron of A. Okay, nucleus of A also attract this. That means nucleus of A is in attraction with EB1 and nucleus of A is in attraction with EB2. So these are the attractive forces, right? Because each electron attract both the nuclei. Each electron attract both the nuclei. Total 4 electrons, so 8. 1, 2, 3, 4, 5, 6, 7, 8. Now come to repulsive attractions. Nucleus of A, nucleus of B. EA1, EB1, EA2, EB2. So nucleus of A repel nucleus of B, electron A repel electron B, electron EA2 repel this, EB1, EA2, EA2, EB2. Even EA1 repel EA2, EB1 repel EB2. So repulsive forces. These are the attractive forces. So we write repulsive. Nucleus of A repel nucleus of B. EA1 repel EA2. EA1 repel EB1. EA1 repel EB2. See, one electron repel 3 other electrons. So there are total 4, so total 12. So these are the repulsive forces, and repulsive forces are dominating over attractive forces. Always. That's why helium atoms will not come close to each other to form a bond. Means if we write the diagram, means potential energy diagram, it should be like this for helium 2. It is always upward. It will never goes down. So there is no minima in the potential energy diagram. Okay, that's why helium 2 does not exist. So this is all about valence bond theory, theoretical concept of hybridization. It is just mixing of 2 or more things. If you talk about s orbital is spherical and p orbital is dumbbell. S orbital is spherical and p orbital is dumbbell, right? Plus minus, there is only plus. So s orbital and this is p orbital. When they mix, they form orbital like this, in which one lobe is bigger than the other. Say in this case both the lobes are equal, but when s orbital mix with p, then the number of orbitals which mix together is equal to number of hybrid orbitals. Okay, when they mix, they give new orbitals, or these 2 new orbitals are like this. Means they have bigger one lobe and smaller the one is smaller lobe and other is bigger lobe. So if bigger lobe overlap, the area of overlap is more, so strength is more. That means hybridization takes place to strengthen the bond, right? So now let us see what is its definition. So if question is define hybridization, so you can see it is just mixing. So write down the exact definition. The phenomenon, you can write from here. the phenomenon of mixing of atomic orbitals, phenomenon of mixing of atomic orbitals of same atom, is it visible, with slight difference in energies. Say, energy difference should not be very large. Mixing of atomic orbitals of the same atom, first thing. Second thing, there is no large difference in energies. Means those belongs to the same shell. Orbital, like 1s orbital cannot mix with the 2s. Okay, but 2s and 2p they can mix together. 3s and 3p they can mix together. Okay, means they should have slightly different energies. Okay, so of slightly different energies, so as to redistribute their energies, so as redistribute their energies. Like, s orbital is lesser in energy, more stable. P orbital slightly large in energy. So when they mix together, what happened? Energy of P orbital is slightly decreased. Energy of s orbital is slightly increased. So midway there is a mixing, means hybrid is formed, and give new orbitals of equivalent energies and shape. And these new orbitals are called hybrid orbitals. These orbitals are called hybrid orbitals, and they are lying in specified directions. For example, if we have, just like now we can apply VSEPR theory. If we have two hybrid orbitals, so tell me, what is the arrangement of those two hybrid orbitals? It is linear. When two hybrid orbitals are there, they lie in a straight line. So now conditions for hybridization. Conditions for hybridization. First, define hybridization, that we have covered. Now, what are the conditions for hybridization? First condition, only the orbitals of the same atom are taking part in hybridization. Okay? The first condition is only the orbitals belonging to the same atom are taking part in hybridization. This is the first condition. Now, from the definition, tell me what should be the second condition? The orbitals taking part in hybridization, I can write this only, should have energy or should have small energy difference. Okay, this is the second condition that can be taken from the definition. Now, third condition. Say, after getting these conditions, say, if we have methane or ammonia. To write third condition, I am giving you example. Say in carbon ground state has 2s2 and 2p2. Tell me how many electrons are required to form CH4. In methane, how many unpaired electrons are required? That's it, 4. But in ground state, GS is ground state, stable state of carbon atom. In stable state of carbon atom, how many electrons are unpaired? Only 2. That means to form methane, carbon should be in excited state. One of the electron from 2s should shift to 2p. Right? After this shifting, now it has 4 unpaired electrons and now it undergoes hybridization. That means electron is promoted to 2p and then it gets hybridization. 1s and 3p. So sp, 3 hybridization. 4 hybrid orbitals are formed. In ammonia, nitrogen has 2s2, 2p3. So now tell me, in ammonia, in nitrogen in ground state has how many unpaired electrons? 3. So, see, only 3 bonds it has to form. And nitrogen has 3 unpaired electrons. So there is no need to promote this pair. That means lone pair can also participate in hybridization. Okay. So promotion of electrons. Here promotion is essential. But here promotion is not required. So third point is promotion of electron is not essential. Promotion of electron is not essential prior to hybridization. In methane, you can see that we need 4 unpaired electrons, but carbon in its ground state has only 2 unpaired electrons. So promotion is required. Excitation of 2s. Promotion means excitation. Okay. So 2s electrons should be promoted to 2p in order to get 4 unpaired electrons so that they can overlap with 1s orbital of hydrogen to form methane. But in this case, you know, nitrogen has 3 unpaired electrons. Nitrogen has 3 unpaired electrons, right? So when it has 3 unpaired electrons and only 3 bond it has to form, then there is no need to promote the electron. There is no need to shift this electron to anywhere. Just these 3 can. That means there are 4 hybrid orbitals. Out of 4, 3 are three form bonds, bond pairs, and 1 is lone pair. not only half-filled orbitals, this is the example, even fully filled orbitals can participate in hybridization. See, you can change the wording you can change, but don't change the meaning. If you shuffle these words, okay, you can write half-filled as well as fully filled orbitals can participate in hybridization. That is the same thing. If you write half-filled as well as fully filled orbital can participate in hybridization, it has same meaning. Or not only half-filled, even fully filled orbitals can participate in hybridization. Or not only half-filled but fully filled orbitals can participate in hybridization. But please don't change the meaning. Okay? That's it. Okay, so these are the conditions of hybridization. That orbitals belong to the same atom. Orbitals taking part in hybridization should have same energy. Promotion is not essential. Okay, and half-filled as well as fully filled orbitals can participate in hybridization. Now, characteristics of hybridization, or we can say features, salient features of hybridization. Visible? Yes. So first is same conditions and definition. You can combine those statements, you get the features. First, only orbitals of slightly different energies can participate in hybridization. Yes, like in carbon, you know, it has 1s2, 2s2, 2p2, right? So carbon, if you write, it is 1s1, 2s2 and 2p2, and after promotion it is like this. So it means that this 1s will not participate in hybridization. 1s cannot mix with 2p. 2s can mix with 2p because they have slightly different energies. Because see, 1s, 2s, 2p. It is like this. So 2s and 2p, they have slightly different energies, so they can participate. They can mix. But 1s cannot mix with 2s and 2p. Now, second thing. If you think that, say, if we have nitrogen, nitrogen has 2s, 2 and 2p, 3. So, in this case, only 3 bonds we have to form. So, why not these 3 can mix? But hybridization tells us that orbitals of the same shell cannot hybridize on its own. They cannot mix together. They can mix with S. there should be some other subshell. Okay, so 2px, 2py and 2pz mixed with 2s. Got it? Means we can write it like that: orbitals of a particular subshell, orbitals of a particular subshell cannot hybridize of their own because they have same energy. See, their shape is same, dumbbell, all are dumbbell, their energy is same, so they cannot mix together. Okay, they can mix with any other orbital having which is in the different subshell of slightly different energy. Point is the number of hybrid orbitals, is equal to number of atomic orbitals participating in hybridization. Third point, simple. If one S and one P they mix together, then we will get two sp hybrid orbitals. See, one S and one P. When they mix together, I will write one S plus one P orbital. They mix together, we get two sp hybrid orbitals, right? 1s plus 2p, they mix together, then we how many, or we get 3 sp2 hybrid orbitals. Now tell me, if 1s and 3p orbitals mix together, tell me what would we get? If 1s and 1p mix together, we get sp hybrid orbitals. How many? 2, because there is 1s and 1p. If 1s and 2p combine together, then we get 3 sp2. Very good, Raghab. If we combine 1s and 3p, then we get 4 sp3 hybrid orbitals. It means it has 1 part of s and 3 part of p in each orbital. 1 part of s, 2 part of p in each orbital. 1 part of s, 1 part of p in each orbital. Hybridization never takes place in an isolated atom. Means if atom is isolated, isolate means when it is not forming bond, simple atom is there, then hybridization has no role to play. There is no hybridization of an isolated atom. But and it occurs in atoms taking participation in bond formation. Those which can form bond, okay, that only undergoes hybridization. Actually, main advantage is I showed you that if we have P and S, they overlap to form two hybrid orbitals having large size. So when they have large size, they can form stronger bond, means overlapping region is more. So hybridized orbitals are most effective. Hybridized orbitals, or we can say hybrid orbitals, are more effective. Hybrid orbitals are more effective in forming stable bonds than pure atomic orbitals. That's why we use the concept of hybridization, because hybrid orbitals can form stronger bond. They can form more stable bond than the pure atomic orbitals because their area of overlap is large. Effectiveness of overlapping is more in hybrid orbitals rather than pure atomic orbitals. So this is the point number 5. Now, see, if you talk about shape, if we have sp hybridization, arrangement is linear. If we have sp2 hybridization, arrangement is trigonal planar. If we have sp3 hybridization, arrangement is tetrahedral, and so is the shape. Okay, so the shape of the molecule or shape of the covalent molecules can be predicted on the basis of hybridization. The shape of covalent compounds can be determined or can be predicted on the basis of type of hybridization. So we know the type of hybridization of the central atom, we can predict its shape, arrangement or geometry. So these are the features of hybridization. We have done definition of hybridization, conditions for hybridization, as well as features of hybridization. Okay, now first case, let us discuss sp hybridization. So in sp hybridization, we have one s and one p orbital. Okay, when they mix, that is called sp hybridization. We get two sp hybrid orbitals and they are arranged in linear arrangement. There is linear arrangement of these two hybrid orbitals. Only bigger lobe participate in overlapping. Smaller lobe will not take part in bonding. Keep in mind this thing. Only bigger lobe participate. So arrangement is linear. and hybrid orbital has either lone pair or they form sigma bond, but unhybridized orbital can form pi bond. Okay, so now for example, for in sp hybridization, let us discuss the case of ethine. So see, in ethine, it is C2H2, or you have drawn its structure like this. Am I right? So see, tell me, each carbon has how many sigma bond and how many pi bonds? When this is like when plus overlap with plus, then negative overlap is negative. So we get larger part of plus and larger part of negative. Okay, but when we have larger part of positive and positive part interact with negative part, what happened? We have smaller positive and smaller negative. So say when we have S, it is positive, in P positive negative. So when positive interact, it becomes bigger. When positive, this plus interact with negative, this is destructive interference, so it becomes smaller. Each carbon, say this is sigma and pi, means each carbon has 2 sigma bonds and 2 pi bonds. 2 sigma, 2 pi, each carbon has 2 sigma bonds and 2 pi bonds. Now, got it? Why positive part is bigger and negative part is smaller? Okay. This is related to wave concept, okay? Now let us discuss about structure of methane. So, ethine. Ethine is also called acetylene. Its another name is acetylene. Okay. Now, carbon, but each carbon forms 4 bonds. So it should have 4 unpaired electrons. First condition. Out of 4, only 2 form sigma bonds. So 2 hybrid orbitals and 2 unhybrid orbitals. See, carbon in its ground state, its electronic configuration is 2s2 and 2p2. So in excited state, one of the electron gets promoted from 2s to 2p. Okay, 2s to 2p. So now we have 4 unpaired electrons, but out of 4, only 2 gets hybridized. Why is it so? Because it forms 2 sigma bonds only. Each carbon forms 2 sigma bonds. That means this carbon has 2 smaller part. I am not showing. There is no need to show smaller part because that is not taking part in hybridization. That we have shown earlier to just show you how it responds when they mix. Positive part becomes bigger, negative part becomes smaller. So negative part I am not showing. Only the part which is participating in bonding, that is shown here. Each carbon has 2 sp hybrid orbital. This is sp hybrid. This is also sp hybrid. And along with this, there are 2 unhybridized p orbital. So 1 and 2. There are 2 unhybridized p orbital. Okay, plus minus plus minus. It's your choice to write plus minus or not. It is up to you only. Now second carbon. In second carbon, one sp hybrid orbital overlap with each other. They should be equal in size, okay? And another sp hybrid orbital. And two unhybridized p orbital. This plus minus, it is your choice. Better to avoid the confusion, better to remove them. There is no need to write plus minus, okay? And plus minus, you know what is that? Crest and trough. So now, say one sp hybrid orbital of each carbon overlap with each other to form carbon-carbon sigma bond, and one carbon left, sp hybridized carbon left on each carbon overlap with 1s orbital of hydrogen. It overlap with 1s orbital of hydrogen. 1s orbital of hydrogen. That's it. This is CH sigma bond, CH sigma bond. Concept of sigma bond is clear. This hybrid part shows crest. You know, 1s has crest plus part. Okay, so this plus part overlap with plus part. See 1s orbital, its shape is like this, that you know, only plus part is there. Okay, so crest, 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 crest. Trough part is not participating. Pi bond. This orbital has same symmetry as this. Orbitals of same symmetry overlap sideways. Okay, to form pi bond. Right? This is one pi bond. One electron cloud above the plane, other electron cloud below the plane. Okay, and second p orbital on each carbon having same symmetry overlap again sideways to form second pi bond. But now say two electron clouds, one above the plane, other below the plane. So what about other two? Second pi bond is formed. Again we have two electron clouds, total 4 electron clouds. So how we will arrange them? One above the plane, one below the plane. Okay. So what about other two? Front and back. Front and back. Because on this side there is carbon hydrogen sigma bond. Okay. So it is like this. One above the plane, one below the plane, and others are like this. Okay. So they form a whole cylindrical shape. They form a cylindrical pi electron cloud. Like this. See. So it is like carbon, hydrogen, sigma bond, carbon, hydrogen, carbon, carbon, sigma bond, and one electron cloud above the plane, other electron cloud below the plane. So they are like this. That is cylindrical pi electron cloud. There is a formation of cylindrical pi electron cloud. The shape is linear, right? How do we write this pi electron cloud? Because there are 4 electron clouds for 2 pi bonds. One pi bond has 2 electron clouds, one above the plane, one below the plane. Okay, so In ethyne there are 4 electron clouds. Okay. So now sp2. In sp2, we have carbon, S and 2 P. So 3 orbitals overlap. sp2 hybridization, and we get 3 sp2 hybrid orbitals, and arrangement is like this: trigonal, planar. Arrangement is trigonal, planar. 1s and 2p, they mix together and we get trigonal planar arrangement of 3 sp2 hybrid orbitals. They are all sp2 hybrid orbitals. Then, so let us discuss the case of ethene. So in ethene, it is C2H4. So in C2H4, you know that it is like CH2 double bond CH2, or we can write it as C double bond C H H H H. That you have done in class 10. Okay. Now, again tell me now, each carbon form how many sigma bonds and how many pi bonds? There are 3 sigma bonds and 1 pi bond. Again 3 sigma bond, 1 pi bond. So, carbon in ground state again has 2s2 and 2p2, but it forms 4 bonds. So it goes in excited state. 1. So 4 unpaired electrons. Out of 4, 3 are involved in sigma bond formation. So sp2 hybridization. So each carbon has sp2 hybridization. sp2, sp2, sp2. 1 sp2 hybrid orbital overlap with each other, and other 2 on each carbon overlap with 1s orbital of hydrogen. Right? And each carbon left with 1 unhybridized orbital. And that unhybridized orbital, these are unhybridized orbital. Okay? They overlap sideways. So they form sigma bonds, and electron cloud is formed one above the plane and other below the plane. One above the plane, one below the plane, and arrangement is, or shape is, trigonal. Okay. So now sp3 hybridization. In sp3 hybridization, okay, Siddharth, Poonam means Siddharth, right? Okay, Siddharth. In sp3 hybridization, 1s and 3 p orbitals. You can write plus minus like this or either way. And so when these 4 orbitals mix together, it undergoes sp3 hybridization, form 4 sp3 hybrid orbitals, and they are arranged like this. They are sp3 hybrid orbitals, means plus 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 plus, right? Minus 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 minus. Arrangement is tetrahedral and angle is 109 degree 28 minutes. Yes, we have not discussed about angle. So in SP, linearly arranged, so 180 degree angle. In trigonal planar, there is 120 degree angle, and here angle is 109 degree 28 minutes. So we will discuss the angle in detail in the next class. Okay. Now just we should look at the shapes only. See, let us take example of methane and ethane, both. In methane, see, it is CH4 and this is C2H6, means CH3 CH3, or you can write it as like this. So each carbon form 4 sigma bonds. In methane, each carbon form 4 sigma bonds. That means carbon in the ground state, again same condition, there are only 2 unpaired electrons, so it undergoes excitation and we get 4 unpaired electrons. All are hybridized because it forms 4 sigma bonds. Now carbon sp3 hybrid orbital, and each sp3 hybrid orbital overlap with 1s orbital of hydrogen. So tetrahedral arrangement like this. In ethane, each carbon has 4 sp3 hybrid orbital. Arrangement is tetrahedral. Out of 4, 1 of each carbon overlap with each other to form carbon-carbon sigma bond, and one s orbital of hydrogen. So it is like this. You know, angle is 109 degree 28 minutes, and carbon hydrogen bond length, carbon sp3 hybrid, carbon hydrogen bond length is 111 picometer, keep in mind, and carbon carbon bond length is 154 picometer. Carbon carbon single bond length, carbon carbon single bond length is 154 picometer. Okay. In ethene, okay, let us write all the 3 and compare. This is ethane, this is ethane, and this one is ethine. Ethane, ethene, and ethine. If we talk about bond angle, Here bond angle is 109 degree 28 minute. Here angle is 120 degree and here angle is 180 degree. Now tell me, say there are two angles HCH. According to hybridization, that is sp3, angle is 109 degree 28 minute. In ethane, each carbon is sp2 hybridized, so bond angle should be 120. In ethyne, each carbon is sp hybridized, so bond angle should be 180. But now tell me, HCH and HCC, are they equal or different? HCH, this one, theta 1, okay, and this one, theta 2. So tell me, are these theta 1 and theta 2 is equal or different? It is different. Why is it so? Because double bond repel more than single bond. Because this is bulkier group, so it should be away from hydrogens. Hydrogen, they are very small, so they can come closer easily. And at the same time, single bonds repel less than double bond. Yes, it is unequal. So which one is larger? Obviously theta 2 is greater than theta 1. Okay? There is slight difference. It is 121 degree. It is 117.5 degree. Okay? Because of this double bond, single bond, size, all that counts. Okay? Now tell me, carbon, sp3, carbon, it is 154 picometer. Carbon, single bond. Okay. And what about carbon, double bond? It is 134 picometer. And carbon, triple bond length. Okay, bond length. That is 120 picometer. 154, 134, and around about 120 ethyne. Yes, it is 120 picometer. Now carbon hydrogen bond length of sp3, carbon hydrogen bond length of sp2, and carbon hydrogen bond length of sp. sp3, sp2, sp, which one is larger in size? sp3, because that has more number of orbitals involved. Okay, 1s3p, so that is bigger in size. 1s2p, smaller. 1s1p, still smaller. Okay, yes, Namita. So sp3, that's why its bond length is 111 picometer. Here it is 110 picometer and it is only 108 picometer. Though all are single bonds, but hybridization plays an important role. If we talk about reactivity, because of pi bond, it is more reactive. In triple bond, pi bond is delocalized. It is not locked. This pi bond is locked above and below, but this pi bond is delocalized. So alkene is more reactive because of pi bond. Though alkyne is also reactive, but less reactive than this. In the chemical properties hydrocarbon chapter, we will discuss all the reactivity concept. Ethane, because single bond, sigma bond, very strong bond, so it is least reactive. आज कर रहे हैं हम molecular orbital theory and hydrogen bonding वाला part. तो molecular orbital theory जो है वो it was given by
these two scientists, that is Hunt and Mulliken, इन्होंने मॉलिक्यूलर ऑर्बिटल थियरी जो है उसको डेवलप किया था इन 1932 और उनका फर्स्ट पोस्टुलेट जो है वो क्या है कि जैसे इलेक्ट्रॉन होते हैं एक एटम में, वो किसमें प्रेजेंट होते हैं? एटॉमिक ऑर्बिटल में। एटम्स जो है, जो इलेक्ट्रॉन होते हैं एटम में, वो किसमें होते हैं? इन एटॉमिक ऑर्बिटल्स। और जो इलेक्ट्रॉन्स होते हैं द मॉलिक्यूल आर प्रेजेंट इन वेरियस मॉलिक्यूलर ऑर्बिटल। तो देखो एटम में इलेक्ट्रॉन्स किसमें होते हैं? एटॉमिक ऑर्बिटल में। और मॉलिक्यूल में जो है वो होते हैं मॉलिक्यूलर ऑर्बिटल में। ओके, तो ये हो गया फर्स्ट पॉइंट एमओटी का कि इलेक्ट्रॉन एटम में जैसे एटॉमिक ऑर्बिटल में होते हैं, वैसे ही मॉलिक्यूल में जो इलेक्ट्रॉन होते हैं वो मॉलिक्यूलर ऑर्बिटल्स में होते हैं। मॉलिक्यूल में मॉलिक्यूलर ऑर्बिटल होते हैं, एटम्स में एटॉमिक ऑर्बिटल। और मॉलिक्यूलर ऑर्बिटल कैसे बनते हैं? एटॉमिक ऑर्बिटल के कॉम्बिनेशन से। कौन से एटॉमिक ऑर्बिटल? जिनके कंपेरेबल एनर्जीज हो और क्या हो? प्रॉपर सिमेट्री। जैसे 2px से ओवरलैप कर सकता है, ठीक है ना, बट 2px 4px से ओवरलैप नहीं कर सकते क्योंकि एनर्जी डिफरेंस बहुत ज्यादा होगा। 2px 3px से भी नहीं कर सकता क्योंकि शेल ही चेंज हो गया, ठीक है ना। 2px 2py से भी नहीं कर सकता क्योंकि उनकी जो सिमेट्री है वो प्रॉपर नहीं होगी। तो वही मॉलिक्यूलर ऑर्बिटल कंबाइन करते हैं जिनके कंपेरेबल एनर्जी हो, मतलब एनर्जी ऑलमोस्ट इक्वल हो और सिमेट्री जो है वो प्रॉपर हो, ठीक है। वो ही बनाते हैं मॉलिक्यूलर ऑर्बिटल्स, वही एटॉमिक ऑर्बिटल। सो एक एटॉमिक ऑर्बिटल में जो इलेक्ट्रॉन होता है वो किसके इन्फ्लुएंस होता है? ओनली वन न्यूक्लियस। बट मॉलिक्यूलर ऑर्बिटल जो होता है उसमें जो इलेक्ट्रॉन होता है दैट इज अंडर द इन्फ्लुएंस ऑफ टू और मोर न्यूक्लियाई डिपेंडिंग अपॉन द नंबर ऑफ एटम्स इन द मॉलिक्यूल, कि मॉलिक्यूल में कितने एटम्स है ना। तो एटॉमिक ऑर्बिटल जो है मोनोसेंट्रिक होता है और मॉलिक्यूलर ऑर्बिटल जो होता है वो क्या होता है? पॉलीसेंट्रिक। एटॉमिक ऑर्बिटल इज मोनोसेंट्रिक, मॉलिक्यूलर ऑर्बिटल इज पॉलीसेंट्रिक। और नंबर ऑफ मॉलिक्यूलर ऑर्बिटल जो बनते हैं दैट इज इक्वल टू द कंबाइनिंग एटॉमिक ऑर्बिटल। मान लिया दो एटॉमिक ऑर्बिटल कंबाइन किए तो दो ही मॉलिक्यूलर ऑर्बिटल बनेंगे, जिसमें एक होगा बॉन्डिंग और दूसरा क्या होगा? एंटी बॉन्डिंग। अगर 3 कंबाइन करते हैं तो 3 मॉलिक्यूलर ऑर्बिटल बनेंगे, उसमें क्या होगा? एक बॉन्डिंग, एक एंटी बॉन्डिंग और एक होगा नॉन बॉन्डिंग। तो याद रखना कि बॉन्डिंग की एनर्जी हमेशा कम होती है, एंटी बॉन्डिंग की एनर्जी हमेशा ज्यादा होती है। तो बेटर होता है कि हम इसको भी एनर्जी की टर्म में लिखते कि नीचे वाला बॉन्डिंग और ऊपर वाला एंटी बॉन्डिंग। वैसे 4 मॉलिक्यूलर ऑर्बिटल ज्वाइन करेंगे तो 4 मॉलिक्यूलर ऑर्बिटल बनेंगे जिसमें 2 बॉन्डिंग होंगे और 2 क्या होंगे? एंटी बॉन्डिंग। 2 एंटी बॉन्डिंग, 2 बॉन्डिंग। बॉन्डिंग मॉलिक्यूलर ऑर्बिटल जो होते हैं उनकी एनर्जी क्या होती है? लो। मैंने अभी बताया आपको। और स्टेबिलिटी ज्यादा होगी ऑब्वियसली, जिसकी एनर्जी कम उसकी स्टेबिलिटी ज्यादा एंटी बॉन्डिंग ऑर्बिटल से। और जैसे हम इलेक्ट्रॉन प्रोबेबिलिटी डिस्ट्रीब्यूशन जो न्यूक्लियस के अराउंड एटम में वो किससे डिटरमिन करते हैं? एटॉमिक ऑर्बिटल से। वैसे ही जो इलेक्ट्रॉन प्रोबेबिलिटी डिस्ट्रीब्यूशन है अराउंड अ ग्रुप ऑफ न्यूक्लियाई मॉलिक्यूल में, इट इज गिवन बाय मॉलिक्यूलर ऑर्बिटल। तो मॉलिक्यूलर ऑर्बिटल जो है जस्ट लाइक एटॉमिक ऑर्बिटल कैसे फिल होंगे? जैसे जो प्रिंसिपल यूज किए थे हमने, अक्वा प्रिंसिपल, पॉलीज एक्सक्लूजन प्रिंसिपल, हर्ट्ज रूल, स्ट्रक्चर ऑफ एटम में किए ना, वो जो फिलिंग का ऑर्डर है मॉलिक्यूल का इज ऑलवेज एक्सपेरिमेंटली डिसाइडेड। यहाँ कोई n प्लस एल रूल नहीं चलता है, जो उसमें था n प्लस एल रूल एटॉमिक ऑर्बिटल के केस में, इसमें जो है वो एक्सपेरिमेंटली डिसाइड करते हैं मॉलिक्यूलर ऑर्बिटल की एनर्जी का ऑर्डर, फिलिंग का ऑर्डर। ओके, तो ये हो गए अपने पोस्टुलेट्स। अब फॉर्मेशन जो है मॉलिक्यूलर ऑर्बिटल का, दैट इज ऑन द बेसिस ऑफ, इसको बोलते हैं LCAO, LCAO, लीनियर कॉम्बिनेशन ऑफ एटॉमिक ऑर्बिटल। ठीक है, A एंड B, तो A का ऑर्बिटल लिया साई A, B का साई B, तो बॉन्डिंग मॉलिक्यूलर ऑर्बिटल क्या होगा, जिसमें एडिशन ऑफ वेव फंक्शन है, देखो प्लस साइन है बीच में, और एंटी बॉन्डिंग में क्या होगा, इसको हम स्टार से डिनोट करते हैं, और ये होगा दोनों का डिफरेंस, एक में एडिशन ऑफ वेव फंक्शन, एक में सब्ट्रैक्शन ऑफ वेव फंक्शन। ये एडिशन और सब्ट्रैक्शन क्या है मैं आगे बताता हूं आपको। तो देखो जो प्रोबेबिलिटी डेंसिटी है ना, इलेक्ट्रॉन डेंसिटी, वो साई स्क्वायर से डिनोट करते हैं हम। तो बॉन्डिंग मॉलिक्यूल के लिए साई स्क्वायर क्या हो जाएगा, साई ए प्लस साई बी होल स्क्वायर, तो साई ए स्क्वायर साई बी स्क्वायर प्लस 2 साई ए साई बी। इसका मतलब ये हुआ कि ये देखो, अगर प्योर ए है तो इतनी इलेक्ट्रॉन डेंसिटी होनी चाहिए, यूनिफॉर्मली डिस्ट्रीब्यूट होगी ना, अगर साई बी होगा तो इतनी होनी चाहिए, और अगर बॉन्ड बन जाता है तो दो न्यूक्लियस के बीच में इतनी इलेक्ट्रॉन डेंसिटी बढ़ जाएगी, ये एक न्यूक्लियस ये दूसरा न्यूक्लियस, इनके बीच में इलेक्ट्रॉन डेंसिटी वैसे तो होनी चाहिए साई ए स्क्वायर फ्रॉम वन साइड, साई बी स्क्वायर फ्रॉम द अदर साइड, तो साई ए स्क्वायर प्लस साई बी स्क्वायर होनी चाहिए थी, बट इतनी अमाउंट में बढ़ जाती है। ठीक है, जब बॉन्डिंग मॉलिक्यूलर ऑर्बिटल बनता है तो इस वजह से देखो ये एक का है साई का, ये दूसरा साई, तो ये जो पार्ट है उसमें इलेक्ट्रॉन डेंसिटी बढ़ जाती है। और अब इलेक्ट्रॉन डेंसिटी जब बढ़ेगी, देखो ये न्यूक्लियस है ये न्यूक्लियस, इनके बीच में अगर इलेक्ट्रॉन डेंसिटी बढ़ जाती है तो इसका मतलब इनके बीच में जो रिपल्शन है न्यूक्लियर के बीच में वो कम हो जाएगा, और इलेक्ट्रॉन क्या पार्ट प्ले करेंगे, अट्रैक्शन का, अट्रैक्शन बढ़ाने का काम करेंगे। इससे बॉन्डिंग मॉलिक्यूलर ऑर्बिटल जो है उसकी एनर्जी कम हो जाती है, एनर्जी कम और स्टेबिलिटी ज्यादा। वैसे ही एंटी बॉन्डिंग की बात करें तो एंटी बॉन्डिंग में क्या होता है, साई ए माइनस साई बी का होल स्क्वायर, तो जितना दोनों का सम है इतनी इलेक्ट्रॉन डेंसिटी से माइनस पार्ट, देखो माइनस 2 साई ए साई बी, इतना जो है पार्ट कम हो जाता है, इतना पार्ट कम हो जाता है। देखो साई ए प्लस साई बी एक साइड ऐसा है, साई और साई स्क्वायर का, देखो पर एंटी बॉन्डिंग जब बनेगा, बॉन्डिंग में क्या होता है, इलेक्ट्रॉन डेंसिटी बिटवीन द न्यूक्लियर इंक्रीजेस, इलेक्ट्रॉन डेंसिटी न्यूक्लियर के बीच में बढ़ जाती है, तो रिपल्शन जो है न्यूक्लियर के बीच में वो क्या हो जाता है, डिक्रीज, और स्टेबिलिटी क्या हो जाती है, इंक्रीज। बट एंटी बॉन्डिंग में क्या होता है, देखो जब साई स्टार साई ए और साई बी हमने प्लॉट किया तो ये माइनस है ना इसके बीच में, तो ये उल्टा हो जाएगा बी वाला पार्ट, बट जब साई स्टार स्क्वायर करेंगे तो ये पार्ट दोनों क्या हो जाएंगे, ऊपर आ जाएंगे, ये पार्ट ऐसे चला जाएगा ना ऊपर, देखो, बट एक पार्ट आएगा, ये देखो जहां इलेक्ट्रॉन डेंसिटी 0 होगी, नोड आएगा। नोड क्या होता है, वेयर द प्रोबेबिलिटी ऑफ फाइंडिंग द इलेक्ट्रॉन इज निल। तो देखो इलेक्ट्रॉन डेंसिटी बिटवीन द न्यूक्लियाई क्या हो रही है, डिक्रीज, तो रिपल्शन जो है न्यूक्लियाई के बीच में, क्योंकि न्यूक्लियाई के बीच में न्यूक्लियर न्यूक्लियर दोनों क्या है, पॉजिटिव पॉजिटिव, अगर इलेक्ट्रॉन की डेंसिटी थिन है तो इनके बीच में जो है रिपल्शन बढ़ जाएगा, रिपल्शन बढ़ जाएगा तो एनर्जी इंक्रीज हो जाएगी, एनर्जी इंक्रीज हो जाएगी तो स्टेबिलिटी डिक्रीज हो जाएगी। तो देखो ऐसा बनता है, ये साई ए एटॉमिक ऑर्बिटल, ये साई बी एटॉमिक ऑर्बिटल, तो ये दोनों कंबाइन करेंगे तो एक बनेगा बॉन्डिंग और एक बनेगा एंटी बॉन्डिंग। तो बॉन्डिंग की एनर्जी क्या हो जाती है, कम, और एंटी बॉन्डिंग की एनर्जी बढ़ जाती है। तो देखो H2, तो हाइड्रोजन जो है इट इज 1s1। तो जब ये दोनों 1s ऑर्बिटल आपस में ओवरलैप करेंगे तो ऐसा इलेक्ट्रॉन डेंसिटी बीच में देखो एक पार्ट बनाया है, ओवरलैपिंग, है ना, मतलब रियल बॉन्ड जो बनता है वो बॉन्डिंग मॉलिक्यूल से बनता है। तो सिग्मा बॉन्ड बनेगा, ये अभी बताया सिग्मा एंड पाई कि इंटरन्यूक्लियर एक्सिस के सिमेट्रिकल है जो ओवरलैपिंग है, तो सिग्मा बॉन्ड है। और सिग्मा बॉन्ड जो रियली बनता है दैट इज सिग्मा मतलब बॉन्डिंग मॉलिक्यूल। तो सिग्मा 1s हो गया, ठीक है। और जो इनके बीच में माइनस साइन का मतलब है कि एक का क्रस्ट और दूसरे का ट्रफ, तो ये दोनों तो आपस में ओवरलैप करते नहीं है, तो प्लस माइनस क्या होगा, प्लस वाला पार्ट भी छोटा हो जाएगा और माइनस वाला पार्ट भी, इसको इसमें ओवरलैपिंग नहीं है, ओवरलैपिंग नहीं हो सकती इनमें, ठीक है। तो ये क्या बनेगा, एंटी बॉन्डिंग। और देखो इनके बीच में जो है इलेक्ट्रॉन की डेंसिटी नील है, और इसको बोलते हैं बेटा नोडल प्लेन। इसका मतलब जब बॉन्डिंग मॉलिक्यूल बनता है सिग्मा, तो नोडल प्लेन नहीं होता है कोई भी, बट जब एंटी बॉन्डिंग बनता है तो देयर इज वन नोडल प्लेन, तो एक नोडल प्लेन बनता है उसमें, ठीक है। उसके बाद आ जाओ हाइड्रोजन मॉलिक्यूल की फॉर्मेशन। तो देखो हाइड्रोजन, ये इसको मॉलिक्यूलर ऑर्बिटल डायग्राम भी बोलते हैं, है ना। तो इसमें क्या होगा, इलेक्ट्रॉनिक कॉन्फ़िगरेशन जो है हाइड्रोजन एटम की, मॉलिक्यूल की सॉरी, दैट इज सिग्मा 1s2, क्योंकि जब 1s और 1s ओवरलैप करते हैं तो क्या बनता है, सिग्मा 1s और सिग्मा स्टार 1s। तो जब दो इलेक्ट्रॉन है, जब दो एटॉमिक ऑर्बिटल के इलेक्ट्रॉन पास आएंगे तो उनकी स्पिन क्या होगी, अपोजिट, तो दोनों पेयर अप कर जाएंगे। ये देखो सिग्मा 1s बना दिया, ठीक है। इसको जरूरी नहीं है कि आप डाउन स्पिन लिखो, इसको अप स्पिन लिख सकते हो, बट जब वो बॉन्ड बनाएगा दोनों इलेक्ट्रॉन पास आएंगे तो वो ऐसे होने चाहिए, है ना, अपोजिट स्पिन के, है ना। तो सिग्मा 1s2 इसकी इलेक्ट्रॉनिक कॉन्फ़िगरेशन हुई। तो बॉन्ड ऑर्डर क्या होता है, नंबर ऑफ बॉन्डिंग इलेक्ट्रॉन्स माइनस नंबर ऑफ एंटी बॉन्डिंग इलेक्ट्रॉन्स डिवाइडेड बाई 2, तो बॉन्ड ऑर्डर आएगा 1। और दूसरी बात कि इलेक्ट्रॉन पेयर्ड है, तो अगर पेयर्ड होते हैं तो क्या बोलते हैं उसको, डायमैग्नेटिक। अगर अनपेयर्ड इलेक्ट्रॉन होते हैं तो पैरामैग्नेटिक। नाउ क्वेश्चन है कि He2 मॉलिक्यूल डज नॉट एग्जिस्ट, तो क्यों, तो आप लिखोगे हीलियम क्या होता है 1s2, ये भी हीलियम 1s2, जब कंबाइन करेंगे 1s 1s तो एक सिग्मा 1s बनेगा, एक सिग्मा स्टार 1s। सिग्मा स्टार 1s की एनर्जी क्या होगी, ज्यादा, सिग्मा 1s की एनर्जी कम, बट टोटल इलेक्ट्रॉन हो गए 4, तो दो दो इलेक्ट्रॉन आ जाएंगे, तो सिग्मा 1s में भी 2, सिग्मा स्टार 1s में भी 2। तो बॉन्ड ऑर्डर जो है बॉन्डिंग माइनस एंटी बॉन्डिंग डिवाइड बाय 2, तो बॉन्ड ऑर्डर आएगा बेटा 0, बॉन्ड ऑर्डर आया 0। सो इसका मतलब कोई बॉन्ड ही नहीं है बिटवीन टू हीलियम एटम्स, दैट्स व्हाई हीलियम 2 मॉलिक्यूल डज नॉट एग्जिस्ट। तो हम बोलेंगे कि हीलियम 2 मॉलिक्यूल डज नॉट एग्जिस्ट, that's why helium 2 molecule does not exist because there is no bond between two helium atoms। ये important question है। Now come to next, MO electronic configuration of homodiatomic molecules। तो देखो अभी बताया था मैंने कि 1s ओवरलैप करता है तो क्या बनता है सिग्मा 1s। अगर 1s का जो है एडिशन ऑफ वेव फंक्शन होता है तो सिग्मा 1s, और अगर सब्ट्रैक्शन ऑफ वेव फंक्शन होता है तो एंटी बॉन्डिंग सिग्मा स्टार 1s। और देयर इज वन नोडल प्लेन, सिग्मा 1s में देयर इज नो नोडल प्लेन। 2s ओवरलैप करेंगे तो क्या बनेगा सिग्मा 2s एंड सिग्मा स्टार 2s। तो अगेन सिग्मा 2s में नो नोडल प्लेन, सिग्मा स्टार में वन नोडल प्लेन। 2px ओवरलैप करेंगे तो क्या होगा, देखो यहाँ पे जो न्यूक्लियर के बीच में हम लाइन खींच रहे हैं इंटर न्यूक्लियर एक्सिस, उसके ऊपर और नीचे ओवरलैप हो रही है, तो ये क्या, और ये कौन सा बॉन्ड बना, पाई बॉन्ड। कौन सा बॉन्ड बना, पाई बॉन्ड। और एक लोब अबव द प्लेन, एक बिलो द प्लेन, तो ये बना पाई 2p x एंड देयर इज वन नोडल प्लेन। ये वाला जो है दैट इज अ नोडल प्लेन। तो पाई 2px में एक नोडल प्लेन होता है। अब पाई स्टार की बात करते हैं, तो देखो मैंने प्लस साइन लगाया है, बट देखो ये अपोजिट है, इसको दो तरह से लिख सकते हैं, प्लस माइनस, माइनस प्लस माइनस, या फिर ये प्लस हटा दो, ये माइनस हटा दो, प्लस कर दो, तो ये साइन चेंज हो जाएंगे, माइनस प्लस माइनस, और ये माइनस माइनस प्लस, ऐसे लिख सकते हैं। तो इसका और ये प्लस सामने आया माइनस के, माइनस सामने आया प्लस के, तो प्लस के सामने माइनस मतलब क्रस्ट के सामने ट्रफ। अगर क्रस्ट के सामने ट्रफ आएगा तो क्रस्ट का पार्ट भी छोटा हो जाएगा, ट्रफ का पार्ट भी छोटा हो जाएगा। यहाँ ट्रफ का पार्ट छोटा, क्रस्ट का पार्ट भी छोटा, तो ये दो नोडल प्लेन बनेंगे। देयर आर टू नोडल प्लेन्स। तो एक बना पाई 2px और दूसरा बना पाई स्टार 2px। एक में 2px प्लस 2px या 2py, वैसे ही 2py माइनस 2py, तो एक में पाई स्टार एक में पाई, वैसे ही 2px में पाई 2px पाई स्टार 2px। अब आ जाओ 2pz। 2pz में क्या होता है, z को हम लेते हैं इंटर न्यूक्लियर एक्सिस, z इज टेकन एज इंटर न्यूक्लियर एक्सिस। अब देखो अगर मैं इंटर न्यूक्लियर एक्सिस x लेता तो सिग्मा 2px बनता, याद रखना कई बुक्स में ऐसा भी लिखा है, पर हमारी जो NCERT है उसमें z इज टेकन एज इंटर न्यूक्लियर एक्सिस, तो इसलिए z pz जब ओवरलैप करेंगे तो क्या बनाएंगे, देखो प्लस प्लस ओवरलैप करेंगे तो प्लस वाला पार्ट बड़ा और माइनस वाले पार्ट जो है छोटे हो जाएंगे। देखो ये जो प्लस और प्लस ओवरलैप करेंगे ना, प्लस वाला पार्ट बड़ा हो जाएगा, और सॉरी ये गलती से ये प्लस लिखा है यहाँ, ये माइनस ही है ना, ये माइनस ये भी माइनस, तो ये पूरा पार्ट हो जाएगा प्लस। तो ये हो गया सिग्मा 2pz। वैसे ही अगर 2pz और 2pz, देखो इसका प्लस इसका माइनस, तो क्या होगा बनेगा, तो देखो ये ओवरलैपिंग जो है वो तो इंटरन्यूक्लियर एक्सिस के ऊपर ही है, तो सिग्मा स्टार बना ये, बट इससे क्या होगा प्लस वाला पार्ट भी छोटा हो जाएगा, ये माइनस वाला पार्ट भी छोटा, और इनके बीच में नील हो जाएगी इलेक्ट्रॉन डेंसिटी, मतलब वन नोडल प्लेन आ गया। तो इसका मतलब ये क्लियर हो गया कि जब भी सिग्मा बॉन्ड बनेगा तो नो नोडल प्लेन, जब सिग्मा स्टार बनेगा या पाई बनेगा तो वन नोडल प्लेन, और जब पाई स्टार बनेगा तो टू नोडल प्लेन्स। और नोडल प्लेन्स क्या होते हैं, द प्लेन वेयर द प्रोबेबिलिटी ऑफ फाइंडिंग द इलेक्ट्रॉन इज nil, the plane where the probability of finding the electron is nil। इसमें इलेक्ट्रॉन डेंसिटी जो है वो nil होती है, ठीक है। देखो 1s ओवरलैप किए तो सिग्मा 1s सिग्मा स्टार 1s बना, 2s ओवरलैप करेंगे तो सिग्मा 2s सिग्मा स्टार 2s बनेगा, 2px ओवरलैप करेंगे तो पाई 2px पाई स्टार 2px बनेगा, 2py जुड़ेंगे तो पाई 2py पाई स्टार 2py बनेगा, 2pz ओवरलैप करेंगे तो सिग्मा 2pz और सिग्मा स्टार 2pz। अब आ जाते हैं मॉलिक्यूलर ऑर्बिटल इलेक्ट्रॉनिक कॉन्फ़िगरेशन पे। तो अप टू नाइट्रोजन, देखो अप टू नाइट्रोजन सबसे कम एनर्जी होती है सिग्मा 1s की, फिर सिग्मा स्टार 1s, फिर सिग्मा 2s, सिग्मा स्टार 2s, पाई 2px और पाई 2py की एनर्जी इक्वल होती है, फिर सिग्मा 2pz आता है, फिर पाई 2px पाई 2py पाई स्टार 2px पाई स्टार 2py की एनर्जी भी बराबर, और सबसे ज्यादा सिग्मा स्टार 2pz की एनर्जी होती है। और O2 F2 Na2 में यहाँ पे चेंज आता है, देखो सिर्फ यहाँ पे, बाकी सब सेम है। और इनको बोल देते हैं बेटा के, क्योंकि इनर शेल्स है ना, तो इसमें भी हम इसको के लिख सकते हैं, याद रखना, ठीक है। सिर्फ हाइड्रोजन हीलियम को छोड़ के बाकी सब में हम वी कैन राइट इट एज के, क्योंकि के मतलब फर्स्ट शेल, तो फर्स्ट शेल में 1s आते हैं ना, तो सिग्मा 1s सिग्मा स्टार 1s कैन बी टेकन एज के, ठीक है। और सिग्मा 2s सिग्मा स्टार 2s सेम है, बस यहाँ पे चेंज है, देखो इसमें पाई 2px पाई 2py पहले, इसमें सिग्मा 2pz पहले, और पाई 2px पाई 2py बाद में, इसमें पाई 2px पाई 2py पहले, सिग्मा 2pz बाद। लिथियम 2, तो लिथियम की बात करें तो 1s2 2s1 होता है, तो इसमें कितने इलेक्ट्रॉन हो गए टोटल 3, तो लिथियम 2 में कितने हो जाएंगे टोटल 6। तो यहाँ पे देख लो, ये याद रखना है, पहले सिग्मा 1s में इलेक्ट्रॉन जाएगा, फिर सिग्मा स्टार 1s में जाएगा, फिर सिग्मा 2s में, तो 2 + 2 + 2 हो गए पूरे 6 इलेक्ट्रॉन। और बॉन्ड ऑर्डर क्या होगा 4 - 2, 1 बॉन्ड ऑर्डर आ जाएगा। बेरिलियम 2 में टोटल इलेक्ट्रॉन कितने हुए 4, तो बेरिलियम में 4 हुए ना, तो बेरिलियम 2 में कितने हो जाएंगे 8, तो 8 को इस कॉन्फ़िगरेशन के हिसाब से डालते जाओ, सिग्मा 1s में 2 सिग्मा स्टार 1s में 2 सिग्मा 2s में 2 सिग्मा स्टार 2s में भी 2। तो इस तरह से जो बेरिलियम 2 है उसका बॉन्ड ऑर्डर क्या आता है 0, इसका मतलब बेरिलियम 2 डज नॉट एग्जिस्ट, बेरिलियम 2 डज नॉट एग्जिस्ट। अगर क्वेश्चन आता है तो आप लिखोगे MOT के अकॉर्डिंग कि बेरिलियम 2 का जो बॉन्ड ऑर्डर है दैट इज 0, मीन देयर इज नो बॉन्ड बिटवीन 2 बेरिलियम एटम्स, इसलिए बॉन्ड ऑर्डर इज सॉरी, इसलिए बेरिलियम 2 डज नॉट एग्जिस्ट। सेम इज द केस विद हीलियम 2। नाउ बोरोन, बोरोन की बात करें तो 1s2 2s2 2p1 5 इलेक्ट्रॉन है, मतलब B2 में कितने हो जाएंगे टोटल 6, तो 6 इलेक्ट्रॉन को ये याद रख के ऐड करना है, देखो सिग्मा 1s में 2 सिग्मा स्टार 1s में 2 सिग्मा 2s में 2 सिग्मा स्टार 2s में 2 पाई 2px और पाई 2py में 1 1, पाई 2px पाई 2py में 1 1, C2 में क्या हो जाएगा पाई 2px में भी 2 पाई 2py में भी 2, तो देखो और बॉन्ड ऑर्डर आ जाएगा 1, पर देखो सिग्मा 1s सिग्मा स्टार 1s कैंसिल, सिग्मा 2s सिग्मा स्टार 2s कैंसिल, बट पाई 2px पाई स्टार 2px नहीं है, पाई 2py पाई स्टार 2py नहीं है, तो बॉन्ड जो बनेगा बेटा दैट इज पाई बॉन्ड, सिर्फ एक ही बॉन्ड बनेगा और वो होगा पाई बॉन्ड। हमने पीछे पढ़ा था कि पाई बॉन्ड इज ऑलवेज अकम्पनीड विद सिग्मा बॉन्ड, बट ये दो जो हैं B2 एंड C2 दीज आर द एक्सेप्शंस, कि इसमें C2 में 2 बॉन्ड बनते हैं और दोनों पाई बॉन्ड, अगर C2 बनता है तो सामने दिख रहा है पाई 2px 2 है, पाई स्टार 2px नील नहीं है, पाई 2py भी 2 है, पाई स्टार 2py नील नहीं है ना, तो इस तरह से बॉन्ड ऑर्डर आता है 2। अब आ जाओ N2, तो N2 के केस में क्या होगा सिग्मा 1s2 सिग्मा स्टार 1s2 सिग्मा 2s2 सिग्मा स्टार 2s2, देखो सिग्मा 1s2 और सिग्मा स्टार 2s2 1s2 को हमने के लिख दिया है, और पाई 2px पाई 2p/2 तो C2 का हो गया, फिर जो 2 इलेक्ट्रॉन एक्स्ट्रा बचे N2 में वो जाएंगे सिग्मा 2pz में। अब देखो बॉन्ड ऑर्डर 3 है, बट इसमें एक सिग्मा बॉन्ड है और 2 पाई बॉन्ड, तो ये आ गया नॉर्मल कंडीशन में, बट याद रखना B2 एंड C2 जो है दे आर एक्सेप्शंस, ये क्या है एक्सेप्शंस है। अब आ जाओ ऑक्सीजन पे, ऑक्सीजन में जब आप जाते हो, मैंने अभी बताया था आपको कि उसमें सिग्मा 2pz पहले आ जाता है और पाई 2px पाई 2py बाद में। तो टोटल इलेक्ट्रॉन O2 में कितने होंगे? 16 है ना। 8 इलेक्ट्रॉन होते हैं ना एक ऑक्सीजन में, तो 16 हुए, 2 2 4 6 8 8 इलेक्ट्रॉन चले गए। अब सिग्मा 2pz 2 10, पाई 2px पाई 2py में भी 2 2 12 14 और 2 इलेक्ट्रॉन बचे, वो कहाँ चले जाएंगे? पाई स्टार 2px में एक और पाई स्टार 2py में भी एक। अब देखो, जब हम ऑक्सीजन का बॉन्ड बनाते हैं तो एक तो सिग्मा बॉन्ड बनेगा। सिग्मा बॉन्ड कहाँ बनेगा? सिग्मा 2pz और सिग्मा स्टार 2pz में नील, ठीक है ना। अब पाई 2px में 2 और पाई स्टार 2px में 1, तो देखो 2 बॉन्डिंग और एक एंटी बॉन्डिंग। तो पाई बॉन्ड जो बना 3 इलेक्ट्रॉन बॉन्ड बना, और उसका बॉन्ड ऑर्डर बेटा होता है हाफ, और ये भी 3 इलेक्ट्रॉन बॉन्ड बना और इसका भी बॉन्ड ऑर्डर हाफ। तो इसलिए देखो, ऑक्सीजन में नॉर्मली हम जब हम उसका लुईस डॉट स्ट्रक्चर बनाते हैं तो ऐसे बना देते हैं, बनाते हैं ऐसे, बट इट इज नॉट द एक्चुअल स्ट्रक्चर। जनरली हम बना देते हैं, बट एक्चुअल स्ट्रक्चर इज दिस वन विच एक्सप्लेन इट्स प्रॉपर्टीज। कौन सी प्रॉपर्टी मैं बताता हूं, क्योंकि ये अनपेयर्ड इलेक्ट्रॉन है, जिनमें भी अनपेयर्ड इलेक्ट्रॉन होते हैं वो होते हैं पैरामैग्नेटिक। तो F2 में टोटल इलेक्ट्रॉन कितने हो गए? 18, तो 18 फिल कर दिए हमने। तो इसमें पाई 2px 2 के सामने पाई स्टार 2px 2, पाई 2py 2 के सामने पाई स्टार 2py 2, नील हो गया पाई बॉन्ड, देयर इज ओनली वन सिग्मा बॉन्ड, सिग्मा 2pz और सिग्मा स्टार 2pz नील। तो टोटल बॉन्डिंग इलेक्ट्रॉन माइनस एंटी बॉन्डिंग डिवाइड बाय 2, तो बॉन्ड ऑर्डर 1। नियोन 2 अगेन डज नॉट एग्जिस्ट, क्योंकि इसमें भी बॉन्ड ऑर्डर क्या आएगा? 0। हाँ, ये मैं बात कर रहा था कि पैरामैग्नेटिक सब्सटेंसेस, मैग्नेटिक प्रॉपर्टीज की बात हो रही है। ऐसा आ सकता है क्वेश्चन की कौन मैग्नेटिक है, पैरामैग्नेटिक है, कौन डायमैग्नेटिक है। तो पैरामैग्नेटिक क्या होते हैं? सब्सटेंसेस, जी बेटा मैं बाद में फोन करता हूँ। The substances which has unpaired electrons and are weakly attracted by the magnetic field, that is called paramagnetic substances. और diamagnetic substances क्या होते हैं? The substances which has paired electrons only and are weakly repelled by the magnetic field. एक में diamagnetic, दूसरे में paramagnetic। तो यहां से हम देख सकते हैं कि कौन कौन डायमैग्नेटिक है, कौन पैरामैग्नेटिक है। नियोन 2 तो एग्जिस्ट ही नहीं करता, उसको तो छोड़ दो। बताओ F2 पैरामैग्नेटिक है या डायमैग्नेटिक? यस बेटा, F2 इज इट पैरामैग्नेटिक और डायमैग्नेटिक? ये स्वस्तिका, माय गॉड। हेलो, ये कब से सुनाई नहीं दे रहा था? तो बेटा आप एक बार तो बोलते, मैं इतनी देर से पढ़ाई यार, बोला था। ओ आई एम रियली वेरी सॉरी। तो अब बताओ, ये डायमैग्नेटिक पैरा आपने पढ़ा है चैप्टर पहले ये? अच्छा, कोई नहीं, रिकॉर्ड मैंने किया है ये, पर ओ माय गॉड। तो मतलब एक बार कॉल कर देते कि मैं, अगर मैं नहीं बोल रहा हूँ, मुझे लगा कि सब सुन तो रहे हैं, मैं आप आराम से पढ़ाई जा रहा हूँ, कोई बात नहीं। अभी बताओ कि डायमैग्नेटिक क्या होते हैं? जिनमें पेयर्ड इलेक्ट्रॉन्स होते हैं सारे, और पैरामैग्नेटिक जिसमें के अनपेयर्ड इलेक्ट्रॉन्स होते हैं। तो F2 जो है वो पैरामैग्नेटिक है या डायमैग्नेटिक? F2 is it paramagnetic or diamagnetic? Very good. F2 is diamagnetic. And what about O2? So it is, मैं DM लिख देता हूँ, diamagnetic. And O2, बेटा O2 is paramagnetic. क्यों? क्योंकि O2 में क्या है, ये देखो एक एक इलेक्ट्रॉन है लास्ट, तो जिसमें भी अनपेयर्ड इलेक्ट्रॉन्स हो। ओके, अगर हम इस ऐसे देखें O2 को, तो इसमें सारे पेयर्ड लग रहे हैं, बट O2 का ये स्ट्रक्चर होता है, इसमें ये सिग्मा बॉन्ड और ये अनपेयर्ड इलेक्ट्रॉन बॉन्ड्स। ओके, व्हाट अबाउट N2? इज इट पैरामैग्नेटिक और डायमैग्नेटिक? तो बेटा दो दो इलेक्ट्रॉन है सब में, ये देखना है सिर्फ, किसी में भी सिंगल अनपेयर्ड इलेक्ट्रॉन नहीं है ना, तो डायमैग्नेटिक। C2, C2 डायमैग्नेटिक और पैरामैग्नेटिक? सब ऑर्बिटल्स में दो दो इलेक्ट्रॉन्स है, देखो दो मींस पेयर्ड, तो इसका मतलब डायमैग्नेटिक। B2 पैरामैग्नेटिक, क्योंकि लास्ट के दो ऑर्बिटल में देयर इज वन वन इलेक्ट्रॉन। बेरिलियम 2 डज नॉट एग्जिस्ट। एंड व्हाट अबाउट लिथियम 2? पैरा, हाँ देखो सब में दो दो इलेक्ट्रॉन है, तो इट इज डायमैग्नेटिक। तो ये अब अगर इसकी मॉलिक्यूलर ऑर्बिटल एनर्जी लेवल डायग्राम बनाए हम, तो देखो सबसे 2s और 2s ओवरलैप करेंगे, तो एक बनेगा सिग्मा 2s, दूसरा बनेगा सिग्मा स्टार 2s। वैसे ही अगर हम 2px 2py 2pz और 2px 2py 2pz ऑफ बोथ द नाइट्रोजन्स तो ओवरलैप करवाते हैं, तो 2pz क्या बनाएगा, सिग्मा 2pz एंड सिग्मा स्टार 2pz। 2px और 2px ओवरलैप करेंगे तो बनाएंगे पाई 2px एंड पाई स्टार 2px। 2py और 2py ओवरलैप करेंगे तो पाई स्टार पाई 2py एंड पाई स्टार 2py। तो इसको हम अगर देखें तो सबसे नीचे क्या है, सिग्मा 2s। देखो 1s हम नहीं ले रहे हैं, क्योंकि 1s इनर शेल है, उसको के लिख देते हैं। तो एनर्जी लेवल देखो 2s बना देंगे, सिग्मा 2s सिग्मा स्टार 2s, दोनों की एनर्जी लिख दी हमने। सिग्मा 2s की एनर्जी सबसे कम और सिग्मा स्टार 2s उसके बाद, फिर पाई 2px और पाई 2py होते हैं, फिर सिग्मा 2pz और फिर पाई स्टार 2px पाई स्टार 2py, फिर सिग्मा स्टार 2pz। एक्चुअली जो एटॉमिक ऑर्बिटल्स हैं, बॉन्डिंग मॉलिक्यूल की एनर्जी उनसे कम होती है और एंटी बॉन्डिंग की एनर्जी उनसे ज्यादा होती है। ठीक है, तो 2s ओवरलैप किए तो सिग्मा 2s बना और सिग्मा स्टार 2s, तो दोनों के इलेक्ट्रॉन दोनों के फिल कर दिए। फिर 2px 2py 2pz में एक एक इलेक्ट्रॉन है, टोटल 6 इलेक्ट्रॉन हो गए, तो 2 2 एंड 2। तो इस तरह से वी कैन अरेंज देम इन द MO डायग्राम। वैसे ही O2 के लिए लिखेंगे तो क्या करेंगे, सिर्फ यहाँ पे चेंज आएगा, सिग्मा 2pz नीचे, पाई 2px पाई 2py ऊपर। देखो O2 F2 Ne2 में सिर्फ इतना सा चेंज है, सिग्मा 2pz नीचे, पाई 2px पाई 2py ऊपर, बाकी सब सेम। तो इसमें जैसे ऑक्सीजन है, तो 2s बनाएंगे सिग्मा 2s सिग्मा स्टार 2s 2p ओवरलैप करेंगे, एक बनेगा सिग्मा 2pz, फिर पाई 2px पाई 2py, फिर पाई स्टार 2px पाई स्टार 2py। और देखो एंटी बॉन्डिंग एनर्जी एटॉमिक ऑर्बिटल p और से ज्यादा और बॉन्डिंग की नीचे। तो अब दो और दो इलेक्ट्रॉन, ये सिग्मा 2s सिग्मा स्टार 2s, अब ये 2p ओवरलैप करेंगे तो 4 और ये 4 तो 8 हो गए, तो 6 हो गए बॉन्डिंग में, और दो इलेक्ट्रॉन जो बचे वो एंटी बॉन्डिंग में, क्योंकि दोनों की एनर्जी सेम है। तो इलेक्ट्रॉन पेयरिंग कब स्टार्ट होती है? व्हेन ईच ऑर्बिटल इज सिंगली फिल्ड विद पैरेलल स्पिन। कौन सा रूल है ये जो मैंने बोला अभी कि इलेक्ट्रॉन पेयरिंग डज नॉट टेक प्लेस until and unless each orbital of equal energy or singly filled with parallel spin। क्या बोलते हैं इसको? हाँ, वेरी गुड, हर्ट्ज रूल ऑफ मैक्सिमम मल्टीप्लिसिटी। तो इस तरह से ये दो अनपेयर्ड इलेक्ट्रॉन आए, O2 पैरामैग्नेटिक हुआ, और इसका जो इलेक्ट्रॉनिक कॉन्फ़िगरेशन लिखेंगे तो इसको देख के लिख सकते हैं कि O2 में पहले तो K, फिर सिग्मा 2s2 सिग्मा स्टार 2s2, फिर सिग्मा 2pz2 पाई 2px पाई 2py 2, ठीक है, पाई स्टार 2px पाई स्टार 2py 1, 1, ठीक है। तो ये हो गया O2 के लिए। वैसे ही आप B2 C2 F2 की एमओ डायग्राम बना सकते हो। तो इसमें एक रूल और, बॉन्ड ऑर्डर और बॉन्ड लेंथ में क्या रिलेशन होता है? इनवर्स रिलेशन होता है। बॉन्ड ऑर्डर और बॉन्ड लेंथ इनवर्सली प्रोपोर्शनल है, और बॉन्ड स्ट्रेंथ के डायरेक्टली प्रोपोर्शनल। तो जैसे O2 पॉजिटिव, O2 नेगेटिव और O2 2 नेगेटिव की बात करें, तो O2 का आपको अगर कॉन्फ़िगरेशन पता है तो यू कैन प्रेडिक्ट फॉर O2 पॉजिटिव, O2 नेगेटिव एंड O2 2 नेगेटिव। क्योंकि अगर एक इलेक्ट्रॉन हम बॉन्डिंग में ऐड करते हैं, ठीक है, या एक इलेक्ट्रॉन एंटी बॉन्डिंग से रिमूव करते हैं, देखो बॉन्डिंग में ऐड करो या एंटी बॉन्डिंग से रिमूव करो, एक ही जैसा उनको असर पड़ेगा। उससे बॉन्ड ऑर्डर कितने से इंक्रीज होता है? बाई हाफ। और अगर कोई इलेक्ट्रॉन हम एंटी बॉन्डिंग में ऐड करते हैं या बॉन्डिंग से रिमूव करते हैं तो भी बॉन्ड ऑर्डर इज इंक्रीज्ड बाई, बॉन्ड ऑर्डर इज डिक्रीज्ड बाई हाफ, ठीक है। तो अब हम बात करते हैं O2 की। तो O2 में क्या होता है कि लास्ट इलेक्ट्रॉन किसमें होता है? एंटी बॉन्डिंग में, पाई स्टार 2px1 पाई स्टार 2py1। तो O2 पॉजिटिव करेंगे, इसका मतलब वन ऑफ द इलेक्ट्रॉन इज रिमूव्ड फ्रॉम द एंटी बॉन्डिंग, क्योंकि इलेक्ट्रॉन रिमूव कहां से होता है? ये होमो का मतलब है हाईएस्ट ऑक्यूपाइड मॉलिक्यूलर ऑर्बिटल। तो इलेक्ट्रॉन O2 पॉजिटिव बनाएंगे तो रिमूव कहां से होगा? पाई स्टार से, हाईएस्ट। पाई स्टार 2px से भी हो सकता है, पाई स्टार 2py से भी हो सकता है, किसी भी एक से। तो एक इलेक्ट्रॉन एंटी बॉन्डिंग से गया तो बॉन्ड ऑर्डर इंक्रीज हो जाएगा, तो 2 से क्या हो जाएगा? 2.5। O2 नेगेटिव करेंगे, इसका मतलब एक इलेक्ट्रॉन ऐड होगा, पर किसमें होगा? एंटी बॉन्डिंग में ही ऐड होगा, तो इसका मतलब बॉन्ड ऑर्डर डिक्रीज बाय हाफ, तो 1.5 हो जाएगा। O2 2 नेगेटिव करेंगे तो एक और इलेक्ट्रॉन आ जाएगा एंटी बॉन्डिंग में, तो बॉन्ड ऑर्डर कितना हो जाएगा? 1.0। तो देखो बॉन्ड ऑर्डर का क्या हुआ? O2 पॉजिटिव का सबसे ज्यादा, O2 उससे कम, O2 नेगेटिव उससे कम, O2 2 नेगेटिव सबसे कम। अगर बॉन्ड लेंथ की बात करें तो सबसे कम बॉन्ड लेंथ किसकी होगी? O2 पॉजिटिव की, उससे ज्यादा होगी O2 की। मतलब बॉन्ड ऑर्डर और बॉन्ड लेंथ में इनवर्स रिलेशन। ये क्वेश्चन इंपॉर्टेंट है, आ सकता है ऐसा। ओके, तो ये हो गया अबाउट एमओ थियरी। जैसे N2 पॉजिटिव N2 नेगेटिव है, तो इसमें भी ऐसे होगा कि N2 में सिग्मा 2p(Z2) होता है, लास्ट इलेक्ट्रॉन सिग्मा 2p(Z) में होता है, मतलब इसका बॉन्ड ऑर्डर होता है 3। तो N2 पॉजिटिव में इलेक्ट्रॉन कहाँ से रिमूव होगा, बॉन्डिंग से, और N2 नेगेटिव लिखेंगे तो जो इलेक्ट्रॉन रिमूव होगा वो कहाँ से होगा, सॉरी ऐड होगा, वो किसमें होगा, एंटी बॉन्डिंग में। देखो इसमें दिखाता हूँ मैं आपको, ये है N2, ठीक है। तो N2 अगर पॉजिटिव करोगे तो सिग्मा 2p(Z) से इलेक्ट्रॉन रिमूव होगा, मतलब बॉन्डिंग से रिमूव होगा। और अगर मैं N2 नेगेटिव करता हूं तो नेक्स्ट शेल में इलेक्ट्रॉन नेक्स्ट ऑर्बिटल में जाएगा, दैट इज pi स्टार 2px pi स्टार 2py। तो या तो बॉन्डिंग में से रिमूव होगा या एंटी बॉन्डिंग में ऐड होगा। तो बॉन्डिंग से रिमूव करो या एंटी बॉन्डिंग में ऐड करो। देखो बॉन्डिंग से इलेक्ट्रॉन रिमूव करो या एंटी बॉन्डिंग में ऐड करो, दोनों केस में बॉन्ड ऑर्डर इज डिक्रीज बाय हाफ। इसका मतलब N2 का बॉन्ड ऑर्डर 3 है, तो N2 पॉजिटिव का और N2 नेगेटिव का दोनों का ही बॉन्ड ऑर्डर हो जाएगा 2.5 एंड 2.5। अब आइसो इलेक्ट्रॉनिक जो स्पीशीज होते हैं उन सबका बॉन्ड ऑर्डर सेम ही होता है, जैसे CO, N2, NO पॉजिटिव, CN नेगेटिव, इन सबका बॉन्ड ऑर्डर सेम हो, ठीक है। जैसे F2 और O2 2 नेगेटिव, बॉन्ड ऑर्डर 1 रहेगा। तो ऐसे भी हम याद कर सकते हैं कि नंबर ऑफ इलेक्ट्रॉन्स काउंट करो और बॉन्ड ऑर्डर भी लिख लो। जैसे अगर इलेक्ट्रॉन होंगे 10 तो बॉन्ड ऑर्डर होगा 1, 12 तो 2, 14 3, 1 2 3 3 2 1। देखो 1 2 3 देन 2 1 0, 16 होगा 2, 18 होगा 1, 20 होंगे इलेक्ट्रॉन 0। तो वैसे ही 10 से 12 में गए तो 1 से 2 गया, तो 11 होंगे तो क्या हो जाएगा 1.5। वैसे 12 टू 14 गए तो 3 हो गया, तो 13 होंगे तो कितना होगा 2.5। 14 से 16 गए तो बॉन्ड ऑर्डर 2 हो गया, 3 से 2 डिक्रीज हुआ, तो 15 होगा तो 2.5, 17 होंगे तो 1.5, 19 होंगे तो 0.5। सो ये हो गया ऑर्डर, मतलब बॉन्ड ऑर्डर निकालने का एक शॉर्टकट। ओके, तो अब आ जाओ लास्ट टॉपिक ऑफ दिस चैप्टर, दैट इज हाइड्रोजन बॉन्डिंग। तो हाइड्रोजन बॉन्डिंग क्या होता है कि व्हेन हाइड्रोजन इज अटैच्ड टू एन एटम, और एटम क्या होना चाहिए, स्मॉल इन साइज एंड हाईली इलेक्ट्रोनेगेटिव। atom should be small in size and it should be highly electronegative। तो स्मॉल साइज्ड और हाईली इलेक्ट्रोनेगेटिव एटम जब अटैच हो हाइड्रोजन से तो क्या होगा, हाइड्रोजन गेट पार्शियल पॉजिटिव एंड दैट एटम गेट्स पार्शियल नेगेटिव। तो इस मोर इलेक्ट्रोनेगेटिव एटम का दूसरे मॉलिक्यूल के या सेम मॉलिक्यूल के हाइड्रोजन के साथ जो इंटरेक्शन होगा, that is called hydrogen bond। This is called H bonding। And these two conditions, the atom which is attached to hydrogen is small in size and highly electronegative, they are satisfied by 3 atoms, F O N। phone करके याद रख सकते हो आप, when hydrogen is attached to phone, F O N, ठीक है, उसको हम बोलते हैं कि हाइड्रोजन बॉन्डिंग बना रहा है। जैसे HF हाइड्रोजन बॉन्डिंग बना सकता है, H2O हाइड्रोजन बॉन्डिंग बनाएगा, अमोनिया हाइड्रोजन बॉन्डिंग बनाएगा। और अगर हाइड्रोजन एक एटम का हो और फ्लोरीन किसी दूसरे एटम का हो, देखो HF जो बनाता है ना हाइड्रोजन बॉन्ड, वो जिगजैग फैशन में होता है, ठीक है, ऐसे जिगजैग फैशन में बनता है HF का। तो HF में क्या है, हाइड्रोजन ऑफ वन मॉलिक्यूल और फ्लोरीन ऑफ द अदर मॉलिक्यूल। तो ये जो हाइड्रोजन बॉन्डिंग बनती है इसको बोलते हैं बेटा इंटर मॉलिक्यूलर हाइड्रोजन बॉन्डिंग, और इससे एसोसिएशन बढ़ जाती है, बॉइलिंग पॉइंट इंक्रीजेस, बॉइलिंग पॉइंट इंक्रीज कर जाता है, ठीक है। और दूसरा होता है इंट्रा मॉलिक्यूलर हाइड्रोजन बॉन्डिंग। इंट्रा मॉलिक्यूलर जो हाइड्रोजन बॉन्डिंग है उसमें क्या होता है कि हाइड्रोजन और जो भी दूसरा एटम है, जैसे मैं ऑर्थोनाइट्रोफिनोल है, क्या बोलते हैं इसको, ऑर्थोनाइट्रोफिनोल। तो इसका H और इसका ऑक्सीजन, तो ये हाइड्रोजन बॉन्ड बनाते हैं। और ये देखो हाइड्रोजन भी इसी में है, ऑक्सीजन भी इसी में ही है, डिफरेंट ग्रुप्स हैं बट सेम मॉलिक्यूल के हैं, तो इसलिए इसको बोलते हैं इंट्रा मॉलिक्यूलर हाइड्रोजन बॉन्डिंग। अब इंट्रा मॉलिक्यूलर हाइड्रोजन बॉन्डिंग और इंटर मॉलिक्यूलर हाइड्रोजन बॉन्डिंग में जो डिफरेंस है, जैसे एक और मॉलिक्यूल है इसी का ही, ये जो है इसको बोलते हैं पैरानाइट्रोफिनोल, एक ऑर्थोनाइट्रोफिनोल दूसरा पैरानाइट्रोफिनोल। तो पैरानाइट्रोफिनोल जो है वो बनाता है इंटर मॉलिक्यूलर हाइड्रोजन बॉन्डिंग। इसमें कौन सी बनती है, इंटर मॉलिक्यूलर हाइड्रोजन बॉन्डिंग। अब इंटर मॉलिक्यूलर हाइड्रोजन बॉन्डिंग से बॉइलिंग पॉइंट इंक्रीज होता है और इंट्रा से बॉइलिंग पॉइंट क्या करता है, डिक्रीज, क्योंकि वो अपने आप में मॉलिक्यूल आइसोलेट हो जाएगा ना, वो दूसरे से इंटरेक्ट नहीं करेगा। तो इंटर और इंट्रा मॉलिक्यूलर हाइड्रोजन बॉन्डिंग में डिफरेंस समझ आ गया बेटा आपको। इंटर में क्या होता है कि दोनों मॉलिक्यूल जो हैं अलग अलग मॉलिक्यूल के हाइड्रोजन और नाइट्रोजन फ्लोरीन ऑक्सीजन होते हैं, और इंट्रा में सेम मॉलिक्यूल के डिफरेंट ग्रुप्स के बीच में वो बॉन्ड बनता है, तो दैट इज कॉल्ड इंट्रा मॉलिक्यूलर हाइड्रोजन बॉन्डिंग। दिस इज ऑल अबाउट ये हाइड्रोजन बॉन्डिंग पार्ट, है ना। और हाँ, ये डिफरेंस आप कर सकते हो बॉन्डिंग और एंटी बॉन्डिंग मॉलिक्यूलर ऑर्बिटल में। व्हाट इज द बेसिक डिफरेंस बिटवीन बॉन्डिंग एंड एंटी बॉन्डिंग मॉलिक्यूलर ऑर्बिटल, ये क्वेश्चन आ सकता है। तो देखो बॉन्डिंग मॉलिक्यूलर ऑर्बिटल जो है उसमें क्या होता है, एडिशन ऑफ वेव फंक्शन, देखा था ना, एडिटिव इफेक्ट होता है एटॉमिक ऑर्बिटल्स का। बट एंटी बॉन्डिंग में क्या होता है, सब्ट्रैक्टिव इफेक्ट, दोनों में सब्ट्रैक्शन होता है। और बॉन्डिंग में जो इलेक्ट्रॉन डेंसिटी है न्यूक्लियर के बीच में वो बढ़ जाती है, और एंटी बॉन्डिंग में इलेक्ट्रॉन डेंसिटी जो है बिटवीन द न्यूक्लियर वो क्या होती है, डिक्रीज, और इसलिए बॉन्ड अनस्टेबल हो जाता है इस केस में, इसमें बॉन्ड स्टेबल हो जाता है। और इसमें इलेक्ट्रॉन जो प्रेजेंट होते हैं बॉन्डिंग ऑर्बिटल में उससे अट्रैक्शन बढ़ता है एटम्स के बीच में। बट एंटी बॉन्डिंग क्या होता है, जो इलेक्ट्रॉन प्रेजेंट होते हैं एंटी बॉन्डिंग में दैट रिजल्ट इन द रिपल्शन बिटवीन द टू एटम्स, उसमें दोनों के बीच में क्या होता है, रिपल्शन। और बॉन्डिंग में क्योंकि अट्रैक्टिव फोर्सेस इन्वॉल्व होती है, तो ये इन मॉलिक्यूलर ऑर्बिटल की एनर्जी क्या होती है, लोअर देन द प्योर एटॉमिक ऑर्बिटल्स, एंड दिस इज द कॉज फॉर देयर स्टेबिलिटी, क्योंकि एनर्जी कम हो रही है इसमें। बट एंटी बॉन्डिंग में रिपल्सिव इंटरेक्शन होता है, इसलिए मॉलिक्यूलर ऑर्बिटल जो है दे हैव हायर एनर्जी देन द एटॉमिक ऑर्बिटल्स, एंड उससे क्या होती है, स्टेबिलिटी लोअर, और बॉन्ड फॉर्मेशन नहीं होती इसमें, एंटी बॉन्डिंग हो जाते हैं वो। और इसमें क्या होता है, जो लोब्स होते हैं जो कंबाइनिंग एटॉमिक ऑर्बिटल्स के, उनका साइन सेम होता है, एक का प्लस तो दूसरे का भी प्लस, सेम साइन वाले ओवरलैप करते हैं। बट एंटी बॉन्डिंग में क्या होता है, जो लोब्स होते हैं कंबाइनिंग एटॉमिक ऑर्बिटल्स के, उनका साइन क्या होता है, अपोजिट। और ये रिप्रेजेंट करते हैं बाय सिग्मा एंड पाई, और एंटी बॉन्डिंग जो है बाय सिग्मा स्टार एंड पाई स्टार। तो ये हो गया बॉन्डिंग और एंटी बॉन्डिंग में डिफरेंस। ये भी क्वेश्चन आ सकता है। देखो दो क्वेश्चन, एक सिग्मा और पाई में बॉन्ड में डिफरेंस बताया था, और बॉन्डिंग और एंटी बॉन्डिंग मॉलिक्यूल का डिफरेंस, इन दोनों में से कोई आ सकता है। सिग्मा पाई वाला के चांसेस ज्यादा है, दैट इज मोर इम्पोर्टेंट।
Hydrogen bonding. So tell me, what is hydrogen bonding? Actually, hydrogen bonding, it is not like ionic bond or covalent bond. It is actually simple dipolar attraction. It is dipolar attraction between hydrogen atom and more electronegative atoms like fluorine, oxygen, nitrogen. We call it as phone, F-O-N, phone. When hydrogen interact with phone, that is called hydrogen bonding. So the atom attached to hydrogen should be small in size and is highly electronegative. This is the condition of the atom attached to hydrogen. Okay, and these two conditions are satisfied by fluorine, oxygen and nitrogen. I call it phone, F-O-N, P-H-O-N-E. Okay. So actual definition of hydrogen bonding is, it is dipolar attraction. Like see, if we have H and A, H is hydrogen and A is the atom which is small in size and highly electronegative. A is either fluorine, oxygen or nitrogen. So A gets partial negative and hydrogen gets partial positive. So this A will interact with hydrogen of other molecule or other group of the same molecule. Okay, so this type of interaction is called hydrogen bonding, and it is denoted by this shaded arrow, broken arrow. Okay, it is denoted by this type of notification. Okay, so this is definition of hydrogen bonding. Now types of hydrogen bonding. Types of hydrogen bonding. So first is hydrogen when attached to an atom which is small in size and is highly electronegative, then hydrogen gets partial positive and that atom which is more electronegative gets partial negative, and this partial negatively charged atom when attract the partially positively charged hydrogen of the other molecule or other group attached in the same molecule, then that type of bonding is called hydrogen bonding. This is one type of dipole-dipole attraction. This is dipole, this is also dipole. So these dipoles attract each other but it is a special type of dipole-dipole attraction. Now, types of hydrogen bonding. I can write here types of hydrogen bonding, right? Yes, types of hydrogen bonding. So it is intermolecular hydrogen bonding and intramolecular hydrogen bonding. Intramolecular hydrogen bonding. Okay. Now, according to intermolecular hydrogen bonding, in this case, hydrogen belongs to one molecule attract atom A belongs to other molecule. Like say inter-school competition between different schools, competition between different schools. Inter-college competition means between two colleges. Let's say intermolecular attraction, hydrogen bonding means hydrogen bonding between different molecules. So like in ammonia or HF, in HF, okay. So HF, it is like zigzag, okay. F likewise. So this type of hydrogen bonding is called intermolecular hydrogen bonding. F negative, HF, F negative, means one FH, then there is hydrogen bonding, complete, again hydrogen bonding, complete, hydrogen bonding, complete. Partially positive, partial negative, right? It is like this. Okay, so that is called intermolecular hydrogen bonding. Even in ammonia N H. So H likewise, these are continue like this. So this is called intermolecular hydrogen bonding. Even in water, ice, there are intermolecular hydrogen bonding, like say in water. This is about ammonia. In water, in ice, OH. There are two lone pairs and the two bond pairs, like this. Then this is hydrogen hydrogen bonding in ice. Okay, so these are cages. Say there are different cages are formed. You know that when we melt ice, what happened? There are some cages. Those are the cages. So when ice melts, what happened? Water comes into these cages, so volume decreases. So volume of ice or density of ice, or we can say, if question is why ice floats on water, what do you write? Yes, tell me. This is the structure of ice, okay? Tell me, if question is why ice floats on water, what will you write? This is question of 8th standard. Why ice floats on water? Yes, because density of ice is less than that of water. And why density of ice is less? Because of the formation of these cages, and that is hydrogen bonding is responsible for that. So it is because of intermolecular hydrogen bonding. So in ice there are hexagonal, these are hexagonal cage like structures. So its volume is large and density is less than that of, because when ice melts, these cages are filled with water, so volume decreases, so density increases. Its volume is large and density is less than that of water. Okay, so ice, so density of ice is less, so ice floats on water. And how these cages are formed? Because of intermolecular hydrogen bonding. Yes, good beta. Next, intramolecular hydrogen bonding. So because of intermolecular hydrogen bonding, density increases, boiling point increases, okay? But intramolecular hydrogen bonding, so intra means when we have nitro and OH. See, hydrogen and atom, more electronegative atom, both are the part of the same molecule but in different groups. Okay, so that inter-house competition means intra-school. So these two groups are attached to the same molecule. It is called ortho-nitrophenol. Structure, you can remember now why it is known as ortho-nitrophenol. Okay, I will let you know when we start organic chemistry. Okay, so it is ortho-nitrophenol. In ortho-nitrophenol, there is a formation of hydrogen bonding between when hydrogen bonding is formed between hydrogen of one group and atom A of other group in the same molecule that is called intramolecular hydrogen bonding. And because of intramolecular hydrogen bonding, boiling point decreases, it becomes inert, it cannot interact with other molecule, like in, even this is called salicylic acid. This is salicylic acid. So in this case, the condition is that groups, both are polar groups, and groups should be at 1,2 position. Both are at 1,2 position. Okay, this is also called 2-hydroxy benzoic acid. So this is about hydrogen bonding.